Tantor Audio presents The Science of Interstellar by Kip Thorne. Narrated by Eric Michael Summerer. Publisher's note: this audiobook is packaged with bonus material, which has been included on the first audio and MP3 CD. If you downloaded this audiobook in a digital format, please visit tantor.com and type The Science of Interstellar into the search box. Follow the link to the book's page, then click on PDF Extra 1. When prompted, enter the access code GALAXY to access the bonus material. If you encounter any issues downloading the PDF, please email customerservice@tantor.com for assistance. Forward. One of the great pleasures of working on Interstellar has been getting to know Kip Thorne. His infectious enthusiasm for science was obvious from our first conversation, as was his reluctance to proffer half-formed opinions. His approach to all the narrative challenges that I threw him was always calm, measured, and above all, scientific. In trying to keep me on the path of plausibility, he never showed impatience with my unwillingness to accept things on trust, although my 2-week challenge to his faster-than-light prohibition might have elicited a gentle sigh. He saw his role not as science police, but as narrative collaborator, scouring scientific journals and academic papers for solutions to corners I'd written myself into. Kip has taught me the defining characteristic of science, its humility in the face of nature's surprises. This attitude allowed him to enjoy the possibilities that speculative fiction presented for attacking paradox and unknowability from a different angle, storytelling. This book is ample demonstration of Kip's lively imagination and his relentless drive to make science accessible to those of us not possessed of his massive intellect or his immense body of knowledge. He wants people to understand and get excited about the crazy truths of our universe. This book is structured to let the listener dip into a topic as deeply as their affinity for science prompts them. No one is left behind, and everyone gets to experience some of the fun I had trying to keep up with Kip's agile mind. Christopher Nolan, Los Angeles, California, July 29, 2014. Preface. I've had a half-century-long career as a scientist. It's been joyously fun, most of the time, and has given me a powerful perspective on our world and the universe. As a child, and later as a teenager, I was motivated to become a scientist by reading science fiction by Isaac Asimov, Robert Heinlein, and others, and popular science books by Asimov and the physicist George Gamow. To them, I owe so much. I've long wanted to repay that debt by passing their message on to the next generation, by enticing youths and adults alike into the world of science, real science, by explaining to non-scientists how science works, and what great power it brings to us as individuals, to our civilization, and to the human race. Christopher Nolan's film Interstellar is an ideal messenger for that. I had the great luck, and it was luck, to be involved with Interstellar from its inception. I helped Nolan and others weave real science into the film's fabric. Much of Interstellar's science is at or just beyond today's frontiers of human understanding. This adds to the film's mystique, and it gives me an opportunity to explain the differences between firm science, educated guesses, and speculation. It lets me describe how scientists take ideas that begin as speculation and prove them wrong, or transform them into educated guesses or firm science. I do this in 2 ways. First, I explain what is known today about phenomena seen in the movie, black holes, wormholes, singularities, the fifth dimension, and the like, and I explain how we learned what we know, and how we hope to master the unknown. Second, I interpret, from a scientist's viewpoint, what we see in Interstellar, much as an art critic or ordinary viewer interprets a Picasso painting. My interpretation is often a description of what I imagine might be going on behind the scenes, the physics of the black hole Gargantua, its singularities, horizon, and visual appearance, how Gargantua's tidal gravity could generate 4,000-foot water waves on Miller's planet, how the tesseract, an object with 4 space dimensions, could transport 3-dimensional Cooper through the 5-dimensional bulk. Sometimes my interpretation is an extrapolation of Interstellar's story beyond what we see in the movie. For example, how Professor Brand, long before the movie began, might have discovered the wormhole via gravitational waves that traveled from a neutron star near Gargantua through the wormhole to Earth. These interpretations, of course, are my own. They are not endorsed by Christopher Nolan any more than an art critic's interpretations were endorsed by Pablo Picasso. They are my vehicle for describing some wonderful science. Some segments of this book may be rough going. That's the nature of real science. It requires thought, sometimes deep thought. But thinking can be rewarding. If your struggle to understand is fruitless, then that's my fault, not yours, and I apologize. I hope that at least once you find yourself, in the dead of night, half asleep, puzzling over something I have written, as I puzzled at night over questions that Christopher Nolan asked me when he was perfecting his screenplay. And I especially hope that, at least once in the dead of night, as you puzzle, you experience a eureka moment, as I often did with Nolan's questions. I'm grateful to Christopher Nolan, Jonathan Nolan, Emma Thomas, Linda Obst, and Steven Spielberg for welcoming me into Hollywood and giving me this wonderful opportunity to fulfill my dream, to pass on to the next generation my message of the beauty, the fascination, and the power of science. Kip Thorne, Pasadena, California, May 15, 2014. 1. A Scientist in Hollywood. The Genesis of Interstellar. Linda Obst, my Hollywood partner. The seed for Interstellar was a failed romance that warped into a creative friendship and partnership. In September 1980, my friend Carl Sagan phoned me. He knew I was a single father, raising a teenage daughter, or trying to do so, I wasn't very good at it, and living a Southern California singles life. I was only a bit better at that, while pursuing a theoretical physics career. At that, I was a lot better. Carl called to propose a blind date. A date with Linda Obst to attend the world premiere of Carl's forthcoming television series, Cosmos. Linda, a brilliant and beautiful counterculture and science editor for the New York Times Magazine, was recently transplanted to Los Angeles. She had been dragged there kicking and screaming by her husband, which contributed to their separation. Making the best of a seemingly bad situation, Linda was trying to break into the movie business by formulating the concepts for a movie called Flashdance. The Cosmos premiere was a black tie event at the Griffith Observatory. Klutz that I was, I wore a baby blue tuxedo. Everybody who was anybody in Los Angeles was there. I was completely out of my element, and had a glorious time. For the next 2 years, Linda and I dated on and off, but the chemistry just wasn't right. Her intensity enthralled and exhausted me. I debated whether the exhaustion was worth the highs, but the choice wasn't mine. Perhaps it was my velour shirts and double-knit pants. I don't know. Linda soon lost romantic interest in me, but something better was growing. A lasting and creative friendship and partnership between two very different people from very different worlds. Fast forward to October 2005, another of our occasional one-on-one dinners where conversation would range from recent cosmological discoveries to left-wing politics to great food to the shifting sands of movie-making. Linda by now was among Hollywood's most accomplished and versatile producers: Flashdance, The Fisher King, Contact, How to Lose a Guy in 10 Days. I had married. My wife, Carol E. Winstein, had become best friends with Linda. And I'd not done badly in the world of physics. Over dinner, Linda described an idea she had conceived for a science fiction movie and asked me to help her flesh it out. This would be her second venture into science fiction, a collaboration with me, modeled on her previous collaboration with Carl Sagan on the movie Contact. I never imagined myself helping create a movie. I never coveted a presence in Hollywood beyond a vicarious one through Linda's adventures. But working with Linda appealed to me, and her ideas involved wormholes, an astrophysics concept I had pioneered, so she easily lured me into brainstorming with her. During the next 4 months, over a few dinners and emails and phone calls, we formulated a rough vision for the film. It included wormholes, black holes, and gravitational waves, a universe with 5 dimensions, and human encounters with higher dimensional creatures. But most important to me was our vision for a blockbuster movie grounded from the outset in real science. Science at and just beyond the frontiers of human knowledge. A film in which the director, screenwriters, and producers respect the science, take inspiration from it, and weave it into the movie's fabric, thoroughly and compellingly. A film that gives the audience a taste of the wondrous things that the laws of physics can and might create in our universe, and the great things humans can achieve by mastering the physical laws. A film that inspires many in the audience to go learn about the science, and perhaps even pursue careers in science. 9 years later, Interstellar is achieving all we envisioned. But the path from there to here has been a bit like the perils of Pauline, with many a spot where our dream could have collapsed. We acquired and then lost the legendary director Steven Spielberg. We acquired a superb young screenwriter, Jonathan Nolan, and then lost him twice, at crucial stages, for many months each. The movie sat in limbo, directorless, for 2.5 years. Then, wondrously, it was resurrected and transformed in the hands of Jonathan's brother, Christopher Nolan, the greatest director of his young generation. Steven Spielberg, the initial director. In February 2006, 4 months after we began brainstorming, Linda had lunch with Todd Feldman, Spielberg's agent at the Creative Artists Agency, CAA. When Feldman asked what movies she was working on, she described her collaboration with me, and our vision for a sci-fi movie with real science woven in from the outset, our dream for Interstellar. Feldman got excited. He thought Spielberg might be interested and urged Linda to send him a treatment that very day. A treatment is a description of the story and characters, usually 20 pages or longer. All we had in writing were a few email exchanges and notes from a few dinner conversations. So we worked at whirlwind speed for a couple of days to craft an 8-page treatment we were proud of and sent it off. A few days later, Linda emailed me. Spielberg has read it and is very interested. We may need to have a little meeting with him. Game? XX, Linda. Of course I was game. But a week later, before any meeting could be arranged, Linda phoned. Spielberg is signing on to direct our Interstellar. Linda was ecstatic. I was ecstatic. This kind of thing never happens in Hollywood, she told me. Never. But it did. I then confessed to Linda that I had seen only one Spielberg movie in my life, E.T., of course. As an adult, I had never been all that interested in movies. So she gave me a homework assignment. Spielberg movies Kip must watch. A month later, on March 27, 2006, we had our first meeting with Spielberg, or Steven, as I began to call him. We met in a homey conference room in the heart of his movie production company, Amblin, in Burbank. At our meeting, I suggested to Steven and Linda 2 guidelines for the science of Interstellar. 1. Nothing in the film will violate firmly established laws of physics, or our firmly established knowledge of the universe. 2. Speculations, often wild, about ill-understood physical laws and the universe will spring from real science, from ideas that at least some respectable scientists regard as possible. Steven seemed to buy in, and then accepted Linda's proposal to convene a group of scientists to brainstorm with us an interstellar science workshop. The workshop was on June 2nd at the California Institute of Technology, Caltech, in a conference room down the hall from my office. It was an 8-hour, freewheeling, intoxicating discussion among 14 scientists, astrobiologists, planetary scientists, theoretical physicists, cosmologists, psychologists, and a space policy expert, plus Linda, Steven, and Steven's father, Arnold, and me. We emerged, exhausted but exhilarated with a plethora of new ideas and objections to our old ideas, stimuli for Linda and me as we revised and expanded our treatment. It took us 6 months due to our other commitments, but by January 2007, our treatment had grown to 37 pages, plus 16 pages about the science of Interstellar. Jonathan Nolan, the screenwriter. In parallel, Linda and Stephen were interviewing potential screenwriters. It was a long process that ultimately converged on Jonathan Nolan, a 31-year-old who had co-authored, with his brother Christopher, just 2 screenplays, The Prestige and The Dark Knight, both big hits. Jonathan, or Jonah as his friends call him, had little knowledge of science, but he was brilliant and curious and eager to learn. He spent many months devouring books about all the science relevant to Interstellar and asking probing questions. And he brought to our film big new ideas that Stephen, Linda, and I embraced. Jonah was wonderful to work with. He and I brainstormed together many times about the science of Interstellar, usually over a 2 or 3 hour lunch at the Caltech faculty club, the Athenaeum. Jonah would come to lunch brimming with new ideas and questions. I would react on the spot. This is scientifically possible, that isn't. My reactions were sometimes wrong. Jonah would press me. Why? What about? But I'm slow. I would go home and sleep on it. In the middle of the night, with my gut reactions suppressed, I would often find some way to make what he wanted to work, or find an alternative that achieved the end he sought. I got good at creative thinking when half asleep. The next morning, I would assemble the semi-coherent notes I had written during the night, decipher them, and write Jonah an email. He would respond by phone or email or another lunch, and we would converge. In this way, we came to gravitational anomalies, for example, and the challenge of harnessing them to lift humanity off Earth. And I discovered ways, just beyond the bounds of current knowledge, to make the anomalies scientifically possible. At crucial times, we brought Linda into the mix. She was great at critiquing our ideas and would send us spinning off in new directions. In parallel with our brainstorming, she was working her magic to keep Paramount Pictures at bay so we could maintain our creative autonomy, and planning the next phases of turning Interstellar into a real movie. By November 2007, Jonah, Linda, Stephen, and I had agreed on the structure for a radically revised story based on Linda's and my original treatment, Jonah's big ideas, and the many other ideas that arose from our discussions. And Jonah was deep into writing. Then, on November 5th, 2007, the Writers Guild of America called a strike. Jonah was forbidden to continue writing and disappeared. I panicked. Will all our hard work, all our dreams be for naught? I asked Linda. She counseled patience, but was clearly very upset. She vividly tells the story of the strike in Scene 6 of her book Sleepless in Hollywood. The scene is titled The Catastrophe. The strike lasted 3 months. On February 12th, when it ended, Jonah returned to writing and to intense discussions with Linda and me. Over the next 16 months, he produced a long, detailed outline for the screenplay, and then 3 successive drafts of the screenplay itself. When each was finished, we met with Stephen to discuss it. Stephen would ask probing questions for an hour or more before proffering suggestions, requests, or instructions for changes. He was not very hands-on, but he was thoughtful, incisive, creative, and sometimes firm. In June 2009, Jonah gave Stephen draft 3 of the screenplay and disappeared from the scene. He had long ago committed to write The Dark Knight Rises and had been delaying for month after month while working on Interstellar. He could delay no more, and we were without a screenwriter. On top of that, Jonah's father became gravely ill. Jonah spent many months in London by his father's side until his father's death in December. Through this long hiatus, I feared that Stephen would lose interest. But Stephen hung in there with us, awaiting Jonah's return. He and Linda could have hired somebody else to complete the screenplay, but they so valued Jonah's talents that they waited. Finally, in February 2010, Jonah was back, and on March 3rd, Stephen, Linda, Jonah, and I had a very productive meeting to discuss Jonah's 9-month-old draft 3. I was feeling a bit giddy. At last, we were back on track. Then, on June 9th, with Jonah deep into draft 4, I got an email from Linda. We have a Stephen deal problem. I'm into it. But it was not soluble. Spielberg and Paramount could not reach an agreement for the next phase of Interstellar, and Linda couldn't broker a solution. Suddenly, we had no director. Interstellar was going to be very expensive, Stephen and Linda had independently told me. There were very few directors with whom Paramount would entrust a movie of this magnitude. I envisioned Interstellar in limbo, dying a slow death. I was devastated. So was Linda at first. But she is a superb problem solver. Christopher Nolan, the director and screenwriter. Only 13 days after Linda's "We have a Stephen deal problem" email, I opened my email queue to find a euphoric follow-on message. Great talk with Emma Thomas. Emma is Christopher Nolan's wife/producer and collaborator on all his movies. She and Christopher were interested. Linda was tremulous with excitement. Jonah called and told her, "This is the best possible outcome." But the deal, for many reasons, would not be finalized for 2.5 years, though we were fairly certain Christopher and Emma were committed. So we sat and waited. June 2010 through 2011 to September 2012. Throughout, I fretted. In front of me, Linda projected an air of confidence, but she later confided having written these words to herself. Tomorrow we could wake up and Chris Nolan could be gone after 2.5 years of waiting. He could come up with his own idea. Another producer could hand him a script he likes more. He could decide to take a break. Then I would have been wrong to have waited for him all this time. It happens. That is my life, the lives of creative producers. But he's the perfect director for us. So we wait. At last, negotiations began, far, far above my pay grade. Christopher Nolan would direct only if Paramount would share the movie with Warner Brothers, the studio that had made his last few movies. So a deal, an extremely complex deal, had to be struck between the two studios, normally rivals. Finally, on December 18th, 2012, Linda emailed, "Pear and Warner's agreed to terms. Well, chop my liver, starting in spring." And from then on, with Interstellar in Christopher Nolan's hands, so far as I could tell, all was clear sailing. At last. Clear, fun, and invigorating. Christopher knew Jonah's screenplay well. They are brothers, after all, and had talked as Jonah wrote. They have a phenomenally successful history of collaborating on screenplays. The Prestige, The Dark Knight, The Dark Knight Rises. Jonah writes the initial drafts, and then Christopher takes over and rewrites, thinking carefully about how he will film each scene as he crafts it on paper. With Interstellar now fully in Christopher's own hands, he combined Jonah's script with the script from another project he'd been working on, and he injected a radically fresh perspective and a set of major new ideas that would take the movie in unexpected new directions. In mid-January, Chris, as I soon came to call him, asked to meet me one-on-one in his office at Syncope, his movie production company on the Warner Brothers lot. As we talked, it became clear that Chris knew a remarkable amount of relevant science and had deep intuition about it. His intuition was occasionally off the mark, but usually right on, and he was tremendously curious. Our conversations often diverged from Interstellar to some irrelevant science issue that fascinated him. In that first meeting, I laid on Chris my proposed science guidelines. Nothing will violate firmly established laws of physics. Speculations will all spring from science. He seemed positively inclined, but told me that if I didn't like what he did with the science, I didn't have to defend him in public. That shook me up a bit. But with the movie now in post-production, I'm impressed how well he followed those guidelines, while making sure they didn't get in the way of making a great movie. Chris worked intensely from mid-January to early May, rewriting Jonah's screenplay. From time to time, he or his assistant, Andy Thompson, would phone me and ask that I come to his office or his home to talk about science issues, or come to read a new draft of his screenplay and then meet to discuss it. Our discussions were long, typically 90 minutes, sometimes followed by long phone calls a day or two later. He raised issues that made me think. As when working with Jonah, my best thinking was in the dead of night. The next morning I would write up my thoughts in a several-paged memo with diagrams and pictures and hand-carry them to Chris. Chris worried about our ideas leaking out and spoiling his fans' mounting anticipation. He is one of the most secretive filmmakers in Hollywood. Chris's ideas occasionally seemed to violate my guidelines, but amazingly, I almost always found a way to make them work, scientifically. Only once did I fail miserably. In response, after several discussions over a 2-week period, Chris backed off and took that bit of the film in another direction. So in the end, I have no qualms about defending what Chris did with the science. On the contrary, I'm enthusiastic. He turned into reality Linda's and my dream of a blockbuster movie with foundations of real science, and with real science woven throughout its fabric. In the hands of Jonah and Chris, Interstellar's story changed enormously. It resembles Linda's and my treatment only in broadest brushstrokes. It is so much better. And as for the science ideas, they are not all mine by any means. Chris brought remarkable science ideas of his own to the film, ideas that my physicist colleagues will assume were mine, ideas that I said to myself when I saw them, why didn't I think of that? And remarkable ideas arose from my discussions with Chris, with Jonah, and with Linda. One April evening, Carolee and I threw a big party for Stephen Hawking at our home in Pasadena, with a diverse crowd of 100 people. Scientists, artists, writers, photographers, filmmakers, historians, school teachers, community organizers, labor organizers, business entrepreneurs, architects, and more. Chris and Emma came, as well as Jonah Nolan and his wife, Lisa Joy, and of course, Linda. In the late evening, we stood together for a long time on a balcony, under the stars, far from the party noise, talking quietly. My first opportunity to get to know Chris as a man, rather than a filmmaker. It was so enjoyable. Chris is down to earth, fascinating to talk with, and has a great sense of wry humor. He reminds me of another friend of mine, Gordon Moore, the founder of Intel. Both at the pinnacle of their fields, completely unpretentious. Both driving old cars, preferring them to their other, more luxurious cars. Both making me feel comfortable, and, introvert that I am, that's not easy. Paul Franklin, Oliver James, Eugenie von Tunzelmann. The visual effects team. One day in mid-May 2013, Chris phoned me. He wanted to send a guy named Paul Franklin over to my home to discuss the computer graphics for Interstellar. Paul came the next day, and we spent a delightful 2 hours brainstorming in my home office. He was modest in demeanor, by contrast with Chris's forcefulness. He was brilliant. He showed a deep knowledge of the relevant science, despite having majored in the arts in college. As Paul was leaving, I asked him which graphics company he was thinking of using for the visual effects. Mine, he responded mildly. And what company is that? I asked, naively. Double Negative. We have 1,000 employees in London and 200 in Singapore. After Paul departed, I Googled him and discovered that not only had he co-founded Double Negative, he had also won an Academy Award for the visual effects in Chris's movie Inception. It's time I get educated about this movie business, I murmured to myself. In a video conference a few weeks later, Paul introduced me to the London-based leaders of his Interstellar visual effects team. Most relevant to me were Oliver James, the chief scientist who would write computer code underlying the visual effects, and Eugenie von Tunzelmann, who led the artistic team that would take Oliver's computer code and add extensive artistic twists to produce compelling images for the movie. Oliver and Eugenie were the first people with physics training that I had met on Interstellar. Oliver has a degree in optics and atomic physics and knows the technical details of Einstein's special relativity. Eugenie is an engineer, trained at Oxford, with a focus on data engineering and computer science. They speak my language. We quickly developed a great working relationship. For several months I struggled near full-time, formulating equations for images of the universe near black holes and wormholes. I tested my equations using low-resolution, user-friendly computer software called Mathematica, and then sent the equations and Mathematica code to Oliver. He devoured them, converted them into sophisticated computer code that could generate the ultra-high-quality IMAX images needed for Interstellar, and then passed them on to Eugenie and her team. It was a joy working with them. And the end product, the visualizations in Interstellar, are amazing and scientifically accurate. You cannot imagine how ecstatic I was when Oliver sent me his initial film clips. For the first time ever, and before any other scientist, I saw in ultra-high definition what a fast-spinning black hole looks like, what it does, visually, to its environment. Matthew McConaughey, Anne Hathaway, Michael Caine, Jessica Chastain. On July 18th, 2 weeks before filming was to begin, I received an email from Matthew McConaughey, who plays Cooper. Per Interstellar, he wrote, I'd like to ask you some questions, and if you are around LA area, in person is preferable. Let me know, please. Thanks. In process, McConaughey. We met 6 days later in a suite at L'Hermitage, a boutique hotel in Beverly Hills. He was ensconced there, struggling to wrap his head around the role of Cooper and the Science of Interstellar. When I arrived, he opened the door dressed in shorts and a tank top, barefooted and thin from having just filmed Dallas Buyers Club, for which he later won the Oscar for Best Actor. He asked if he could call me Kip. I said of course, and asked what I should call him. Anything but Matt. I hate Matt. Matthew, McConaughey, hey you, whatever you like. I chose McConaughey as it trips off the tongue so nicely, and there are too many Matthews in my life. McConaughey had removed all the furniture from the suite's huge living/dining room, except an L-shaped couch and a coffee table. Strewn over the floor and table were 12 by 18-inch sheets of paper, each covered with notes dealing with a particular topic, written in random directions, skiwampus. We sat on the couch. He would pick up a sheet, browse it, and ask a question. The question was usually deep and triggered a long discussion during which he would write notes on the sheet. Often the discussion would take off in unexpected directions, with the sheet forgotten. It was one of the most interesting and enjoyable conversations I've had in a long time. We wandered from the laws of physics, especially quantum physics, to religion and mysticism, to the science of interstellar, to our families and especially our children, to our philosophies of life, to how we each get inspirations, how our minds work, how we make discoveries. I left, 2 hours later, in a state of euphoria. Later, I told Linda about our meeting. Of course, she responded. She could have told me what to expect. Interstellar is her third film with McConaughey. I'm glad she didn't tell me. It was a joy to discover for myself. The next email, a few weeks later, was from Anne Hathaway, who plays Amelia Brand. Hi, Kip. I hope this email finds you well. Emma Thomas passed along your email in case I had any questions. Well, the subject matter is pretty dense, so I have a few. Would we be able to chat? Thank you very much, Annie. We talked by phone, as our schedules couldn't be meshed for an in-person meeting. She described herself as a bit of a physics geek and said that her character, Brand, is expected to know the physics cold, and then she launched into a series of surprisingly technical physics questions. What is the relationship of time to gravity? Why do we think there might be higher dimensions? What is the current status of research on quantum gravity? Are there any experimental tests of quantum gravity? Only at the end did she let us wander off subject, to music, in fact. She played trumpet in high school. I played sax and clarinet. During the filming of Interstellar, I was on set very, very little. I was not needed. But one morning, Emma Thomas toured me through the Endurance set, a full-scale mock-up of the Endurance spacecraft's command and navigation pod, in Stage 30 at Sony Studios. It was tremendously impressive. 44 feet long, 26 feet wide, 16 feet high, suspended in mid-air, able to shift from horizontal to nearly vertical, exquisite in detail. It blew me away and piqued my curiosity. Emma, why build these enormous, complex sets when the same thing could be done with computer graphics? It's not clear which would be cheaper, she responded, and computer graphics can't yet produce the compelling visual details of a real set. Wherever possible, she and Chris use real sets and real practical effects, except for things that can't actually be shot that way, like the black hole Gargantua. On another occasion, I wrote dozens of equations and diagrams on Professor Brand's blackboards, and watched as Chris filmed in the professor's office with Michael Caine as the professor and Jessica Chastain as Murph. I was astonished by the warm and friendly deference that Caine and Chastain showed me. Despite having no role in the filming, I was notorious as Interstellar's real scientist, the guy who inspired everyone's best effort to get the science right for this blockbuster movie. That notoriety triggered fascinating conversations with Hollywood icons, not just the Nolans, McConaughey, and Hathaway, but also Caine, Chastain, and others. A fun bonus from my creative friendship with Linda. Now comes the final phase of Linda's and my interstellar dream. The phase where you, the audience, have become curious about Interstellar's science and seek explanations for bizarre things you saw in the movie. The answers are here. That's why I wrote this book. Enjoy. 1. Foundations. 2. Our universe in brief. Our universe is vast, achingly beautiful, remarkably simple in some ways, intricately complex in others. From our universe's great richness, we'll need only a few basic facts that I'll now lay bare. The Big Bang. Our universe was born in a gigantic explosion 13.7 billion years ago. The explosion was given the irreverent name the Big Bang by my friend Fred Hoyle, a cosmologist who at that time, the 1940s, thought it an outrageous fictional idea. Fred was proved wrong. We've since seen radiation from the explosion, even in just the last week, as I write this, tentative evidence for radiation emitted in the first trillionth of a trillionth of a trillionth of a second after the explosion began. We don't know what triggered the Big Bang, nor what, if anything, existed before it. But somehow the universe emerged as a vast sea of ultra-hot gas, expanding fast in all directions like the fireball ignited by a nuclear bomb blast or by the explosion of a gas pipeline. Except that the Big Bang was not destructive, so far as we know. Instead, it created everything in our universe, or rather the seeds for everything. I would love to write a long chapter about the Big Bang, but with great force of will I restrain myself. We don't need it for the rest of this book. Galaxies. As our universe expanded, its hot gas cooled. In some regions, the gas's density was a bit higher than in others, randomly. When the gas got cold enough, gravity pulled each high-density region inward on itself, giving birth to a galaxy, a huge cluster of stars and their planets and diffuse gas between the stars. The earliest galaxy was born when the universe was a few 100 million years old. There are roughly 1 trillion galaxies in the visible universe. The largest galaxies contain a few trillion stars and are about 1 million light-years across. The smallest, about 10 million stars and 1,000 light-years across. At the center of most every large galaxy there is a huge black hole, one that weighs 1 million times the sun's weight or more. The Earth resides in a galaxy called the Milky Way. Most of the Milky Way stars are in the bright band of light that stretches across Earth's sky on a clear, dark night. And almost all the pinpricks of light that we see in the sky at night, not just those in the bright band, also lie in the Milky Way. The nearest large galaxy to our own is called Andromeda, Figure 1 in your PDF companion. It is 2.5 million light-years from Earth. It contains about 1 trillion stars and is about 100,000 light-years across. The Milky Way is a sort of twin to Andromeda, about the same in size, shape, and number of stars. If Figure 1 were the Milky Way, then the Earth would be where I placed the yellow diamond. Andromeda contains a gigantic black hole, 100 million times heavier than the Sun and as big across as the Earth's orbit, the same weight and size as Interstellar's Gargantua. It resides in the middle of the central bright sphere in Figure 1. Solar System. Stars are large, hot balls of gas, usually kept hot by burning nuclear fuel in their cores. The Sun is a fairly typical star. It is 1.4 million kilometers across, about 100 times larger than the Earth. Its surface has flares and hot spots and cooler spots, and is fascinating to explore through a telescope. 8 planets, including the Earth, travel around the Sun in elliptical orbits, along with many dwarf planets, of which Pluto is the most famous, and many comets and smaller, rocky bodies called asteroids and meteoroids. Earth is the 3rd planet from the Sun. Saturn, with its gorgeous rings, is the 6th planet out and plays a role in Interstellar. The solar system is 1,000 times bigger than the Sun itself. Light needs 11 hours to travel across it. The distance to the nearest star other than the Sun, Proxima Centauri, is 4.24 light-years, 2,500 times farther than the distance across the solar system. In Chapter 13, I discuss the awful implications for interstellar travel. Stellar death, white dwarfs, neutron stars, and black holes. The Sun and Earth are about 4.5 billion years old, about a third the age of the universe. After another 6.5 billion years or so, the Sun will exhaust the nuclear fuel in its core, the fuel that keeps it hot. The Sun will then shift to burning fuel in a shell around its core, and its surface will expand to engulf and fry the Earth. With the shell's fuel spent and the Earth fried, the Sun will shrink to become a white dwarf star, about the size of the Earth, but with density 1,000,000 times higher. The white dwarf will gradually cool over tens of billions of years to become a dense, dark cinder. Stars much heavier than the Sun burn their fuel much more quickly, and then collapse to form a neutron star or a black hole. Neutron stars have masses about 1 to 3 times that of the Sun, circumferences of 75 to 100 kilometers, about the size of Chicago, and densities the same as the nucleus of an atom, 100 trillion times more dense than rock and the Earth. Indeed, neutron stars are made of almost pure nuclear matter, atomic nuclei packed side by side. Black holes, by contrast, are made fully and solely from warped space and warped time. I'll explain this weird claim in Chapter 4. They contain no matter whatsoever, but they have surfaces called event horizons or just horizons, through which nothing can escape, not even light. That's why they are black. A black hole's circumference is proportional to its mass. The heavier it is, the bigger it is. A black hole with about the same mass as a typical neutron star or white dwarf, say 1.2 times as heavy as the Sun, has a circumference of about 22 kilometers, a fourth that of the neutron star and 1,000th that of the white dwarf. Since stars are generally no heavier than about 100 suns, the black holes to which they give birth are also no heavier than 100 suns. The giant black holes in the cores of galaxies, 1,000,000 to 20 billion times heavier than the Sun, therefore, cannot have been born in the death of a star. They must have formed in some other way, perhaps by the agglomeration of many smaller black holes, perhaps by the collapse of massive clouds of gas. Magnetic, electric, and gravitational fields. Because magnetic force lines play a big role in our universe and are important for Interstellar, let's discuss them too, before diving into Interstellar's science. As a student in science class, you may have met magnetic force lines in a beautiful little experiment. Do you remember taking a sheet of paper, placing a bar magnet under it, and sprinkling iron filings, elongated flakes of iron, on top of the paper? The iron filings make the pattern shown in Figure 2 in your PDF companion. They orient themselves along magnetic force lines that otherwise are invisible. The force lines depart from one of the magnet's poles, swing around the magnet, and descend into the other pole. The magnetic field is the collection of all the magnetic force lines. When you try to push two magnets together with their north poles facing each other, their force lines repel each other. You see nothing between the magnets, but you feel the magnetic field's repulsive force. This can be used for magnetic levitation, suspending a magnetized object, even a railroad train, in midair. The Earth also has two magnetic poles, north and south. Magnetic force lines depart from the south magnetic pole, swing around the Earth, and descend into the north magnetic pole. These force lines grab a compass needle, just as they grab iron filings, and drive the needle to point as nearly along the force lines as possible. That's how a compass works. The Earth's magnetic force lines are made visible by the aurora borealis, the northern lights. Protons, flying outward from the sun, are caught by the force lines and travel along them into the Earth's atmosphere. There, the protons collide with oxygen and nitrogen molecules, making the oxygen and nitrogen fluoresce. That fluorescent light is the aurora. Neutron stars have very strong magnetic fields, whose force lines are donut-shaped, like the Earth's. Fast-moving particles trapped in a neutron star's magnetic field light up the force lines, producing the blue rings in Figure 3 in your PDF companion. Some of the particles are liberated and stream out the field's poles, producing the two violet jets in the figure. These jets consist of all types of radiation: gamma rays, X-rays, ultraviolet, visual, infrared, and radio waves. As the star spins, its luminous jets sweep around the sky above the neutron star, like a searchlight. Every time a jet sweeps over the Earth, astronomers see a pulse of radiation. So astronomers have named these objects pulsars. The universe contains other kinds of fields, collections of force lines, in addition to magnetic fields. One example is electric fields, collections of electric force lines that, for example, drive electric current to flow through wires. Another example is gravitational fields, collections of gravitational force lines that, for example, pull us to the Earth's surface. The Earth's gravitational force lines point radially into the Earth, and they pull objects toward the Earth along themselves. The strength of the gravitational pull is proportional to the density of the force lines, the number of lines passing through a fixed area. As they reach inward, the force lines pass through spheres of ever-decreasing area, so the line's density must go up inversely with the sphere's area, which means the Earth's gravity grows as you travel toward it, as 1 divided by the red sphere's area. Since each sphere's area is proportional to the square of its distance r from the Earth's center, the strength of the Earth's gravitational pull grows as 1 divided by r squared. This is Newton's inverse square law for gravity, an example of the fundamental laws of physics that are Professor Brand's passion in Interstellar and our next foundation for Interstellar's science. 3. The laws that control the universe. Mapping the world and deciphering the laws of physics. Physicists have struggled from the 17th century onward to discover the physical laws that shape and control our universe. This has been like European explorers struggling to discover the Earth's geography. By 1506, Eurasia was coming into focus, and there were glimmers of South America. By 1570, the Americas were coming into focus, but there was no sign of Australia. By 1744, Australia was coming into focus, but Antarctica was terra incognita. Similarly, by 1690, the Newtonian laws of physics had come into focus. With concepts such as force, mass, and acceleration, and equations that link them, such as F equals ma, the Newtonian laws accurately describe the motion of the moon around the Earth and the Earth around the sun, the flight of an airplane, the construction of a bridge, and collisions of a child's marbles. In Chapter 2, we briefly met an example of a Newtonian law, the inverse square law for gravity. By 1915, Einstein and others had found strong evidence that the Newtonian laws fail in the realm of the very fast, objects that move at nearly the speed of light, the realm of the very large, our universe as a whole, and the realm of intense gravity, for example, black holes. To remedy these failures, Einstein gave us his revolutionary relativistic laws of physics. Using the concepts of warped time and warped space, the relativistic laws predicted and explained the expansion of the universe, black holes, neutron stars, and wormholes. By 1924, it was crystal clear that the Newtonian laws also fail in the realm of the very small: molecules, atoms, and fundamental particles. To deal with this, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, and others, gave us the quantum laws of physics. Using the concepts that everything fluctuates randomly at least a little bit, and that these fluctuations can produce new particles and radiation where before there were none, the quantum laws have brought us lasers, nuclear energy, light-emitting diodes, and a deep understanding of chemistry. By 1957, it became evident that the relativistic laws and the quantum laws are fundamentally incompatible. They predict different things, incompatible things, in realms where gravity is intense and quantum fluctuations are strong. These realms include the Big Bang birth of our universe, the cores of black holes like Gargantua, and backward time travel. In these realms, a fiery marriage of the incompatible relativistic and quantum laws gives rise to new laws of quantum gravity. We do not yet know the laws of quantum gravity, but we have some compelling insights, including superstring theory, thanks to enormous effort by the world's greatest 21st century physicists. Despite those insights, quantum gravity remains terra almost incognita, an almost unknown land. This leaves much elbow room for exciting science fiction, elbow room that Christopher Nolan exploits with great finesse in Interstellar. Truth, educated guesses, and speculations. The science of Interstellar lies in all four domains: Newtonian, relativistic, quantum, and quantum gravity. Correspondingly, some of the science is known to be true, some is an educated guess, and some is speculation. To be true, the science must be based on well-established physical laws, Newtonian, relativistic, or quantum, and it must have enough basis in observation that we are confident of how to apply the well-established laws. In precisely this sense, neutron stars and their magnetic fields, as described in Chapter 2, are true. Why? First, neutron stars are firmly predicted to exist by the quantum and relativistic laws. Second, astronomers have studied in enormous detail the pulsar radiation from neutron stars, pulses of light, X-rays, and radio waves described in Chapter 2. These pulsar observations are beautifully and accurately explained by the quantum and relativistic laws, if the pulsar is a spinning neutron star, and no other explanation has ever been found. Third, neutron stars are firmly predicted to form in astronomical explosions called supernovae, and pulsars are seen at the centers of big expanding gas clouds, the remnants of old supernovae. Thus, we astrophysicists have no doubt neutron stars really do exist, and they really do produce the observed pulsar radiation. Another example of a truth is the black hole Gargantua and the bending of light rays by which it distorts images of stars. Physicists call this distortion gravitational lensing because it is similar to the distortion of a picture by a curved lens or mirror, as in an amusement park's funhouse, for example. Einstein's relativistic laws predict, unequivocally, all the properties of black holes from their surfaces outward, including their gravitational lensing. Astronomers have firm observational evidence that black holes exist in our universe, including gigantic black holes like Gargantua. Astronomers have seen gravitational lensing by other objects, though not yet by black holes, and the observed lensing is in precise accord with the predictions of Einstein's relativistic laws. This is enough for me. Gargantua's gravitational lensing, as simulated by Paul Franklin's double negative team using relativity equations I gave to them, is true. This is what it really would look like. By contrast, the blight that endangers human life on Earth in Interstellar is an educated guess in one sense and a speculation in another. Let me explain. Throughout recorded history, the crops that humans grow have been plagued by occasional blights, rapidly spreading diseases caused by microbes. The biology that underlies these blights is based on chemistry, which in turn is based on the quantum laws. Scientists do not yet know how to deduce from the quantum laws all of the relevant chemistry, but they can deduce much of it. And they do not yet know how to deduce from chemistry all of the relevant biology. Nevertheless, from observations and experiments, biologists have learned much about blights. The blights encountered by humans thus far have not jumped from infecting one type of plant to another with such speed as to endanger human life. But nothing we know guarantees this can't happen. That such a blight is possible is an educated guess. That it might someday occur is a speculation that most biologists regard as very unlikely. The gravitational anomalies that occur in Interstellar, for example, the coin Cooper tosses that suddenly plunges to the floor, are speculations. So is harnessing the anomalies to lift colonies off Earth. Although experimental physicists, when measuring gravity, have searched hard for anomalies, behaviors that cannot be explained by the Newtonian or relativistic laws, no convincing gravitational anomalies have ever been seen on Earth. However, it seems likely from the quest to understand quantum gravity that our universe is a membrane, physicists call it a brain, residing in a higher dimensional hyperspace, to which physicists give the name bulk. When physicists carry Einstein's relativistic laws into this bulk, as Professor Brand does on the blackboard in his office, they discover the possibility of gravitational anomalies, anomalies triggered by physical fields that reside in the bulk. We are far from sure that the bulk really exists, and it is only an educated guess that, if the bulk does exist, Einstein's laws reign there. And we have no idea whether the bulk, if it exists, contains fields that can generate gravitational anomalies, and if so, whether those anomalies can be harnessed. The anomalies and their harnessing are a rather extreme speculation, but they are a speculation based on science that I and some of my physicist friends are happy to entertain, at least late at night over beer. So they fall within the guidelines I advocated for Interstellar. Speculations will spring from real science, from ideas that at least some respectable scientists regard as possible. Throughout this book, when discussing the science of Interstellar, I explain the status of that science, truth, educated guess, or speculation, and I label it so at the beginning of a chapter or section. Of course, the status of an idea, truth, educated guess, or speculation, can change, and you'll meet such changes occasionally in the movie and in this book. For Cooper, the bulk is an educated guess that becomes a truth when he goes there in the Tesseract, and the laws of quantum gravity are a speculation until TARS extracts them from inside a black hole, so for Cooper and Murph, they become truth. For 19th century physicists, Newton's inverse square law for gravity was an absolute truth. But around 1890, it was revolutionarily upended by a tiny observed anomaly in the orbit of Mercury around the Sun. Newton's law is very nearly correct in our solar system, but not quite. This anomaly helped pave the way for Einstein's 20th century relativistic laws, which, in the realm of strong gravity, began as speculation, became an educated guess when observational data started rolling in, and by 1980, with ever-improving observations, evolved into truth. Revolutions that upend established scientific truth are exceedingly rare, but when they happen, they can have profound effects on science and technology. Can you identify in your own life speculations that became educated guesses and then truth? Have you ever seen your established truths upended with a resulting revolution in your life? 4. Warped time and space and tidal gravity. Status of science, truth. Einstein's law of time warps. Einstein struggled to understand gravity on and off from 1907 onward. Finally, in 1912, he had a brilliant inspiration. Time, he realized, must be warped by the masses of heavy bodies, such as the Earth or a black hole, and that warping is responsible for gravity. He embodied this insight in what I like to call Einstein's law of time warps, a precise mathematical formula that I describe qualitatively this way. Everything likes to live where it will age the most slowly, and gravity pulls it there. The greater the slowing of time, the stronger gravity's pull. On Earth, where time is slowed by only a few microseconds per day, gravity's pull is modest. On the surface of a neutron star, where time is slowed by a few hours per day, gravity's pull is enormous. At the surface of a black hole, time is slowed to a halt, whence gravity's pull is so humongous that nothing can escape, not even light. This slowing of time near a black hole plays a major role in Interstellar. Cooper despairs of ever seeing his daughter Murph again, when his travel near Gargantua causes him to age only a few hours, while Murph, on Earth, is aging 8 decades. Human technology was too puny to test Einstein's law until nearly half a century after he formulated it. The first good test came in 1959 when Bob Pound and Glenn Rebka used a new technique called the Mossbauer effect to compare the rate of flow of time in the basement of a 73-foot tower at Harvard University with time in the tower's penthouse. Their experiment was exquisitely accurate, good enough to detect differences of 0.000000000016 seconds, 1.6 trillionths of a second, in one day. Remarkably, they found a difference 130 times larger than this accuracy, and in excellent agreement with Einstein's law. Time flows more slowly in the basement than in the penthouse by 210 trillionths of a second each day. The accuracy improved in 1976 when Robert Visseau of Harvard flew an atomic clock on a NASA rocket to a 10,000-kilometer height and used radio signals to compare its ticking rate with clocks on the ground. Visseau found that time on the ground flows more slowly than at a height of 10,000 kilometers by about 30 microseconds, 0.00003 seconds, in one day. And his measurement agreed with Einstein's law of time warps to within his experimental accuracy. That accuracy, the uncertainty in Visseau's measurement, was 7 parts in 100,000, 0.00007 of 30 microseconds in a day. The Global Positioning System, GPS, by which our smartphones can tell us where we are to 10 meters accuracy, relies on radio signals from a set of 27 satellites at a height of 20,000 kilometers. Typically, only 4 to 12 satellites can be seen at once from any location on Earth. Each radio signal from a viewable satellite tells the smartphone where the satellite is located and the time the signal was transmitted. The smartphone measures the signal's arrival time and compares it with its transmission time to learn how far the signal traveled, the distance between satellite and phone. Knowing the locations and distances to several satellites, the smartphone can triangulate to learn its own location. This scheme would fail if the signal transmission times were the true times measured on the satellite. Time at a 20,000-kilometer height flows more rapidly than on Earth by 40 microseconds each day, and the satellites must correct for this. They measure time with their own clocks, then slow that time down to the rate of time flow on Earth before transmitting it to our phones. Einstein was a genius, perhaps the greatest scientist ever. This is one of many examples where his insights about the laws of physics could not be tested in his own day. It required a half-century for technology to improve enough for a test with high precision, and another half-century until the phenomena he described became part of everyday life. Among other examples are the laser, nuclear energy, and quantum cryptography. The warping of space, the bulk and our brain. In 1912, Einstein realized that if time can be warped by massive bodies, then space must also be warped. But despite the most intense mental struggle of his life, the full details of space warps long eluded him. From 1912 to late 1915, he struggled. Finally, in November 1915, in a great eureka moment, he formulated his field equation of general relativity, which encapsulated all his relativistic laws, including space warps. Again, human technology was too puny for high-precision tests. This time, the needed improvements took 60 years, culminating in several key experiments. The one I liked best was led by Robert Riesenberg and Erwin Shapiro of Harvard. In 1976 to 77, they transmitted radio signals to two spacecraft in orbit around Mars. The spacecraft, called Viking 1 and Viking 2, amplified the signals and sent them back to Earth, where their round-trip travel time was measured. As the Earth and Mars moved around the Sun in their orbits, the radio signals traversed paths that were changing. At first, the paths were far from the Sun, then they passed near the Sun, and then far again, as shown in the bottom half of Figure 4 in your PDF companion. If space were flat, the round-trip travel time would have changed gradually and steadily. It did not. When the radio waves passed near the Sun, their travel time was longer than expected, longer by hundreds of microseconds. The extra travel time is shown as a function of the spacecraft's location at the top of Figure 4. It went up and then back down. Now, one of Einstein's relativistic laws says that radio waves and light travel at an absolutely constant, unchanging speed. Therefore, the distance from Earth to the spacecraft had to be longer than expected when passing near the Sun, longer by hundreds of microseconds times the speed of light, about 50 kilometers. This greater length would be impossible if space were flat, like a sheet of paper. It is produced by the Sun's space warp. From the extra time delay and how it changed as the spacecraft moved relative to Earth, Riesenberg and Shapiro inferred the shape of the space warp. More precisely, they inferred the shape of the two-dimensional surface formed by the paths of the Viking radio signals. That surface was very nearly the Sun's equatorial plane, so I describe it that way here. The shape that the team measured for the Sun's equatorial plane is shown in Figure 5 in your PDF companion, with the magnitude of the warping exaggerated. The measured shape was precisely what Einstein's relativistic laws predict, precise to within the experimental error, which was 0.001 of the actual warping, that is, a part in 1,000. Around a neutron star, the space warp is far greater. Around a black hole, it is enormously greater. Now, the Sun's equatorial plane divides space into two identical halves, that above the plane and that below. Nonetheless, Figure 5 shows the equatorial plane as warped like the surface of a bowl. It bends downward inside and near the Sun, so that diameters of circles around the Sun, when multiplied by pi, 3.14159, etc., are larger than circumferences, larger in the case of the Sun by roughly 100 kilometers. That's not much, but it was easily measured by the spacecraft, with a precision of a part in 1,000. How can space bend down? Inside what does it bend? It bends inside a higher dimensional hyperspace called the bulk that is not part of our universe. Let's make that more precise. In Figure 5, the Sun's equatorial plane is a two-dimensional surface that bends downward in a three-dimensional bulk. This motivates the way we physicists think about our full universe. Our universe has three space dimensions: east-west, north-south, up-down. And we think of it as a three-dimensional membrane, or brain for short, that is warped in a higher dimensional bulk. How many dimensions does the bulk have? I discuss this carefully in Chapter 21, but for the purposes of Interstellar, the bulk has just one extra space dimension, 4 space dimensions in all. In Interstellar, the characters often refer to 5 dimensions. 3 are the space dimensions of our own universe or brain, east-west, north-south, up-down. The 4th is time, and the 5th is the bulk's extra space dimension. Does the bulk really exist? Is there truly a 5th dimension, and maybe even more, that humans have never experienced? Very likely yes. We'll explore this in Chapter 21. The warping of space, warping of our brain, plays a huge role in Interstellar. For example, it is crucial to the very existence of the wormhole connecting our solar system to the far reaches of the universe, where Gargantua lives. And it distorts the sky around the wormhole and around the black hole Gargantua. Figure 6 is an extreme example of space warps. It is a fanciful drawing by my artist friend Leah Halloran, depicting a hypothetical region of our universe that contains large numbers of wormholes and black holes extending outward from our brain into and through the bulk. The black holes terminate in sharp points called singularities. The wormholes connect one region of our brain to another. I suppress one of our brain's 3 dimensions, so the brain looks like a 2-dimensional surface. Tidal gravity. Einstein's relativistic laws dictate that planets, stars, and unpowered spacecraft near a black hole move along the straightest paths permitted by the hole's warped space and time. Figure 7 in your PDF companion shows examples of 4 such paths. The 2 purple paths headed into the black hole begin parallel to each other. As each path tries to remain straight, the 2 paths get driven toward each other. The warping of space and time drives them together. The green paths, traveling circumferentially around the hole, also begin parallel, but in this case, the warping drives them apart. Several years ago, my students and I discovered a new point of view about these planetary paths. In Einstein's relativity theory, there is a mathematical quantity called the Riemann tensor. It describes the details of the warping of space and time. We found, hidden in the mathematics of this Riemann tensor, lines of force that squeeze some planetary paths together and stretch others apart. Tendex lines, my student David Nichols dubbed them, from the Latin word tendere, meaning to stretch. Figure 8 shows several of these tendex lines around the black hole of Figure 7. The green paths begin, on their right ends, parallel to each other, and then the red tendex lines stretch them apart. I draw a woman lying on a red tendex line. It stretches her, too. She feels a stretching force between her head and her feet, exerted by the red tendex line. The purple paths begin, at their top ends, running parallel to each other. They are then squeezed together by the blue tendex lines, and the woman whose body lies along a blue tendex line is also squeezed. This stretching and squeezing is just a different way of thinking about the influence of the warping of space and time. From one viewpoint, the paths are stretched apart or squeezed together due to the planetary paths moving along the straightest routes possible in the warped space and time. From another viewpoint, it is the tendex lines that do the stretching and squeezing. Therefore, the tendex lines must, in some very deep way, represent the warping of space and time. And indeed they do, as the mathematics of the Riemann tensor taught us. Black holes are not the only objects that produce stretching and squeezing forces. Stars and planets and moons also produce them. In 1687, Isaac Newton discovered them in his own theory of gravity and used them to explain ocean tides. The moon's gravity pulls more strongly on the near face of the Earth than on the far face, Newton reasoned, and the direction of pull on the Earth's sides is slightly inward because it is toward the moon's center, a slightly different direction on the Earth's 2 sides. This is the usual viewpoint about the moon's gravity depicted in Figure 9 in your PDF companion. Now, the Earth does not feel the average of these gravitational pulls because it is falling freely along its orbit. This is like the Endurance's crew not feeling Gargantua's gravitational pull when they are in the Endurance, in its parking orbit above the black hole. They only feel centrifugal forces due to the Endurance's rotation. What the Earth does feel is the red-arrowed lunar pulls in the left half of Figure 9, with their average subtracted away. That is, it feels a stretch toward and away from the moon and a squeeze on its lateral sides, right half of Figure 9. This is qualitatively the same as around a black hole, Figure 8. These felt forces stretch the ocean away from the Earth's surface on the faces toward and away from the moon, producing high tides there. And the felt forces squeeze the oceans toward the Earth's surface on the Earth's lateral sides, producing low tides there. As the Earth turns on its axis, one full turn each 24 hours, we see 2 high tides and 2 low tides. This was Newton's explanation of ocean tides, aside from a slight complication. The sun's tidal gravity also contributes to the tides. Its stretch and squeeze get added to the moon's stretch and squeeze. Because of their role in ocean tides, these gravitational squeezing and stretching forces, the forces the Earth feels, are called tidal forces. To extremely high accuracy, these tidal forces, computed using Newton's laws of gravity, are the same as we compute using Einstein's relativistic laws. They must be the same, since the relativistic laws and the Newtonian laws always make the same predictions when gravity is weak and objects move at speeds much slower than light. In the relativistic description of the moon's tides, Figure 10 in the PDF companion to this audiobook, the tidal forces are produced by blue Tendex lines that squeeze the Earth's lateral sides and red Tendex lines that stretch toward and away from the moon. This is just like a black hole's Tendex lines, Figure 8 in your PDF companion. The moon's Tendex lines are visual embodiments of the moon's warping of space and time. It is remarkable that a warping so tiny can produce forces big enough to cause the ocean tides. On Miller's planet, the tidal forces are enormously larger and are key to the huge waves that Cooper and his crew encounter. We now have 3 points of view on tidal forces. Newton's viewpoint, Figure 9 in your PDF companion. The Earth does not feel the moon's full gravitational pull, but rather the full pull, which varies over the Earth, minus the average pull. The Tendex viewpoint, Figure 10 in your PDF companion. The moon's Tendex lines stretch and squeeze the Earth's oceans. Also, as seen in Figure 8 in your PDF companion, a black hole's Tendex lines stretch and squeeze the paths of planets and stars around the black hole. The straightest route viewpoint, Figure 7 in your PDF companion. The paths of stars and planets around a black hole are the straightest routes possible in the hole's warped space and time. Having 3 different viewpoints on the same phenomenon can be extremely valuable. Scientists and engineers spend most of their lives trying to solve puzzles. The puzzle may be how to design a spacecraft, or it may be figuring out how black holes behave. Whatever the puzzle may be, if one viewpoint doesn't yield progress, another viewpoint may. Peering at the puzzle first from one viewpoint and then from another can often trigger new ideas. This is what Professor Brand does in Interstellar when trying to understand and harness gravitational anomalies. This is what I've spent most of my adult life doing. 5. Black holes. Status of science: truth. The black hole Gargantua plays a major role in Interstellar. Let's look at the basic facts about black holes in this chapter and then focus on Gargantua in the next. First, a weird claim. Black holes are made from warped space and warped time. Nothing else. No matter whatsoever. Now some explanation. Ant on a trampoline. A black hole's warped space. Imagine you're an ant, and you live on a child's trampoline, a sheet of rubber stretched between tall poles. A heavy rock bends the rubber downward, as shown in Figure 11 in your PDF companion. You're a blind ant, so you can't see the poles or the rock or the bent rubber sheet. But you're a smart ant. The rubber sheet is your entire universe, and you suspect it's warped. To determine its shape, you walk around a circle in the upper region, measuring its circumference, and then walk through the center from one side of the circle to the other, measuring its diameter. If your universe were flat, then the circumference would be pi equals 3.14159, etc., times the diameter. But the circumference, you discover, is far smaller than the diameter. Your universe, you conclude, is highly warped. Space around a non-spinning black hole has the same warping as the trampoline. Take an equatorial slice through the black hole. This is a two-dimensional surface. As seen from the bulk, this surface is warped in the same manner as the trampoline. Figure 12, see your PDF companion, is the same as Figure 11, with the ant and poles removed and the rock replaced by a singularity at the black hole's center. The singularity is a tiny region where the surface forms a point and thus is infinitely warped, and where, it turns out, tidal gravitational forces are infinitely strong, so matter, as we know it, gets stretched and squeezed out of existence. In chapters 26, 28, and 29, we see that Gargantua's singularity is somewhat different from this one, and why. For the trampoline, the warping of space is produced by the rock's weight. Similarly, one might suspect the black hole's space warp is produced by the singularity at its center. Not so. In fact, the hole's space is warped by the enormous energy of its warping. Yes, that's what I meant to say. If this seems a bit circular to you, well, it is, but it has deep meaning. Just as it requires a lot of energy to bend a stiff bow in preparation for shooting an arrow, so it requires a lot of energy to bend space, to warp it. And just as the bending energy is stored in the bent bow until the string is released and feeds the bow's energy into the arrow, so the warping energy is stored in the black hole's warped space. And for a black hole, that energy of warping is so great that it generates the warping. Warping begets warping in a nonlinear, self-bootstrapping manner. This is a fundamental feature of Einstein's relativistic laws, and so different from everyday experience. It's somewhat like a hypothetical science fiction character who goes backward in time and gives birth to herself. This warping begets warping scenario does not happen in our solar system hardly at all. Throughout our solar system, the space warps are so weak that their energy is minuscule, far too small to produce much bootstrapped warping. Almost all the space warping in our solar system is produced directly by matter, the sun's matter, the Earth's matter, the matter of the other planets, by contrast with a black hole where the warping is fully responsible for the warping. Event horizon and warped time. When you first hear mention of a black hole, you probably think of its trapping power, as depicted in Figure 13 in your PDF companion, not its warped space. If I fall into a black hole carrying a microwave transmitter, then once I pass through the hole's event horizon, I'm pulled inexorably on downward into the hole's singularity. And any signals I try to transmit in any manner whatsoever get pulled down with me. Nobody above the horizon can ever see the signals I send after I cross the horizon. My signals and I are trapped inside the black hole. This trapping is actually caused by the hole's time warp. If I hover above the black hole, supporting myself by the blast of a rocket engine, then the closer I am to the horizon, the more slowly my time flows. At the horizon itself, time slows to a halt, and therefore, according to Einstein's law of time warps, I must experience an infinitely strong gravitational pull. What happens inside the event horizon? Time is so extremely warped there that it flows in a direction you would have thought was spatial. It flows downward toward the singularity. That downward flow, in fact, is why nothing can escape from a black hole. Everything is drawn inexorably toward the future, and since the future inside the hole is downward, away from the horizon, nothing can escape back upward through the horizon. Space whirl. Black holes can spin, just as the Earth spins. A spinning hole drags space around it into a vortex-type whirling motion. Like the air in a tornado, space whirls fastest near the hole's center, and the whirl slows as one moves outward, away from the hole. Anything that falls toward the hole's horizon gets dragged, by the whirl of space, into a whirling motion around and around the hole, like a straw caught and dragged by a tornado's wind. Near the horizon, there is no way whatsoever to protect oneself against this whirling drag. Precise depiction of the warped space and time around a black hole. These three aspects of space-time warping, the warp of space, the slowing and distortion of time, and the whirl of space, are all described by mathematical formulas. These formulas have been deduced from Einstein's relativistic laws, and their precise predictions are depicted quantitatively in Figure 14 in your PDF companion. The warped shape of the surface in Figure 14 is precisely what we would see from the bulk when looking at the hole's equatorial plane. The colors depict the slowing of time as measured by someone who hovers at a fixed height above the horizon. At the transition from blue to green, time flows 20% as fast as it flows far from the hole. At the transition from yellow to red, Time is slowed to 10% of its normal rate far away. And at the black circle, the bottom of the surface, time slows to a halt. This is the event horizon. It is a circle, not a sphere, because we are looking only at the equatorial plane, only at 2 dimensions of our universe, of our brain. If we were to restore the third space dimension, the horizon would become a flattened sphere, a spheroid. The white arrows depict the rate at which space whirls around the black hole. The whirl is fast at the horizon and decreases as we climb upward in a spacecraft. In the fully accurate Figure 14, I don't depict the hole's interior. We'll get to that later in chapters 26 and 28. The warping in Figure 14 is the essence of a black hole. From its details, expressed mathematically, physicists can deduce everything about the black hole, except the nature of the singularity at its center. For the singularity, they need the ill-understood laws of quantum gravity. A black hole's appearance from inside our universe. We humans are confined to our brain. We can't escape from it, into the bulk, unless an ultra-advanced civilization gives us a ride in a tesseract or some such vehicle, as they do for Cooper in Interstellar. Therefore, we can't see a black hole's warped space, as depicted in Figure 14. The black hole funnels and whirlpools so often shown in movies, for example, Disney Studios' 1979 movie, The Black Hole, would never be seen by any creature that lives in our universe. Interstellar is the first Hollywood movie to depict a black hole correctly, in the manner that humans would actually see and experience it. A black hole casts a black shadow on the field of stars behind it. Light rays from the stars are bent by the hole's warped space. They are gravitationally lensed, producing a concentric pattern of distortion. Light rays, coming to us from the shadow's left edge, move in the same direction as the hole's whirling space. The space whirl gives them a boost, letting them escape from closer to the horizon than light rays on the shadow's right edge, which struggle against the whirl of space. The shadow is flattened on the left and bulges out on the right. In Chapter 8, I talk more about this and other aspects of what a black hole really looks like, as seen up close in our universe, in our brain. How do we know this is true? Einstein's relativistic laws have been tested to high precision. I'm convinced they are right, except when they confront quantum physics. For a big black hole like Interstellar's Gargantua, quantum physics is relevant only near its center, in its singularity. So if black holes exist at all in our universe, they must have the properties that Einstein's relativistic laws dictate, the properties I described previously. These properties and others have been deduced from Einstein's equations by a large number of physicists standing intellectually on each other's shoulders. Most importantly, Karl Schwarzschild, Roy Kerr, and Stephen Hawking. In 1915, shortly before his tragic death on World War I's German-Russian front, Schwarzschild deduced the details of the warped spacetime around a non-spinning black hole. In physicists' jargon, those details are called the Schwarzschild metric. In 1963, Kerr, a New Zealand mathematician, did the same for a spinning black hole. He deduced the spinning hole's Kerr metric. And in the early 1970s, Stephen Hawking and others deduced a set of laws that black holes must obey when they swallow stars, collide and merge, and feel the tidal forces of other objects. Black holes surely do exist. Einstein's relativistic laws insist that when a massive star exhausts the nuclear fuel that keeps it hot, then the star must implode. In 1939, J. Robert Oppenheimer and his student Hartland Snyder used Einstein's laws to discover that if the implosion is precisely spherical, the imploding star must create a black hole around itself, and then create a singularity at the hole's center, and then get swallowed into the singularity. No matter is left behind, none whatsoever. The resulting black hole is made entirely from warped space and time. Over the decades, since 1939, physicists using Einstein's laws have shown that if the imploding star is deformed and spinning, it will also produce a black hole. Computer simulations reveal the full details. Astronomers have seen compelling evidence for many black holes in our universe. The most beautiful example is a massive black hole at the center of our Milky Way galaxy. Andrea Ghez of UCLA, with a small group of astronomers that she leads, has monitored the motions of stars around that black hole. See Figure 15 in your PDF companion. Along each orbit, the dots are the star's position at times separated by 1 year. I marked the black hole's location by a white 5-pointed symbol. From the star's observed motions, Ghez has deduced the strength of the hole's gravity. Its gravitational pull, at a fixed distance, is 4.1 million times greater than the sun's pull at that distance. This means the black hole's mass is 4.1 million times greater than the sun's. A massive black hole inhabits the core of nearly every big galaxy in our universe. Many of these are as heavy as Gargantua, 100 million suns, or even heavier. The heaviest yet measured is 17 billion times more massive than the Sun. It resides at the center of a galaxy whose name is NGC 1277, 250 million light-years from Earth, roughly a tenth of the way to the edge of the visible universe. Inside our own galaxy, there are roughly 100 million smaller black holes, holes that typically are between about 3 and 30 times as heavy as the Sun. We know this not because we've seen evidence for all these, but because astronomers have made a census of heavy stars that will become black holes when they exhaust their nuclear fuel. From that census, astronomers have inferred how many such stars have already exhausted their fuel and become black holes. So black holes are ubiquitous in our universe. Fortunately, there are none in our solar system. If there were, the hole's gravity would wreak havoc with the Earth's orbit. The Earth would be thrown close to the Sun where it boils, or far from the Sun where it freezes, or even out of the solar system, or into the black hole. We humans would survive for no more than a year or so. Astronomers estimate that the nearest black hole to Earth is roughly 300 light-years away, 100 times farther than the nearest star, other than the Sun, Proxima Centauri. Now armed with a basic understanding of the universe, fields, warped time and space, and especially black holes, we are ready, at last, to explore Interstellar's Gargantua. 2. Gargantua. 6. Gargantua's anatomy. If we know the mass of a black hole and how fast it spins, then from Einstein's relativistic laws we can deduce all the hole's other properties. Its size, the strength of its gravitational pull, how much its event horizon is stretched outward near the equator by centrifugal forces, the details of the gravitational lensing of objects behind it, everything. This is amazing. So different from everyday experience. It is as though knowing my weight and how fast I can run, you could deduce everything about me, the color of my eyes, the length of my nose, my IQ. John Wheeler, my mentor, who gave black holes their name, has described this by the phrase, "A black hole has no hair, no extra, independent properties beyond its mass and its spin." Actually, he should have said, "A black hole has only 2 hairs, from which you can deduce everything else about it." But that's not as catchy as no hair, which quickly became embedded in black hole lore and scientists' lexicon. From the properties of Miller's planet, as depicted in Interstellar, a physicist who knows Einstein's relativistic laws can deduce Gargantua's mass and spin, and thence all else about it. Let's see how this works. Gargantua's mass. Status of science, truth. Miller's planet is about as close to Gargantua as it can possibly be and still survive. We know this because the crew's extreme loss of time can only occur very near Gargantua. At so close a distance, Gargantua's tidal gravitational forces are especially strong. They stretch Miller's planet toward and away from Gargantua and squeeze the planet's sides. The strength of this stretch and squeeze is inversely proportional to the square of Gargantua's mass. Why? The greater Gargantua's mass, the greater its circumference, and therefore the more similar Gargantua's gravitational forces are on the various parts of the planet, which results in weaker tidal forces. Working through the details, I conclude that Gargantua's mass must be at least 100 million times bigger than the Sun's mass. If Gargantua were less massive than that, it would tear Miller's planet apart. In all my science interpretations of what happens in Interstellar, I assume that this actually is Gargantua's mass, 100 million suns. For example, I assumed this mass in Chapter 17, when explaining how Gargantua's tidal forces could produce the giant water waves that inundate the Ranger on Miller's planet. The circumference of a black hole's event horizon is proportional to the hole's mass. For Gargantua's 100 million solar masses, the horizon circumference works out to be approximately the same as the Earth's orbit around the Sun, about 1 billion kilometers. That's big. After consulting with me, that's the circumference assumed by Paul Franklin's visual effects team when producing the images in Interstellar. Physicists attribute to a black hole a radius equal to its horizon's circumference divided by 2 pi, about 6.28. Because of the extreme warping of space inside the black hole, this is not the hole's true radius, not the true distance from the horizon to the hole's center as measured in our universe. But it is the event horizon's radius, half its diameter, as measured in the bulk. Gargantua's radius, in this sense, is about 150 million kilometers, the same as the radius of the Earth's orbit around the Sun. Gargantua's spin. Status of science, speculation. When Christopher Nolan told me how much slowing of time he wanted on Miller's planet, 1 hour there is 7 years back on Earth, I was shocked. I didn't think that possible, and I told Chris so. It's non-negotiable, Chris insisted. So not for the first time, and also not the last, I went home, thought about it, did some calculations with Einstein's relativistic equations, and found a way. I discovered that if Miller's planet is about as near Gargantua as it can get without falling in, and if Gargantua is spinning fast enough, then Chris's 1 hour in 7 years time slowing is possible. But Gargantua has to spin awfully fast. There is a maximum spin rate that any black hole can have. If it spins faster than that maximum, its horizon disappears, leaving the singularity inside it wide open for all the universe to see, that is, making it naked, which is probably forbidden by the laws of physics. I found that Chris's huge slowing of time requires Gargantua to spin almost as fast as the maximum, less than the maximum by about 1 part in 100 trillion. In most of my science interpretations of Interstellar, I assume this spin. The crew of the Endurance could measure the spin rate directly by watching from far, far away as the robot TARS falls into Gargantua. As seen from afar, TARS never crosses the horizon, because signals he sends after crossing can't get out of the black hole. Instead, TARS's infall appears to slow down, and he appears to hover just above the horizon. And as he hovers, Gargantua's whirling space sweeps him around and around Gargantua, as seen from afar. With Gargantua's spin very near the maximum possible, TARS's orbital period is about 1 hour, as seen from afar. You can do the math yourself. The orbital distance around Gargantua is 1 billion kilometers, and TARS covers that distance in 1 hour. So his speed, as measured from afar, is about 1 billion kilometers per hour, which is approximately the speed of light. If Gargantua were spinning faster than the maximum, TARS would whip around faster than the speed of light, which violates Einstein's speed limit. This is a heuristic way to understand why there is a maximum possible spin for any black hole. In 1975, I discovered a mechanism by which nature protects black holes from spinning faster than the maximum. When it gets close to the maximum spin, a black hole has difficulty capturing objects that orbit in the same direction as the hole rotates, and that therefore, when captured, increase the hole's spin. But the hole easily captures things that orbit opposite to its spin, and that, when captured, slow the hole's spin. Therefore, the spin is easily slowed, when it gets close to the maximum. In my discovery, I focused on a disk of gas, somewhat like Saturn's rings, that orbits in the same direction as the hole's spin, an accretion disk. Friction in the disk makes the gas gradually spiral into the black hole, spinning it up. Friction also heats the gas, making it radiate photons. The whirl of space around the hole grabs those photons that travel in the same direction as the hole spins and flings them away, so they can't get into the hole. By contrast, the whirl grabs photons that are trying to travel opposite to the spin and sucks them into the hole, where they slow the spin. Ultimately, when the hole's spin reaches 0.998 of the maximum, an equilibrium is reached, with spin down by the captured photons precisely counteracting spin up by the accreting gas. This equilibrium appears to be somewhat robust. In most astrophysical environments, I expect black holes to spin no faster than about 0.998 of the maximum. However, I can imagine situations, very rare or never in the real universe, but possible nevertheless, where the spin gets much closer to the maximum, even as close as Chris requires to produce the slowing of time on Miller's planet, a spin 1 part in 100 trillion less than the maximum spin. Unlikely, but possible. This is common in movies. To make a great film, a superb filmmaker often pushes things to the extreme. In science fantasy films, such as Harry Potter, that extreme is far beyond the bounds of the scientifically possible. In science fiction, it's generally kept in the realm of the possible. That's the main distinction between science fantasy and science fiction. Interstellar is science fiction, not fantasy. Gargantua's ultra-fast spin is scientifically possible. Gargantua's anatomy. Status of science, truth. Having determined Gargantua's mass and spin, I used Einstein's equations to compute its anatomy. As in the previous chapter, here we focus solely on the external anatomy, leaving the interior, especially Gargantua's singularities, for chapters 26 and 28. In the top picture, in Figure 16 in your PDF companion, you see the shape of Gargantua's equatorial plane as viewed from the bulk. This is like Figure 14, also in your PDF companion, but because Gargantua's spin is much closer to the maximum possible, 1 part in 100 trillion contrasted with 2 parts in 1,000 in Figure 14, Gargantua's throat is far longer. It extends much farther downward before reaching the horizon. The region near the horizon, as seen from the bulk, looks like a long cylinder. The length of the cylindrical region is about 2 horizon circumferences, that is, 2 billion kilometers. The cylinder's cross-sections are circles in the diagram, but if we were to restore the third dimension of our brain by moving out of Gargantua's equatorial plane, the cross-sections would become flattened spheres, spheroids. On Gargantua's equatorial plane, shown in Figure 16, I marked several special locations that occur in my science interpretations of Interstellar. Gargantua's event horizon, black circle, the critical orbit from which Cooper and TARS fall into Gargantua near the end of the movie, green circle, the orbit of Miller's planet, blue circle, the orbit in which the Endurance is parked while the crew visit Miller's planet, yellow circle, and a segment of the non-equatorial orbit of man's planet, projected into the equatorial plane, purple circle. The outer part of man's orbit is so far away from Gargantua, 600 Gargantua radii or more, that I had to redraw the picture on a much larger scale to fit it in. Bottom picture in Figure 16. And even so, I didn't do it honestly. I only put the outer part at 100 Gargantua radii instead of 600 as I should. The red circles are labeled SOF for shell of fire. How did I come up with these locations? I use the parking orbit as an illustration here and discuss the others later. In the movie, Cooper describes the parking orbit this way. So we track a wider orbit of Gargantua, parallel with Miller's planet, but a little further out. And he wants it to be far enough from Gargantua to be out of the time shift, that is, far enough from Gargantua that the slowing of time compared to Earth is very modest. This motivated my choice of 5 Gargantua radii, yellow circle in Figure 16. The time for the Ranger to travel from this parking orbit to Miller's planet, 2.5 hours, reinforced my choice. But there was a problem with this choice. At this distance, Gargantua would look huge. It would subtend about 50 degrees on the Endurance's sky. Truly awe-inspiring, but undesirable for so early in the movie. So Chris and Paul chose to make Gargantua look much smaller at the parking orbit, about 2.5 degrees, which is 5 times the size of the Moon as seen from Earth. Still impressive, but not overwhelmingly so. The shell of fire. Status of science, truth. Gravity is so strong near Gargantua, and space and time are so warped that light, photons, can be trapped in orbits outside the horizon, traveling around and around the hole many times before escaping. These trapped orbits are unstable in the sense that the photons always escape from them eventually. By contrast, photons caught inside the horizon can never get out. I like to call this temporarily trapped light the shell of fire. This fire shell plays an important role in the computer simulations that underlie Gargantua's visual appearance in Interstellar. For a non-spinning black hole, the shell of fire is a sphere, one with circumference 1.5 times larger than the horizon's circumference. The trapped light travels around and around this sphere on great circles, like the lines of constant longitude on the Earth. And some of it leaks into the black hole, while the rest leaks outward, away from the hole. When a black hole is spun up, its shell of fire expands outward and inward, so it occupies a finite volume rather than just the surface of a sphere. For Gargantua, with its huge spin, the shell of fire in the equatorial plane extends from the bottom red circle of Figure 16 to the upper red circle. See your PDF companion. The shell of fire has expanded to encompass Miller's planet and the critical orbit, and much, much more. The bottom red circle is a light ray, a photon orbit, that moves around and around Gargantua in the same direction as Gargantua spins, the forward direction. The upper red circle is a photon orbit that moves in the opposite direction to Gargantua's spin, the backward direction. Evidently, the whirl of space enables the forward light to be much closer to the horizon without falling in than the backward light. What a huge effect the space whirl has. The region of space occupied by the shell of fire above and below the equatorial plane is depicted in Figure 17 in your PDF companion. It is a large, annular region. I omit the warping of space from this picture. It would get in the way of showing the shell of fire's full 3 dimensions. Figure 18 in your PDF companion shows some examples of photon orbits, light rays, trapped, temporarily, in the shell of fire. The black hole is at the center of each of these orbits. The leftmost orbit winds around and around the equatorial region of a small sphere, traveling always forward in the same direction as Gargantua's spin. It is nearly the same as the bottom, inner, red orbit in Figures 16 and 17 in your PDF companion. The next orbit in Figure 18 winds around a slightly larger sphere, in a nearly polar and slightly forward direction. The third orbit is larger still, but backward and nearly polar. The fourth is very nearly equatorial and backward, that is, nearly the upper, outer, red equatorial orbit of Figures 16 and 17. These orbits are actually inside each other. I pulled them apart so they are easier to see. Some photons that are temporarily trapped in the shell of fire escape outward. They spiral away from Gargantua. The rest escape spiraling inward. They spiral toward Gargantua and plunge through its horizon. The nearly trapped but escaping photons have a big impact on Gargantua's visual appearance in Interstellar. They mark the edge of Gargantua's shadow as seen by the Endurance's crew, and they produce a thin, bright line along the shadow's edge, a ring of fire. 7. Gravitational slingshots. Status of science, truth. Navigating a spacecraft near Gargantua is hard because the speeds are very high. To survive, a planet or star or spacecraft must counteract Gargantua's huge gravity with a comparably huge centrifugal force. This means it must move at very high speed. Near the speed of light, it turns out. In my science interpretation of Interstellar, the Endurance, parked at 10 Gargantua radii while the crew visit Miller's planet, moves at 1/3 the speed of light, c/3, where c represents the speed of light. Miller's planet moves at 55% the speed of light, 0.55 c. To reach Miller's planet from the parking orbit in my interpretation, the Ranger must slow its forward motion from c/3 to far less than that, so Gargantua's gravity can pull it downward. And when it reaches the vicinity of the planet, the Ranger must turn from downward to forward, and having picked up far too much speed while falling, it must slow by about c/4 to reach the planet's 0.55 c speed and rendezvous with it. What mechanism can Cooper, the Ranger's pilot, possibly use to produce these huge velocity changes? 21st century technology. The required changes of velocity, roughly c/3, are 100,000 kilometers per second. Per second, not per hour. By contrast, the most powerful rockets we humans have today can reach 15 kilometers per second, 7,000 times too slow. In Interstellar, the Endurance travels from Earth to Saturn in 2 years at an average speed of 20 kilometers per second, 5,000 times too slow. The fastest that human spacecraft are likely to achieve in the 21st century, I think, is 300 kilometers per second. That would require a major R&D effort on nuclear rockets, but it is still 300 times too slow for Interstellar's needs. Fortunately, nature provides a way to achieve the huge speed changes, c/3, required in Interstellar. Gravitational slingshots around black holes far smaller than Gargantua. Slingshot navigation to Miller's planet. Stars and small black holes congregate around gigantic black holes like Gargantua. In my science interpretation of the movie, I imagine that Cooper and his team make a survey of all the small black holes orbiting Gargantua. They identify one that is well positioned to gravitationally deflect the Ranger from its near circular orbit and send it plunging downward toward Miller's planet. This gravity-assisted maneuver is called a gravitational slingshot and has often been used by NASA in the solar system, though with the gravity coming from planets rather than a black hole. This slingshot maneuver is not seen or discussed in Interstellar, but the next one is mentioned by Cooper. "Look, I can swing around that neutron star to decelerate," he says. Deceleration is necessary because, having fallen under Gargantua's huge gravitational pull from the Endurance's orbit to Miller's orbit, the Ranger has acquired too much speed. It is moving c/4 faster than Miller's planet. The neutron star, traveling leftward relative to Miller's planet, deflects and slows the Ranger's motion so it can rendezvous gently with the planet. Now, there is a feature of these slingshots that could be very unpleasant, indeed deadly: tidal forces. To change velocities by as much as c/3 or c/4, the Ranger must come close enough to the small black hole and neutron star to feel their intense gravity. At those close distances, if the deflector is a neutron star or is a black hole with radius less than 10,000 kilometers, the humans and the Ranger will be torn apart by tidal forces. For the Ranger and humans to survive, the deflector must be a black hole at least 10,000 kilometers in size, about the size of the Earth. Now, black holes that size do occur in nature. They are called intermediate mass black holes, or IMBHs, and despite their big size, they are tiny compared to Gargantua, 10,000 times smaller. So Christopher Nolan should have used an Earth-sized IMBH to slow down the Ranger, not a neutron star. I discussed this with Chris early in his rewrites of Jonah's screenplay. After our discussion, Chris chose the neutron star. Why? because he didn't want to confuse his mass audience by having more than one black hole in the movie. One black hole, one wormhole, and also a neutron star, along with Interstellar's other rich science, all to be absorbed in a fast-paced 2-hour film. That was all Chris thought he could get away with. Recognizing that strong gravitational slingshots are needed to navigate near Gargantua, Chris included one slingshot in Cooper's dialogue at the price of using a scientifically implausible deflector, the neutron star instead of a black hole. Intermediate mass black holes in galactic nuclei. A 10,000-kilometer IMBH weighs about 10,000 solar masses. That's 10,000 times less than Gargantua, but 1,000 times heavier than typical black holes. These are the deflectors Cooper needs. Some IMBHs are thought to form in the cores of dense clusters of stars called globular clusters, and some of them are likely to find their way into the nuclei of galaxies, where gigantic black holes reside. An example is Andromeda, the nearest large galaxy to our own, in whose nucleus lurks a gargantua-sized black hole, 100 million solar masses. Huge numbers of stars are drawn into the vicinity of such gigantic black holes, as many as 1,000 stars per cubic light-year. When an IMBH passes through such a dense region, it gravitationally deflects the stars, creating a wake with enhanced density behind itself. The wake pulls on the IMBH gravitationally, slowing the IMBH down, a process called dynamical friction. As the IMBH very gradually slows, it sinks deeper into the vicinity of the gigantic black hole. In this manner, nature could provide Cooper, in my interpretation of Interstellar, with the IMBHs that he needs for his slingshots. Orbital navigation by ultra-advanced civilizations. A digression. The orbits of planets and comets in our solar system are all ellipses to very high accuracy. Newton's laws of gravity guarantee and enforce this. By contrast, around a gigantic spinning black hole such as Gargantua, where Einstein's relativistic laws hold sway, the orbits are far more complex. For an orbit, each trip around Gargantua would require a few hours to a few days, so the entire pattern would be swept out in about a year. After a few years, the orbit would pass near most any destination you might wish, though the speed at which you arrive might not be right. A slingshot might be needed to change speed and make a rendezvous. I'll let you imagine how an ultra-advanced civilization might use such complex orbits. In my science interpretations of the movie, for simplicity, I mostly eschew them and focus primarily on circular, equatorial orbits, those of the parked Endurance, Miller's Planet, and the critical orbit, and on simple trajectories for the Endurance as it travels from one circular equatorial orbit to another. An exception is the orbit of man's planet, discussed in Chapter 19. NASA's gravitational slingshots in the solar system. Let's return from the world of the possible, what the laws of physics allow, to hard-nosed, real-life gravitational slingshots in the comfy confines of our solar system, what humans have actually achieved as of 2014. You may be familiar with NASA's Cassini spacecraft. It was launched from Earth on October 15, 1997, with too little fuel to reach its destination, Saturn. The deficit was dealt with by slingshots. Around Venus on April 26, 1998, a second slingshot around Venus on July 24, 1999, around Earth on August 18, 1999, and around Jupiter on December 30, 2000. Arriving at Saturn on July 1, 2004, Cassini slowed down with the aid of a slingshot around Saturn's closest moon, Io. None of these slingshots looked like the ones I described previously. Instead of strongly deflecting the spacecraft's direction of motion, Venus, Earth, Jupiter, and Io deflected it only mildly. Why? The deflector's gravity was too weak to produce a strong deflection. For Venus, Earth, and Io, the deflection was inevitably small because their gravity is intrinsically weak. Jupiter has much stronger gravity, but a large deflection would have sent Cassini in the wrong direction. Reaching Saturn required a small deflection. Despite the small deflections, Cassini got substantial kicks from the flybys, big enough to compensate for inadequate fuel. In each flyby, except Io, Cassini traveled behind the deflecting planet but at an angle, so the planet's gravity optimally pulled Cassini forward, speeding it up. In Interstellar, the Endurance does a similar slingshot around Mars. Cassini has been exploring Saturn and Saturn's moons for the past 10 years, sending back amazing images and information, a treasure trove of beauty and science. For a glimpse, see http://www.nasa.gov/mission_pages/Cassini/main/. By contrast with these weak slingshots in the solar system, Gargantua's intense gravity can grab even objects moving at ultra-high speeds and throw them around on strongly bent slingshots, even a light ray. This produces gravitational lensing, the key to seeing Gargantua. 8. Imaging Gargantua. Status of science. Truth. Black holes emit no light, so the only way to see Gargantua is by its influence on light from other objects. In Interstellar, the other objects are an accretion disk and the galaxy in which it lives, including nebulae and a rich field of stars. For the sake of simplicity, let's include only the stars for now. Gargantua casts a black shadow on the field of stars, and it also deflects the light rays from each star, distorting the stellar pattern that the camera sees. This distortion is the gravitational lensing discussed in Chapter 3. Figure 19 in your PDF companion shows a rapidly spinning black hole, let's call it Gargantua, in front of a field of stars, as it would appear to you if you were in Gargantua's equatorial plane. Gargantua's shadow is the totally black region. Immediately outside the shadow's edge is a very thin ring of starlight called the Ring of Fire that I intensified by hand to make the edge of the shadow more distinct. Outside that ring, we see a dense sprinkling of stars with a pattern of concentric shells, a pattern produced by the gravitational lensing. As the camera orbits around Gargantua, the field of stars appears to move. This motion, combined with the lensing, produces dramatically changing patterns of light. The stars stream at high speed in some regions, they float gently in others, and they're frozen in still other regions. See the film clip on this book's page at interstellar.withgoogle.com. In this chapter, I explain all these features, beginning with the shadow and its ring of fire. Then I describe how the black hole images in Interstellar were actually produced. When imaging Gargantua in this chapter, I treat it as a fast-spinning black hole, as it must be to produce the extreme loss of time that the Endurance's crew experience relative to Earth. However, for fast spin, a mass audience could be confused by the flattening of the left edge of Gargantua's shadow, as seen in Figure 19, and by some peculiar features of the star streaming and the accretion disk. So Christopher Nolan and Paul Franklin chose a smaller spin, 60% of the maximum, for their Gargantua images in the movie. The shadow and its ring of fire. The shell of fire plays a key role in producing Gargantua's shadow and the thin ring of fire alongside it. The shell of fire is the purple region surrounding Gargantua in Figure 20 in your PDF companion, and it contains nearly trapped photon orbits, light rays, such as the one in the upper right inset, also in Figure 20. Suppose you are at the location of the yellow dot seen in Figure 20. The white light rays, A and B, and others like them, bring you the image of the ring of fire, and the black light rays, A and B, bring you the image of the shadow's edge. For example, the white ray A originates at some star far from Gargantua. It travels inward and gets trapped on the inner edge of the shell of fire in Gargantua's equatorial plane, where it flies round and round, driven by the whirl of space, and then escapes and comes to your eyes. The black ray, also labeled A, originates on Gargantua's event horizon. It travels outward and gets trapped on that same inner edge of the shell of fire, where it goes round and round, then escapes and reaches your eyes alongside the white ray A. The white ray brings you an image of a bit of the thin ring, the black ray an image of a bit of the shadow's edge. The shell of fire is responsible for merging the rays side by side and directing them toward your eyes. Similarly, for the white and black rays B, except they get trapped on the outer edge of the shell of fire going clockwise, struggling against the whirl of space, while rays A are trapped on the inner edge going counterclockwise and driven by the whirl of space. The flattening of the shadow's left edge in Figure 19 and rounding of its right edge are due to rays A, left edge, coming from the inner edge of the shell of fire, very close to the horizon, and rays B, right edge, from the outer edge of the shell of fire, much further out. Black rays C and D in Figure 20 begin on the horizon, travel outward and get trapped on non-equatorial orbits in the shell of fire, and then escape from their trapped orbits and come to your eyes, bringing images of bits of the shadow edge that lie outside the equatorial plane. The trapped orbit for ray D is shown in the upper right inset. White rays C and D, not shown, coming from distant stars, get trapped alongside black rays C and D, and then travel to your eyes alongside C and D, bringing images of bits of the ring of fire alongside bits of the shadow edge. Lensing by a non-spinning black hole. To understand the pattern of gravitationally lensed stars outside the shadow and their streaming as the camera moves, let's begin with a non-spinning black hole and with light rays that emerge from a single star. See Figure 21 in your PDF companion. Two light rays travel from the star to the camera. They each travel along the straightest line they can in the hole's warped space, but because of the warping, each ray gets bent. One bent ray travels to the camera around the hole's left side, the other around its right side. Each ray brings the camera its own image of the star. The two images, as seen by the camera, are shown in the inset of Figure 21. I put red circles around them to distinguish them from all the other stars the camera sees. Note that the right image is much closer to the hole's shadow than the left image. This is because its bent ray passed closer to the hole's event horizon. Each of the other stars appears twice in the picture, on opposite sides of the hole's shadow. Can you identify some of the pairs? The black hole's shadow in the picture consists of directions from which no rays can come to the camera. See the triangular-shaped region labeled shadow in the upper diagram. All the rays that want to be in the shadow got caught and swallowed by the black hole. As the camera moves rightward in its orbit, see Figure 21, the pattern of stars seen by the camera changes as shown in Figure 22. This figure highlights two particular stars. One is circled in red, the same star circled in Figure 21. The other is inside a yellow diamond. We see two images of each star. One image is outside the pink circle, the other is inside the pink circle. This pink circle is called the Einstein ring. As the camera moves rightward, the images move along the yellow and red curves. The star images outside the Einstein ring, the primary images, let's call them, move in the way one might expect, smoothly from left to right, but deflecting away from the black hole as they move. Can you figure out why the deflection is away from the hole instead of toward it? However, the secondary images inside the Einstein ring move in an unexpected manner. They appear to emerge from the right edge of the shadow, move outward into the annulus between the shadow and the Einstein ring, swing leftward around the shadow, and descend back toward the shadow's edge. You can understand this by going back to the upper drawing in Figure 21. The right ray passes near the black hole, so the right stellar image is near its shadow. Earlier in time, when the camera was further leftward, the right ray had to pass even closer to the black hole in order to bend more strongly and reach the camera. So the right image was very close to the edge of the shadow. By contrast, earlier in time, the left ray passed rather far from the hole, and so was nearly straight and produced an image rather far from the hole. Now, if you're ready, think through the subsequent motions of the images depicted in Figure 22. Lensing by a rapidly spinning black hole. Gargantua. The whirl of space generated by Gargantua's very fast spin changes the gravitational lensing. The star patterns in Figure 19, Gargantua, look somewhat different from those in Figure 22, a non-spinning black hole, and the streaming patterns differ even more. For Gargantua, the streaming, Figure 23 in your PDF companion, reveals two Einstein rings, shown as pink curves. Outside the outer ring, the stars stream rightward, for example, along the two red curves, as they did for a non-spinning black hole in Figure 22. However, the whirl of space has concentrated the stream into narrowed high-speed strips along the back edge of the hole's shadow, strips that bend somewhat sharply at the equator. The whirl has also produced eddies in the streaming, the closed red curves. The secondary image of each star appears between the two Einstein rings. Each secondary image circulates along a closed curve, for example, the two yellow curves, and it circulates in the opposite direction to the red streaming motions outside the outer ring. There are two very special stars in Gargantua's sky with gravitational lensing turned off. One lies directly above Gargantua's north pole, the other directly below its south pole. These are analogues of the star Polaris, which resides directly above the Earth's north pole. I placed 5 pointed stars at the primary, red, and secondary, yellow, images of Gargantua's pole stars. All the stars on the Earth's sky appear to circulate around Polaris, as we humans are carried around by the Earth's rotation. Similarly, all of Gargantua's primary stellar images circulate around the red pole star images as the camera orbits the hole. But their circulation paths, for example, the two red eddy curves, are highly distorted by the whirl of space and gravitational lensing. Similarly, all the secondary stellar images circulate around the yellow pole star images, for example, along the two distorted yellow curves. Why, for a non-spinning hole, Figure 22 in your PDF companion, did the secondary images appear to emerge from the black hole's shadow, swing around the hole, and descend back into the shadow, instead of circulating around a closed curve as for Gargantua, Figure 23 in your PDF companion? They actually do circulate around closed curves for a non-spinning hole. However, the inner edge of the closed curve is so close to the shadow's edge that it can't be seen. Gargantua's spin makes space whirl, and that whirl moves the inner Einstein ring outward, revealing the secondary image's full circulatory pattern, yellow curves in Figure 23, and revealing the inner Einstein ring. Inside the inner Einstein ring, the streaming pattern is more complicated. The stars in this region are tertiary and higher-order images of all the stars in the universe, the same stars as appear as primary images outside the outer Einstein ring and secondary images between the Einstein rings. In Figure 24, in your PDF companion, I show 5 small pictures of Gargantua's equatorial plane, with Gargantua itself in black, the camera's orbit in dashed purple, and a light ray in red. The light ray brings to the camera the stellar image that is at the tip of the blue arrow. The camera is moving counterclockwise around Gargantua. You can get a lot of insight into the gravitational lensing by walking yourself through these pictures one by one. Take note, the actual direction to the star is upward and rightward, see outer ends of the red rays. The camera and beginning of each ray point toward the stellar image. The 10th image is very near the left edge of the shadow, and the right secondary image is near the right edge. Comparing the directions of the camera for these images, we see that the shadow subtends about 150 degrees in the upward direction. This despite the fact that the actual direction from camera to center of Gargantua is leftward and upward. The lensing has moved the shadow relative to Gargantua's actual direction. Creating Interstellar's black hole and wormhole visual effects. Chris wanted Gargantua to look like what a spinning black hole really looks like when viewed up close, so he asked Paul to consult with me. Paul put me in touch with the Interstellar team he had assembled at his London-based visual effects studio, Double Negative. I wound up working closely with Oliver James, the chief scientist. Oliver and I talked by phone and Skype, exchanged emails and electronic files, and met in person in Los Angeles and at his London office. Oliver has a college degree in optics and atomic physics and understands Einstein's relativity laws, so we speak the same technical language. Several of my physicist colleagues had already done computer simulations of what one would see when orbiting a black hole and even falling into one. The best experts were Elaine Riazuelo at the Institut d'Astrophysics in Paris and Andrew Hamilton at the University of Colorado in Boulder. Andrew had generated black hole movies shown in planetariums around the world, and Elaine had simulated black holes that spin very, very fast, like Gargantua. So initially, I planned to put Oliver in touch with Elaine and Andrew and ask them to provide him the input he needed. I lived uncomfortably with that decision for several days, and then changed my mind. During my half-century physics career, I put great effort into making new discoveries myself and mentoring students as they made new discoveries. Why not, for a change, do something just because it's fun, I asked myself, even though others have done it before me. And so I went for it. And it was fun. And to my surprise, as a byproduct, it produced modest new discoveries. Using Einstein's relativistic laws of physics and leaning heavily on prior work by others, especially Brandon Carter at the Laboratoire Univers et Théories in France and Jana Levin at Columbia University, I worked out the equations Oliver needed. These equations compute the trajectories of light rays that begin at some light source, for example, a distant star, and travel inward through Gargantua's warped space and time to the camera. From those light rays, my equations then compute the images the camera sees, taking account not only of the light's sources and Gargantua's warping of space and time, but also the camera's motion around Gargantua. Having derived the equations, I implemented them myself, using user-friendly computer software called Mathematica. I compared images produced by my Mathematica computer code with Elaine Riazuelo's images, and when they agreed, I cheered. I then wrote up detailed descriptions of my equations and sent them to Oliver in London, along with my Mathematica code. My code was very slow and had low resolution. Oliver's challenge was to convert my equations into computer code that could generate the ultra-high-quality IMAX images needed for the movie. Oliver and I did this in steps. We began with a non-spinning black hole and a non-moving camera. Then we added the black hole's spin. Then we added the camera's motion, first motion in a circular orbit and then plunging into a black hole. And then we switched to a camera around a wormhole. At this point, Oliver hit me with a mini bombshell. To model some of the more subtle effects, he would need not only equations describing the trajectory of a ray of light, but also equations describing how the cross-section of a beam of light changes its size and shape during its journey past the black hole. I knew more or less how to do this, but the equations were horrendously complicated, and I feared making mistakes. So I searched the technical literature and found that in 1977, Serge Penault and Rob Roeder at the University of Toronto had derived the necessary equations in almost the form I needed. After a 3-week struggle with my own stupidities, I brought their equations into precisely the needed form, implemented them in Mathematica, and wrote them up for Oliver, who incorporated them into his own computer code. At last, his code could produce the quality images needed for the movie. At double negative, Oliver's computer code was just the beginning. He handed it over to an artistic team led by Eugenie von Tunzelmann, who added an accretion disk and created the background galaxy with its stars and nebulae that Gargantua would lens. Her team then added the endurance and rangers and landers and the camera animation, its changing motion, direction, field of view, etc., and molded the images into intensely compelling forms, the fabulous scenes that actually appear in the movie. In the meantime, I puzzled over the high-resolution film clips that Oliver and Eugenie sent me, struggling to extract insights into why the images look like they look, and why the star fields stream as they stream. For me, those film clips are like experimental data. They reveal things I never could have figured out on my own without those simulations. For example, the things I described in the previous section. Refer to figures 23 and 24 in your PDF companion. We plan to publish one or more technical papers describing the new things we learned. Imaging a gravitational slingshot. Although Chris chose not to show any gravitational slingshots in Interstellar, I wondered what they would look like to Cooper as he piloted the Ranger toward Miller's planet. So I used my equations and Mathematica to simulate them and produce images. My images have far lower resolution than Oliver's and Eugenie's due to my code's slowness. In your PDF companion, Figure 25 shows a sequence of images as Cooper's Ranger swings around an intermediate mass black hole, IMBH, to initiate its descent toward Miller's planet, in my scientist's interpretation of Interstellar. This is the slingshot described in Chapter 7. In the top image of Figure 25, Gargantua is in the background with the IMBH passing in front of it. The IMBH grabs light rays from distant stars that are headed toward Gargantua, swings the rays around itself, and ejects them toward the camera. This explains the donut of starlight that surrounds the IMBH's shadow. Although the IMBH is 1,000 times smaller than Gargantua, it is far closer to the Ranger than is Gargantua, so it looks only modestly smaller. As the IMBH appears to move rightward, as seen by the slingshot moving camera, it leaves Gargantua's primary shadow behind itself, middle picture in Figure 25, and it pushes a secondary image of Gargantua's shadow ahead of itself. These two images are completely analogous to the primary and secondary images of a star gravitationally lensed by a black hole. But now it is Gargantua's shadow that is being lensed by the IMBH. In the bottom picture, the secondary shadow is shrinking in size as the IMBH moves onward. By this time, the slingshot is nearly complete, and the camera on board the Ranger is headed downward toward Miller's planet. As impressive as these images may be, they can be seen only up close to the IMBH and Gargantua, not from the great distance of Earth. To astronomers on Earth, the most visually impressive things about gigantic black holes are jets that stick out of them and the light from brilliant disks of hot gas that orbit them. To these, we'll now turn. 9. Disks and jets. Status of science. Truth. Quasars. Most of the objects seen by radio telescopes are huge clouds of gas, clouds far larger than any star. But in the early 1960s, a few tiny objects were found. Astronomers named these objects quasars for quasi-stellar radio sources. In 1962, the Caltech astronomer Martin Schmidt, looking through the world's largest optical telescope on Palomar Mountain, discovered light coming from a quasar called 3C273. It looked like a bright star with a faint jet shooting out of it. This was weird. When Schmidt split 3C273's light into its various colors, as is sometimes done by sending light through a prism, he saw a set of spectral lines. At first sight, these were unlike any spectral lines he had ever seen. But in February 1963, after a few months' struggle, he realized the lines were unfamiliar simply because their wavelengths were 16% larger than normal. This is called the Doppler shift. It was caused by the quasars moving away from Earth at 16% the speed of light, about c/6. What could cause that ultra-fast motion? The least crazy explanation Schmidt could find was the expansion of the universe. As the universe expands, objects far from Earth move apart from us at very high speed, and objects nearer move away more slowly. 3C-273's enormous speed, 1/6 that of light, meant that 3C-273 was 2 billion light-years from Earth, nearly the farthest object that had ever been seen at that time. From its brightness and its distance, Schmidt concluded that 3C-273 puts out 4 trillion times more power in light than the Sun, and 100 times more power than the brightest galaxies. This prodigious power fluctuated on times as short as a month, so most of the light must be coming from an object so small that the light can travel across it in 1 month's time, far smaller than the distance from Earth to the nearest star, Proxima Centauri. And other quasars with almost as much power fluctuated on times of a few hours, so they had to be not much larger than our solar system. 100 times the power of a bright galaxy, coming from a region the size of our solar system. That was phenomenal. Black holes and accretion disks. How could so much power come out of a region so small? When we think about the fundamental forces in nature, there are 3 possibilities: chemical energy, nuclear energy, or gravitational energy. Chemical energy is the energy released when molecules combine together to make new kinds of molecules. An example is burning gasoline, which combines oxygen from the air with gasoline molecules to make water and carbon dioxide, and a lot of heat. The power from that would be far, far, far too little, though. Nuclear energy results when atomic nuclei combine together to make new atomic nuclei. Examples are an atomic bomb, a hydrogen bomb, and the burning of nuclear fuel inside a star. Though this can be far more powerful than chemical energy, think of the difference between a gasoline fire and a nuclear bomb, astrophysicists couldn't see any plausible way for nuclear energy to power quasars. It was still too puny. So the only possibility left was gravitational energy, the same kind of energy we were driven to when navigating the Endurance around Gargantua. For the Endurance, gravitational energy was harnessed by a slingshot around an intermediate mass black hole. The black hole's intense gravity was key. For quasars, similarly, the power must come from a black hole. For several years, astrophysicists struggled to figure out how a black hole could do the job. The answer was found in 1969 by Donald Lynden Bell at the Royal Greenwich Observatory in England. A quasar, Lynden Bell hypothesized, is a gigantic black hole surrounded by a disk of hot gas, an accretion disk, that is threaded by a magnetic field. Hot gas in our universe is almost always threaded by magnetic fields. These fields are locked into the gas. The gas and fields move together in lockstep. When threading an accretion disk, a magnetic field becomes a catalyst for converting gravitational energy into heat and then light. The field provides ultra-strong friction that slows the gas's circumferential motion, reducing the centrifugal force that holds it out against the pull of gravity, so the gas moves inward toward the black hole. As the gas moves inward, the hole's gravity speeds up its orbital motion by even more than the friction slowed it. In other words, gravitational energy is converted into kinetic energy, energy of motion. Magnetic friction then converts half that new kinetic energy into heat and light, and the process repeats. The energy comes from the black hole's gravity. The agents for extracting it are magnetic friction and the disk's gas. The quasar's bright light, seen by astronomers, comes from the disk's heated gas, Lynden Bell concluded. Moreover, the magnetic field accelerates some of the gas's electrons to high energies, and the electrons then spiral around the magnetic force lines, emitting the quasar's observed radio waves. Lyndon Bell worked out the details of all this using a combination of the Newtonian, relativistic, and quantum laws of physics. He easily explained everything about quasars that astronomers had seen, except their jets. His technical article describing his reasoning and his calculations, Lyndon Bell, 1979, is one of the great astrophysics articles of all time. The jets. Extracting power from whirling space. Over the next few years, astronomers discovered many more jets sticking out of quasars and studied them in great detail. It soon became clear that they are streams of hot, magnetized gas ejected from the quasar itself, from the black hole and its accretion disk. And the ejection is extremely powerful. The gas travels out the jets at nearly the speed of light. As it travels, and when it plows into material far from the quasar, the gas emits power in light, in radio waves, in X-rays, and even in gamma rays. The jets are sometimes as bright as the quasar itself, 100 times brighter than the brightest galaxies. Astrophysicists struggled for nearly a decade to explain how the jets are powered and what makes them so fast, so narrow, and so straight. The answers came in several variants, with the most interesting in 1977 from Roger Blandford at the University of Cambridge, England, and his student Roman Znajek, building on foundations laid by the Oxford physicist Roger Penrose. The accretion disk's gas gradually spirals into the black hole. When crossing the hole's event horizon, each bit of gas deposits its bit of magnetic field onto the horizon, and then the surrounding disk holds it there, Blandford and Znajek concluded. As the black hole spins, it drags space into whirling motion, and the whirling space makes the magnetic field whirl. The whirling magnetic field generates an intense electric field, like in a dynamo at a hydroelectric power station. The electric field and the whirling magnetic field together fling plasma, hot ionized gas, upward and downward at near light speed, creating and powering two jets. The jet's directions are held steady, when averaged over years, by the black hole's spin, which is steady due to gyroscopic action. In 3C273, only one jet was bright enough to see, but in many other quasars, both are seen. Blandford and Znajek worked out the full details, relying heavily on Einstein's relativistic laws. They were able to explain most everything about the jets that astronomers see. In a second variant of the explanation, the whirling magnetic field is anchored in the accretion disk instead of the hole, and is dragged around by the disk's orbital motion. Otherwise, the story is the same. Dynamo action, plasma flung out. This variant works well even if the black hole isn't spinning. But we're pretty sure that most black holes spin fast, so I suspect the Blandford-Znajek mechanism is the most common one in quasars. However, I may be prejudiced. I spent much time in the 1980s exploring aspects of the Blandford-Znajek ideas, and even co-authored a technical book about them. Whence comes the disk? Tidal forces tear stars apart. Lyndon Bell, in 1969, speculated that quasars live at the centers of galaxies. We don't see a quasar's host galaxy, he said, because its light is so much fainter than the quasar's light. The quasar drowns the galaxy out. In the decades since then, with improving technology, astronomers have found the galaxy's light around many quasars, confirming Lyndon Bell's speculation. In those recent decades, we also learned where most of the disk's gas comes from. Occasionally, a star strays so close to the quasar's black hole that the hole's tidal gravity tears the star apart. Much of the shredded star's gas is captured by the black hole and forms an accretion disk, but some of the gas escapes. In recent years, thanks to improving computer technology, astrophysicists simulated this. Figure 26 in your PDF companion is from a recent simulation by James Guillochon, Enrico Ramirez-Ruiz, and Daniel Kaysen, University of California at Santa Cruz, and Stefan Roswag, University of Bremen. At time zero, not shown, the star was headed almost precisely toward the black hole, and the hole's tidal gravity was beginning to stretch the star toward the hole and squeeze it from the sides. 12 hours later, the star is strongly deformed and at the location shown in Figure 26. Over the next few hours, it swings around the hole along the blue gravitational slingshot orbit and deforms further, as shown. By 24 hours, the star is flying apart. Its own gravity can no longer hold it together. The star's subsequent fate is shown in Figure 27 in your PDF companion, from a different simulation by James Guillochon, together with Suvi Ghazari, Johns Hopkins University. For a movie of this simulation, see http://hubblesite.org/newscenter/archive/releases/2012/18/video/A/. The top two images in Figure 27 are shortly before the beginning and shortly after the end of Figure 26. I enlarged these two images tenfold compared to the others to make the hole and the disrupting star visible. As the whole set of images shows, over the subsequent several years, much of the star's matter is captured into orbit around the black hole, where it begins to form an accretion disk, and the remaining matter escapes from the hole's gravitational pull along a streaming, jet-like trajectory. Gargantua's accretion disk and missing jet. A typical accretion disk and its jet emit radiation: X-rays, gamma rays, radio waves, and light. Radiation so intense that it would fry any human nearby. To avoid frying, Christopher Nolan and Paul Franklin gave Gargantua an exceedingly anemic disk. Now, anemic doesn't mean anemic by human standards, just by the standards of typical quasars. Instead of being 100 million degrees like a typical quasar's disk, Gargantua's disk is only a few thousand degrees, like the sun's surface, so it emits lots of light but little to no X-rays or gamma rays. With gas so cool, the atom's thermal motions are too slow to puff the disk up much. The disk is thin and nearly confined to Gargantua's equatorial plane, with only a little puffing. Disks like this might be common around black holes that have not torn a star apart in the past millions of years or more, that have not been fed in a long time. The magnetic field, originally confined by the disk's plasma, may have largely leaked away, and the jet, previously powered by the magnetic field, may have died. Such is Gargantua's disk, jetless and thin and relatively safe for humans. Relatively. Gargantua's disk looks quite different from the pictures of thin disks that you see on the web or in astrophysicists' technical publications, because those pictures omit a key feature: the gravitational lensing of the disk by its black hole. Not so in Interstellar, where Chris insisted on visual accuracy. Eugenie von Tunzelmann was charged with putting an accretion disk into Oliver James' gravitational lensing computer code, the code I described in Chapter 8. As a first step, just to see what the lensing does, Eugenie inserted a disk that was truly infinitesimally thin and lay precisely in Gargantua's equatorial plane. For this book, she has provided a more pedagogical version of that disk, made of equally spaced color swatches. See inset in Figure 28 in your PDF companion. If there had been no gravitational lensing, the disk would have looked like the inset. The lensing produced huge changes from this. See body of Figure 28. You might have expected the back portion of the disk to be hidden behind the black hole. Not so. Instead, it is gravitationally lensed to produce two images, one above Gargantua and the other below. Refer to Figure 29 in your PDF companion. Light rays emitted from the disk's top face behind Gargantua travel up and over the hole to the camera, producing the disk image that wraps over the top of Gargantua's shadow in Figure 28, and similarly for the disk image that wraps under the bottom of Gargantua's shadow. Inside these primary images, we see thin secondary images of the disk, wrapping over and under the shadow, near the shadow's edge. And if the picture were made much larger, you would see tertiary and higher order images, closer and closer to the shadow. Can you figure out why the lensed disk has the form you see? Why is the primary image wrapping under the shadow, attached to the thin secondary image wrapping over it? Why are the paint swatches on the overwrapping and underwrapping images widened so greatly, and those on the sides squeezed? Gargantua's space whirl, space moving toward us on the left and away on the right, distorts the disk images. It pushes the disk away from the shadow on the left and toward the shadow on the right, so the disk looks a bit lopsided. Can you explain why? To get further insight, Eugenie von Tunzelmann and her team replaced their variant of the color swatch disk in Figure 28 with a more realistic thin accretion disk, that which you see in Figure 30. This was much more beautiful, but it raised problems. Chris did not want his mass audience to be confused by the lopsidedness of the disk and black hole shadow, and the shadow's flat left edge, and the complicated starfield patterns near that edge. So he and Paul slowed Gargantua's spin to 0.6 of the maximum, making these weirdnesses more modest. Eugenie had already omitted the Doppler shift caused by the disk's motion toward us on the left and away on the right. It would have made the disk far more lopsided, bright blue on the left and dim red on the right, totally confusing to a mass audience. The artistic team at Double Negative then gave the disk the texture and surface relief that we expect a real, anemic accretion disk to have, puffing it up a bit in a manner that varied from place to place. They made the disk hotter, brighter near Gargantua, and cooler, dimmer, at larger distances. They made it thicker at larger distances because it is Gargantua's tidal gravity that squeezes the disk into the equatorial plane, and tidal gravity is much weaker farther from the black hole. They added the background galaxy, many layers of artwork, dust, nebulae, stars, and they added lens flare, the haze and glare and streaks of light that would arise from scattering of the disk's bright light in a camera lens. The results were the wonderful and compelling images in the movie. Eugenie and her team also, of course, made the disk's gas orbit Gargantua, as it must to avoid falling in. When combined with gravitational lensing, the gas's orbital motion produced the impressive streaming effects in the movie. What a joy it was when I first saw these images. For the first time ever, in a Hollywood movie, a black hole and its disk depicted as we humans will really see them when we've mastered interstellar travel. And for the first time for me as a physicist, a realistic disk, gravitationally lensed, so it wraps over the top and bottom of the hole instead of being hidden behind the hole's shadow. With Gargantua's disk anemic, though gorgeously beautiful and with no jet, is Gargantua's environment truly benign? Amelia Brand thinks so. 10. Accident is the first building block of evolution. Status of science: truth. In Interstellar, upon finding Miller's planet sterile, Amelia Brand argues for going next to a planet very far from Gargantua, Edmund's planet, instead of the closer Man's planet. Accident is the first building block of evolution, she tells Cooper. But when you're orbiting a black hole, not enough can happen. It sucks in asteroids and comets, other events that would otherwise reach you. We need to go further afield. This is one of the few spots in Interstellar where the characters get the science wrong. Christopher Nolan knew that Brand's argument was wrong, but he chose to retain these lines from Jonah's draft of the screenplay. No scientist has perfect judgment. Although Gargantua tries to suck asteroids and comets into itself, and planets and stars and small black holes too, it rarely succeeds. Why? When far from Gargantua, any object has a large angular momentum unless its orbit is headed almost directly toward the black hole. That large angular momentum produces centrifugal forces that easily overwhelm Gargantua's gravitational pull whenever the object's orbit carries it near the black hole. A typical orbit has a form like that seen in Figure 31 of your PDF companion. The object travels inward, pulled by Gargantua's strong gravity. But before it reaches the horizon, centrifugal forces grow strong enough to fling the object back outward. This happens over and over again, almost endlessly. The only thing that can intervene is an accidental near encounter with some other massive body, a small black hole or star or planet. The object swings around the other body on a slingshot trajectory and thereby is thrown into a new orbit around Gargantua with a changed angular momentum. The new orbit almost always has a large angular momentum, like the old one did, with centrifugal forces that save the object from Gargantua. Very rarely, the new orbit carries the object almost directly toward Gargantua, with a small enough angular momentum that centrifugal forces can't win, so the object plunges through Gargantua's horizon. Astrophysicists have carried out simulations of the simultaneous orbital motions of millions of stars around a gigantic black hole like Gargantua. Slingshots gradually change all the orbits and thereby change the density of stars, how many stars there are in some chosen volume. The star density near Gargantua does not go down, it grows. And the density of asteroids and comets will also grow. Random bombardment by asteroids and comets will become more frequent, not less frequent. The environment near Gargantua will become more dangerous for individual life forms, including humans, promoting faster evolution if enough individuals survive. With Gargantua and its dangerous environment under our belts, let's make a brief change of direction to Earth and our solar system, to disaster on Earth and the extreme challenge of escaping disaster via interstellar travel. 3. Disaster on Earth. 11. Blight. Status of science: speculation. In 2007, when Jonah Nolan joined Interstellar as screenwriter, he set the movie in an era when human civilization is a pale remnant of today's and is being dealt a final blow by blight. Later, when Jonah's brother Christopher Nolan took over as director, he embraced this idea. But Linda Obst, Jonah, and I worried a bit about the scientific plausibility of Cooper's world, as envisioned by Jonah. How could human civilization decline so far, yet seem so normal in many respects? And is it scientifically possible that a blight could wipe out all edible crops? I don't know much about blight, so we turned to experts for advice. I organized a dinner at the Caltech faculty club, the Athenaeum, on July 8, 2008. Great food, superb wine. Jonah, Linda, me, and 4 Caltech biologists with the right mixture of expertise. Elliot Meyerowitz, an expert on plants. Jared Ledbetter, an expert on the diverse microbes that degrade plants. Mel Simon, an expert on the cells that make up plants and how they are affected by microbes. And David Baltimore, a Nobel laureate with a broad perspective on all of biology. Caltech is a wonderful place. Named the top university in the world by the Times of London in each of the last 3 years, it is small enough, just 300 professors, 1,000 undergrads, and 1,200 graduate students, that I know Caltech experts in all branches of science. It was easy to find and recruit the experts we needed for our blight dinner. As dinner began, I placed a microphone at the center of our round table and recorded our 2.5-hour freewheeling conversation. This chapter is based on that recording, but I've paraphrased what people said, and they checked and approved my paraphrasing. Our final consensus, easily reached, is that Cooper's world is scientifically possible, but not very likely. It is very unlikely to happen, but it could. That's why I labeled this chapter speculative. Cooper's world. Over wine and hors d'oeuvres, Jonah described his vision for Cooper's world. Some combination of catastrophes has reduced the population of North America tenfold or more, and similarly on all other continents. We have become a largely agrarian society, struggling to feed and shelter ourselves. But ours is not a dystopia, Life is still tolerable and in some ways pleasant, with little amenities such as baseball continuing. However, we no longer think big. We no longer aspire to great things. We aspire to little more than just keeping life going. Most of us think that catastrophes are finished, that we humans are securing ourselves in this new world and things may start improving. But in reality, the blight is so lethal and leaps so quickly from crop to crop that the human race is doomed within the lifetime of Cooper's grandchildren. What catastrophes? What kind of catastrophes could have produced Cooper's world? Our biologist experts offered a number of possible but improbable answers. Here are several. Ledbetter. Today, 2008, most people aren't growing their own food. We're dependent on a global system for growing and distributing food and for distributing water. You could imagine that system breaking down due to some biological or geophysical catastrophe. As an example on a small scale, if there was no snow in the Sierra Nevada mountains for a few consecutive years, there would be little drinking water in Los Angeles. 10 million people would be forced to migrate, and agricultural output in California would plummet. You can easily imagine much larger-scale catastrophes. In Cooper's world, with a vastly reduced population and a return to agrarian society, the production and distribution problems are lessened. Simon. Another possible catastrophe. Over human history, there has been a continual battle between us and pathogens, microbes that attack the human body or attack plants or other animals. We humans have developed a sophisticated immune system to deal with the pathogens that attack us directly. But the pathogens keep evolving, and we're always half a step behind them. At some point, there could be a catastrophe where the pathogens change so fast that our immune systems can't keep up. Baltimore. For example, the AIDS virus could quickly evolve into a far more contagious form, one transmitted by coughing or breathing instead of sex. Simon. The Earth's ice caps, melting due to global warming, could release a long-dormant lethal pathogen from before the last ice age. Ledbetter. Yet another scenario. People could panic about global warming. The warming is largely caused by increasing carbon dioxide in the atmosphere. To save us, they might fertilize the Earth's oceans to produce algae that will eat much of the atmosphere's carbon dioxide via photosynthesis. A lot of iron thrown into the oceans could do the job. But there might be catastrophic unintended side effects. You might get some new kinds of algae that produce toxins, poison chemicals, not deadly life forms, that poison the oceans. There would be a massive kill-off of fish and plant life. Human civilization depends heavily on the oceans. This could be catastrophic for humans. Is it impossible? Not at all. Experiments have been done where iron was thrown locally into the ocean to produce algae, so much algae that it could be seen from space as green spots. Some of the algae that bloomed were of types never before known to science. We were lucky. The new algae were not noxious, but they might have been. Meyerowitz. Ultraviolet light, streaming through our atmosphere's ozone hole, could mutate your enormous bloom of algae so it creates new pathogens. These pathogens could wipe out plants in the ocean and then jump to land and start wiping out crops. Baltimore. When faced with catastrophes like these, our only hope for dealing with them is advanced science and technology. If, politically, we don't invest in science and technology, or we hobble them by anti-intellectual ideologies such as denial of evolution, the very source of these catastrophes, we may find ourselves without the solutions we need. And then there is blight, the consequence of many of these scenarios. Blight. Blight is a general term for most any disease in a plant that is caused by a pathogen. Baltimore. If you want something to wipe out humanity, there might be no better way than a blight that attacks plants. We are dependent on plants to eat. Yes, we can eat animals or fish instead, but they ate plants. Meyerowitz. It might be sufficient for the blight just to kill off the grasses and nothing else. Grasses are the basis of most of our agriculture: rice, corn, barley, sorghum, wheat, and most animals that we eat feed on grasses. Meyerowitz. We already live in a world where 50% of the food grown is destroyed by pathogens, and it's much higher than that in Africa. Fungi, bacteria, viruses, they all can be pathogens. The East Coast used to be covered with chestnut trees. They are no more. They were killed by a blight. The species of banana preferred by most people in the 18th century was wiped out by a blight. The replacement species, the Cavendish banana, today is being threatened by blight. Kip. I thought that blights are specialists that attack only one narrow group of plants and don't jump to others. Ledbetter. There are also generalist blights. There seems to be a trade-off between being a generalist that attacks many species and a specialist that attacks only a few. For the specialist blight, the lethality can be turned up really high. It can knock out, say, 99% of a very specific group of plants. For the generalist, the range of plants attacked is much broader, but its lethality for any one plant in that range might be much smaller. That's a pattern we see again and again in nature. Linda. Could you have a generalist blight that becomes much more lethal? Meyerowitz. Something like that has happened before. Early in the Earth's history, when cyanobacteria started making oxygen, thereby changing radically the composition of the Earth's atmosphere, they managed to kill most everything else on Earth. Ledbetter. But the oxygen was a lethal byproduct, a poison, produced by the cyanobacteria, not a generalist pathogen. Baltimore. We may not have seen it, but I can imagine a very lethal specialist pathogen becoming a lethal generalist. It could spread the range of plants it attacks with the help of an insect that carries it to many species. A Japanese beetle, for example, which eats something like 200 different plant species, could infect many species with the pathogen it carries, and the pathogen might adapt to attack those species lethally. Meyerowitz. I can conceive of a totally lethal generalist, a pathogen that attacks chloroplasts. Chloroplasts are something that all plants have in common. They are crucial to photosynthesis, the process where a plant combines sunlight with carbon dioxide from the air and water from its roots to produce carbohydrates that it needs for growth. Without chloroplasts, a plant will die. Now suppose that some new pathogen evolves, for example in the oceans, that attacks chloroplasts. It could wipe out all algae and plant life in the oceans and jump to the land where it wipes out all land plants. So everything becomes a desert. This is possible. I see nothing to prevent it. But it's not very plausible. It is unlikely ever to happen, but it could be a basis for Cooper's world. These speculations give us a sense of the kinds of nightmare scenarios that could keep a biologist awake at night. In Interstellar, the focus is a lethal generalist blight running rampant over the Earth. But Professor Brand has a secondary worry: humankind's running out of oxygen to breathe. 12. Gasping for oxygen. Status of science. Speculation. Early in Interstellar, Professor Brand says to Cooper, Earth's atmosphere is 80% nitrogen. We don't even breathe nitrogen. Blight does. And as it thrives, our air gets less and less oxygen. The last people to starve will be the first to suffocate. And your daughter's generation will be the last to survive on Earth. Is there any basis in science for the professor's prediction? This question lies at the interface of two branches of science, biology and geophysics. So I asked the biologists at our blight dinner, particularly Elliot Meyerowitz, and I asked two geophysicists, Caltech professors Gerald Wasserberg, an expert on the origin and history of the Earth, Moon, and Solar System, and Yuk Young, an expert on the physics and chemistry of our Earth's atmosphere and the atmospheres of other planets. From them, and from technical articles they pointed me to, I learned the following. Creating and destroying breathable oxygen. The oxygen we breathe is O2. a molecule made of two oxygen atoms bound together by electrons. There is lots of oxygen on Earth in other forms: carbon dioxide, water, minerals in the Earth's crust, to name a few. But our bodies can't use that oxygen until some organism liberates it and converts it to O2. The atmosphere's O2 is destroyed by breathing, burning, and decay. When we breathe in O2, our bodies combine it with carbon to form carbon dioxide, CO2, releasing lots of energy that our bodies use. When wood is burned, the flames rapidly combine the atmosphere's O2 with the wood's carbon to form CO2, which generates the heat that keeps the burning going. When dead plants decay on the forest floor, their carbon is slowly combined with the atmosphere's O2 to form CO2 and heat. The atmosphere's O2 is created primarily by photosynthesis. Chloroplasts in plants use energy from sunlight to split CO2 into C and O2. The O2 is liberated into the Earth's atmosphere, while the plants combine the carbon with hydrogen and oxygen from water to form the carbohydrates that they need for growth. O2 destruction and CO2 poisoning. Suppose evolution creates a pathogen that destroys chloroplasts, as speculated by Elliot Meyerowitz at the end of the last chapter. Photosynthesis ends, not all at once, but gradually as plants die out. O2 is no longer being created, but it is still being destroyed by breathing, burning, and decay, primarily decay, it turns out. Fortunately for the remaining humans, there is not enough decaying plant life on the Earth's surface to swallow up all the O2. Most of the decay will be finished after 30 years, and only about 1% of the O2 will be used up. There is still plenty for Cooper's children and grandchildren to breathe, if they can find anything to eat. But that 1% of the atmospheric O2 will have been converted into carbon dioxide, which means 0.2% of the atmosphere will then be CO2, since most of the atmosphere is nitrogen. That's enough CO2 to make breathing unpleasant for highly sensitive people and perhaps drive the Earth's temperature up, via the greenhouse effect, by 10 degrees Celsius, 18 degrees Fahrenheit. Unpleasant for everyone, to put it mildly. To make everyone's breathing uncomfortable and induce drowsiness, 10 times more atmospheric O2 would have to be converted into CO2, and to kill most everyone by CO2 poisoning, an additional 5 times more would have to be converted, a factor of 50 in all. I have not found a plausible mechanism for this. So is Professor Brand wrong? Even theoretical physicists can make mistakes, especially theoretical physicists. I know. I am one. Probably, yes, he is wrong, but conceivably, no. The professor could be right, but it would require geophysicists' understanding of ocean bottoms to be severely flawed. There is undecayed organic material on the ocean bottoms as well as on land. Geophysicists estimate that the amount on ocean bottoms is about 1/20th that on land. If they are wrong, and there is 50 times more on the ocean bottoms than on land, and if there is a mechanism to quickly dredge it up, then its decay to produce CO2 could leave everyone gasping for oxygen and dying of CO2 poisoning. Now, once every many thousand years, an instability triggers the ocean to turn over. Water from the surface sinks to the bottom and drives bottom water to the surface. It is conceivable that in Cooper's era there is such an overturn so vigorous that the upwelling bottom water brings with itself most of the ocean bottom's organic material. Suddenly exposed to the atmosphere, this material could decay, converting atmospheric O2 into lethal amounts of CO2. Conceivable, yes, but highly improbable on 2 counts. Highly unlikely that there is 1,000 times more undecayed ocean bottom organic material than geophysicists think, and highly unlikely that a sufficiently vigorous oceanic overturn will occur. Nevertheless, in Interstellar the Earth is surely dying and humanity must find a new home. The solar system, aside from Earth, is inhospitable. So the search is on, beyond our solar system. 13. Interstellar travel. Professor Brand tells Cooper, in their first meeting, that the Lazarus missions have been sent out to search for new homes for humanity. Cooper responds, "There's no planet in our solar system that can support life, and it'd take 1,000 years to reach the nearest star. That doesn't even qualify as futile." "Where did you send them, Professor?" The worse than futile challenge, if you don't have a wormhole, is obvious when you realize just how far it is to the nearest stars. Distances to nearest stars. Status of science, truth. The nearest star, other than our Sun, thought to have a habitable planet, is Tau Ceti, 11.9 light-years from Earth. So traveling at light speed, you would need 11.9 years to reach it. If there are any habitable planets closer than that, they can't be much closer. To get some sense of just how far Tau Ceti is compared to more familiar things, let's scale its distance down enormously. Imagine it as the distance from New York City to Perth, Australia, about halfway around the world. The very nearest star, other than the Sun, is Proxima Centauri, 4.24 light-years from Earth, but there is no evidence it has habitable planets. With Tau Ceti's distance imagined as New York to Perth, then Proxima Centauri is like New York to Berlin. It's not a lot closer than Tau Ceti. For comparison, the most distant unmanned spacecraft that humans have sent into interstellar space is Voyager 1, now about 18 light-hours from Earth. It has been traveling for 37 years to get there. With Tau Ceti's distance imagined as New York to Perth, then Earth to Voyager 1 is about 3 kilometers, 2 miles. The distance from the Empire State Building to the southern end of Greenwich Village. That's hugely less than New York to Perth. The Earth to Saturn is even smaller, 200 meters, 2 east-west blocks in New York City, from the Empire State Building to Park Avenue. The Earth to Mars is just 20 meters, and the Earth to the Moon, the greatest distance humans have ever yet traveled, is just 7 centimeters. About 2.5 inches. Compare what we have achieved in going to the Moon, 2.5 inches, with the challenge of going halfway around the world. That's the leap of technology required to take humans to habitable planets outside our solar system. Travel times with 21st century technology. Status of science, truth. Voyager 1 is traveling out of the solar system at 17 kilometers per second, having been boosted by gravitational slingshots around Jupiter and Saturn. In Interstellar, the Endurance travels from Earth to Saturn in 2 years, at an average speed of about 20 kilometers per second. The fastest speed I think rocket technology plus solar system slingshots are likely to achieve in this, the 21st century, is about 300 kilometers per second. At that 300 kilometers per second, we would need 5,000 years to reach Proxima Centauri and 13,000 years to reach Tau Ceti. Not a pleasant prospect. To get there far faster in the 21st century, you need something like a wormhole. Far future technology. Status of science, educated guess. Technically savvy scientists and engineers have put much effort into conceiving far future technologies that might make possible near light-speed travel. You can learn a lot about their ideas by browsing the web. It will take many centuries for humans to make any of those ideas real, I think. But they do convince me that ultra-advanced civilizations are likely to travel between the stars at 1/10 the speed of light or faster. Here are 3 far-out examples of near-light-speed propulsion that intrigue me. Thermonuclear fusion. Status of science, educated guess. Thermonuclear fusion is the most conventional of the 3 ideas. R&D to develop controlled fusion power plants on Earth was initiated in the 1950s, and full success will not come until the 2050s, a full century of R&D. That's a realistic measure of the difficulties. And what will fusion power plants in 2050 mean for spacecraft propulsion by fusion? The most practical designs may achieve 100 kilometers per second, and conceivably 300 kilometers per second by the end of this century. A whole new approach to harnessing fusion will be required for reaching near light speed. A simple calculation shows fusion's possibility. When two deuterium, heavy hydrogen, atoms are fused to form a helium atom, 0.0064, nearly 1%, of their rest mass gets converted into energy. If this were all transformed to kinetic energy, energy of motion, of the helium atom, the atom would move at about 1/10 the speed of light. This suggests that if we could convert all the fusion energy of deuterium fuel into ordered motion of a spacecraft, we could achieve a spacecraft speed of roughly 1/10 the speed of light, and somewhat higher if we are clever. In 1968, Freeman Dyson, a brilliant physicist for whom I have great respect, described and analyzed a crude propulsion system that, in the hands of a sufficiently advanced civilization, could achieve this. Thermonuclear bombs, hydrogen bombs, are detonated just behind a hemispherical shock absorber that is 20 kilometers in diameter. The bomb debris pushes the ship forward, achieving, in Dyson's most optimistic estimate, a speed 1/30th that of light. A less crude design could do somewhat better. In 1968, Dyson estimated that such a propulsion system would not be practical any sooner than the late 22nd century, 150 years from now. I think that's overly optimistic. Laser beam and light sail. Status of science, speculation. In 1962, Robert Forward, another physicist whom I respect, wrote a short article in a popular magazine about a spacecraft with a sail, pushed by a distant, focused laser beam. In a 1984 technical article, he made this concept more sophisticated and precise. An array of solar-powered lasers in space or on the moon generates a laser beam with 7.2 terawatts of power, about twice the total power consumption of the United States in 2014. This beam is focused by a Fresnel lens 1,000 kilometers in diameter. It is focused onto a distant sail, 100 kilometers in diameter and weighing about 1,000 metric tons, that is attached to a less massive spacecraft. The beam direction must be accurate to about a millionth of an arcsecond. The beam's light pressure pushes the sail and spacecraft up to about a fifth the speed of light, halfway through a 40-year trip to Proxima Centauri. A modification of this scheme then slows the ship down during the second half of the trip, so it arrives at its destination with a speed low enough to rendezvous with a planet. Can you figure out how the slowdown is achieved? Forward, like Dyson, imagined his scheme practical in the 22nd century. When I look at the technical challenges, I think longer. Gravitational slingshots in a black hole binary. Status of science, speculation. My third example is my own wild, very wild, variant of an idea due to Dyson. Suppose you want to fly across much of the universe, not just interstellar travel, but intergalactic travel, at near light speed in a few years of your own life. You can do so with the aid of two black holes that are orbiting each other, a black hole binary. They must be in a highly elliptical orbit and must be large enough that their tidal forces do not destroy your ship. Using chemical or nuclear fuel, you navigate your ship into an orbit that comes close to one of the black holes, a so-called zoom-whirl orbit. Your ship zooms close to the hole, whirls around it a few times, and then when the hole is traveling nearly directly toward its companion, the ship zooms out, crosses over to the companion hole, and slides into a whirl around it. If the two holes are still headed toward each other, the whirl is brief. You zoom back toward the first hole. If the holes are no longer headed toward each other, the whirl is much longer. You must park yourself in orbit around the second hole until the holes are again headed toward each other, and then launch back toward the first hole. In this way, always traveling between holes only when the holes are approaching each other, your ship gets boosted to higher and higher speeds, approaching as close as you wish to the speed of light if the binary is sufficiently elliptical. It is a remarkable fact that you only need a small amount of rocket fuel to control how long you linger around each hole. The key is to navigate onto the hole's critical orbit, and there perform your controlled whirl. I discuss the critical orbit in Chapter 27. For now, suffice it to say that this is a highly unstable orbit. It is rather like riding a motorcycle around a very smooth volcano rim. If you balance delicately, you can stay on the rim as long as you want. When you wish to leave, a slight turn of the bike's front wheel will send you careening off the rim. When you want to leave the critical orbit, a slight rocket thrust will enable centrifugal forces to take over and send your ship careening toward the other black hole. Once you are as close to the speed of light as you wish, you can launch yourself off a critical orbit toward your target galaxy in the distant universe. The trip may be long, as much as 10 billion light-years distance, but when you move at near light speed, your time flows far more slowly than on Earth. If you are close enough to light speed, you can make it to your target in a few years or less, as measured by you, slowing down with the aid of a highly elliptical black hole binary at your target, if you can find one. You can return home by the same method, but your homecoming may not be pleasant. Billions of years will have passed at home, while you have aged only a few years. Imagine what you find. These types of slingshots could provide a means for spreading a civilization across the great reaches of intergalactic space. The principal obstacle, perhaps insurmountable, is finding or making the needed black hole binaries. The launch binary might not be a problem if you are a sufficiently advanced civilization, but the slowdown binary is another matter. What happens to you if there is no slowdown binary, or there is one but your aim is bad and you miss it? This is a tricky question because of the expansion of the universe. Think about it. As exciting as these three far future propulsion systems may seem, they truly are far future. Using 21st century technology, we are stuck with thousands of years to reach other solar systems. The only hope, an exceedingly faint hope, for faster interstellar travel in the event of an earthly disaster is a wormhole like that in Interstellar, or some other extreme form of space-time warp. 4. The wormhole. 14. Wormholes. How wormholes got their name. Status of science: truth. My mentor, John Wheeler, gave astrophysical wormholes their name. He based it on wormholes in apples. For an ant walking on an apple, the apple's surface is the entire universe. If the apple is threaded by a wormhole, the ant has two ways to get from the top to the bottom: around the outside, through the ant's universe, or down the wormhole. The wormhole route is shorter. It's a shortcut from one side of the ant's universe to the other. The apple's delicious interior, through which the wormhole passes, is not part of the ant's universe. It is a three-dimensional bulk, or hyperspace. The wormhole's wall can be thought of as part of the ant's universe. It has the same dimensionality as the universe, 2 dimensions, and it joins onto the universe, the apple's surface, at the wormhole's entrance. From another viewpoint, the wormhole's wall is not part of the ant's universe. It is just a shortcut by which the ant can travel across the bulk, from one point in its universe to another. Flom's wormhole. Status of science: truth. In 1916, just 1 year after Einstein formulated his general relativistic laws of physics, Ludwig Flom in Vienna discovered a solution of Einstein's equations that describes a wormhole, though he did not call it that. We now know that Einstein's equations allow many kinds of wormholes with many different shapes and behaviors. But Flom's is the only one that is precisely spherical and contains no gravitating matter. When we take an equatorial slice through Flom's wormhole, so it and our universe, our brain, have just 2 dimensions rather than 3, and when we then view our universe and the wormhole from the bulk, They look like the left part of figure 32 in your PDF companion. With one of our universe's dimensions lost from the picture, you must think of yourself as a two-dimensional creature confined to move on the bent sheet or on the wormhole's two-dimensional wall. There are two routes for travel from location A, in our universe, to location B. The short route, dashed blue curve in figure 32, down the wormhole's wall, or the long route, dashed red curve, along the bent sheet, our universe. Of course, our universe is really three-dimensional. The concentric circles in the left part of figure 32 are really the nested green spheres shown in the right part of the figure. As you enter the wormhole along the blue path from location A, you pass through spheres that get smaller and smaller. Then the spheres, though nested inside each other, cease changing circumference. And then, as you exit the wormhole toward location B, the spheres get larger and larger. For 19 years, physicists paid little attention to Flam's outrageous solution of Einstein's equations, his wormhole. Then, in 1935, Einstein himself and fellow physicist Nathan Rosen, unaware of Flam's work, rediscovered Flam's solution, explored its properties, and speculated about its significance in the real world. Other physicists, also unaware of Flam's work, began to call his wormhole the Einstein-Rosen bridge. Wormhole collapse. Status of science: truth. It is often difficult to extract, from the mathematics of Einstein's equations, a full understanding of their predictions. Flam's wormhole is a remarkable example. From 1916 until 1962, nearly a half-century, physicists thought that the wormhole is static, forever unchanging. Then John Wheeler and his student Robert Fuller discovered otherwise. Looking much more closely at the mathematics, they discovered that the wormhole is born, expands, contracts, and dies, as shown in figure 33 in your PDF companion. If we examine figure 33, initially, in picture A, our universe has two singularities. As time passes, the singularities reach out to each other through the bulk and meet to create the wormhole, B. The wormhole expands in circumference, C and D, then shrinks and pinches off, E, leaving behind the two singularities, F. The birth, expansion, shrinkage, and pinch-off happen so quickly that nothing, not even light, has time to travel through the wormhole from one side to the other. Anything or anyone that attempts the trip will get destroyed in the pinch-off. This prediction is inescapable. If the universe were ever somehow to develop a spherical wormhole that contains no gravitating matter, this is how the wormhole would behave. Einstein's relativistic laws dictate it. Wheeler was not dismayed by this conclusion. On the contrary, he was pleased. He regarded singularities, places where space and time are infinitely warped, as a crisis for the laws of physics. And crises are wonderful tutors. By probing wisely, we can get great insights into the physical laws. To this I return in Chapter 26. Contact. Status of science: truth. Fast forward a quarter century, to May 1985. A phone call from Carl Sagan asking me to critique the relativistic science in his forthcoming novel, Contact. I happily agreed. We were close friends. I thought it would be fun, and besides, I still owed him one for introducing me to Linda Obst. Carl sent me his manuscript. I read it, and I loved it. But there was one problem. He sent his heroine, Dr. Eleanor Arroway, through a black hole from our solar system to the star Vega. But I knew that a black hole interior cannot be a route from here to Vega or to anywhere else in our universe. After plunging through the black hole's horizon, Dr. Arroway would get killed by its singularity. To reach Vega fast, she needed a wormhole, not a black hole. But a wormhole that does not pinch off, a traversable wormhole. So I asked myself, what do I have to do to Flam's wormhole to save it from pinching off, to hold it open so it can be traversed? A simple thought experiment gave me the answer. Suppose you have a wormhole that is spherical, like Flam's, but unlike Flam's, it does not pinch off. Send a light beam into the wormhole radially. Since all the beam's light rays travel radially, the beam must have the shape shown in Figure 34 in the PDF companion to this audiobook. It is converging. Its cross-sectional area is decreasing as it enters the wormhole, and it is diverging, its area is increasing, as it leaves the wormhole. The wormhole has bent the light rays outward, as would a diverging lens. Now, gravitating bodies, such as the sun or a black hole, bend rays inward. They can't bend rays outward. To bend light rays outward, a body must have negative mass, or equivalently, negative energy. Recall Einstein's equivalence of mass and energy. From this fundamental fact, I concluded that any traversable spherical wormhole must be threaded by some sort of material that has negative energy. At least the material's energy must be negative as seen by the light beam, or by anything or anyone else that travels through the wormhole at nearly the speed of light. I call such material exotic matter. I later learned that, according to Einstein's relativistic laws, any wormhole, spherical or not, is traversable only if it is threaded by exotic matter. This follows from a theorem proved in 1975 by Dennis Gannon at the University of California at Davis. Being somewhat illiterate, I was unaware of Gannon's theorem. Now, it is an amazing fact that exotic matter can exist thanks to weirdnesses in the laws of quantum physics. Exotic matter has even been made in physicists' laboratories in tiny amounts between two closely spaced electrically conducting plates. This is called the Casimir effect. However, it was very unclear to me in 1985 whether a wormhole can contain enough exotic matter to hold it open. So I did two things. First, I wrote a letter to my friend Carl suggesting that he send Eleanor Arroway to Vega through a wormhole rather than a black hole, and I enclosed a copy of the calculations by which I had shown that the wormhole must be threaded by exotic matter. Carl embraced my suggestion and wrote about my equations in the acknowledgement of his novel, and that is how wormholes entered modern science fiction, novels, films, and television. Second, with two of my students, Mark Morris and Ulvi Yurtsever, I published 2 technical articles about traversable wormholes. In our articles, we challenged our physicist colleagues to figure out whether the combined quantum laws and relativistic laws permit a very advanced civilization to collect enough exotic matter inside a wormhole to hold it open. This triggered a lot of research by a lot of physicists. But today, nearly 30 years later, the answer is still unknown. The preponderance of the evidence suggests that the answer may be no, so traversable wormholes are impossible. But we are still far from a final answer. For details, check out Time Travel and Warp Drives by my physicist colleagues Alan Everett and Thomas Roman. What does a traversable wormhole look like? Status of science, educated guess. What does a traversable wormhole look like to people like us who live in our universe? I can't answer definitively. If a wormhole can be held open, the precise details of how remain a mystery, so the precise details of the wormhole's shape are unknown. For black holes, by contrast, Roy Kerr has given us the precise details, so I can make the firm predictions described in Chapter 8. So for wormholes, I can make only an educated guess, but one in which I have considerable confidence, hence this section's designation as educated guess. Imagine we have a wormhole here on Earth, stretching through the bulk from Grafton Street in Dublin, Ireland, to the desert in Southern California. The distance through the wormhole might be only a few meters. The entrances to the wormhole are called mouths. You are sitting in a sidewalk cafe alongside the Dublin mouth. I am standing in the desert beside the California mouth. Both mouths look rather like crystal balls. When I look into my California mouth, I see a distorted image of Grafton Street, Dublin. That image is brought to me by light that travels through the wormhole from Dublin to California, rather like light traveling through an optical fiber. When you look into your Dublin mouth, you see a distorted image of Joshua trees, cactus trees, in the California desert. Can wormholes exist naturally as astrophysical objects? Status of science, speculation. In Interstellar, Cooper says, "A wormhole isn't a naturally occurring phenomenon." I agree with him completely. If traversable wormholes are allowed by the laws of physics, I think it extremely unlikely they can exist naturally in the real universe. I must confess, though, that this is little more than a speculation, not even an educated guess. Maybe a highly educated speculation, but speculation nonetheless, so I labeled this section as such. Why am I so pessimistic about natural wormholes? We see no objects in our universe that could become wormholes as they age. By contrast, astronomers see huge numbers of massive stars that will collapse to form black holes when they have exhausted their nuclear fuel. On the other hand, there is reason to hope that wormholes do exist naturally on sub-microscopic scales in the form of quantum foam. This foam is a hypothesized network of wormholes that is continually fluctuating in and out of existence in a manner governed by the ill-understood laws of quantum gravity. The foam is probabilistic in the sense that at any moment there is a certain probability the foam has one form and also a probability that it has another form, and these probabilities are continually changing. And the foam is truly tiny. The typical length of a wormhole would be the so-called Planck length, 0.0000000000000000000000000001 centimeters. 1/100th of a billionth of a billionth the size of the nucleus of an atom. That's small. Back in the 1950s, John Wheeler gave persuasive arguments for quantum foam, but there is now evidence that the laws of quantum gravity might suppress the foam and might even prevent it from arising. If quantum foam does exist, I hope there is a natural process by which some of its wormholes can spontaneously grow to human size or bigger, and even did so during the extremely rapid inflationary expansion of the universe, when the universe was very, very young. However, we physicists have no hint of any evidence at all that such natural enlargement can or did occur. The other tiny hope for natural wormholes is the Big Bang creation of the universe. It is conceivable, but very unlikely, that traversable wormholes could have formed in the Big Bang itself. Conceivable for the simple reason that we don't understand the Big Bang well at all. Unlikely because nothing we do know about the Big Bang gives any hint that traversable wormholes might form there. Can wormholes be created by an ultra-advanced civilization? Status of science, speculation. An ultra-advanced civilization is my only serious hope for making traversable wormholes, but it would face huge obstacles, so I'm pessimistic. One way to make a wormhole, where previously there were none, is to extract it from the quantum foam, if the foam exists, enlarge it to human size or larger, and thread it with exotic matter to hold it open. This seems like a pretty tall order, even for an ultra-advanced civilization, but perhaps only because we don't understand the quantum gravity laws that control the foam, the extraction, and the earliest stages of enlargement. Of course, we don't understand exotic matter very well either. At first sight, making a wormhole seems easy. Just push a piece of our brain, our universe, downward in the bulk to create a thimble, fold our brain around in the bulk, tear a hole in our brain just below the thimble, tear a hole in the thimble itself, and sew the tears together. Just. In Interstellar, Romilly demonstrates the same thing with a sheet of paper and a pencil. As easy as this may look from the outside, playing with pencils and paper, It is horrendously daunting when the sheet is our brain and these manipulations must be carried out from within the brain by a civilization that lives in our brain. In fact, I have no idea how to execute any of these maneuvers from inside our brain except the first, creating a thimble in our brain, which requires only a very dense mass, such as a neutron star. Moreover, if it is possible at all to tear holes in our brain, it can only be done with the help of the laws of quantum gravity. Einstein's relativistic laws forbid tearing our brain, so the only hope is to make the tear where his laws fail, in a realm of quantum gravity. We then are back to the domain of terra almost incognita. The bottom line. Status of science, speculation. I doubt the laws of physics permit traversable wormholes, but this may be pure prejudice. I could be wrong. If they can exist, I doubt very much that they can form naturally in the astrophysical universe. My only real hope for forming them is artificially, in the hands of an ultra-advanced civilization. But we are extremely ignorant of how such a civilization could do it. And it appears more than daunting, at least from inside our brain, our universe, even for the most advanced of civilizations. In Interstellar, however, the wormhole is thought to have been made, held open, and placed near Saturn by a civilization that lives in the bulk, a civilization whose beings have 4 space dimensions, like the bulk. This is terra extremely incognita. Nevertheless, I discuss bulk beings in Chapter 22. In the meantime, let's talk about the wormhole in Interstellar. 15. Visualizing Interstellar's wormhole. Status of science, speculation. The wormhole in Interstellar is thought to have been constructed by an ultra-advanced civilization, most likely one that lives in the bulk. In this spirit, when laying foundations for visualizing Interstellar's wormhole, Oliver James and I pretended we were ultra-advanced engineers. We assumed that wormholes are allowed by the laws of physics. We assumed the wormhole's builders had all the exotic matter they needed to hold the wormhole open. We assumed the builders could warp space and time in whatever way we wished them to, inside and around the wormhole. These are pretty extreme assumptions, so I labeled this chapter speculative. The wormhole's gravity and time warping. Christopher Nolan wanted the wormhole to have a mild gravitational pull, strong enough to hold the endurance in orbit around itself, but weak enough that a modest rocket blast would slow the endurance, letting it drop gently into the wormhole. This meant a gravitational pull much less than the Earth's. Einstein's law of time warps tells us that the slowing of time inside the wormhole is proportional to the strength of the wormhole's gravitational pull. With that pull weaker than the Earth's pull, the slowing of time must be smaller than on Earth, which is only a part in a billion, that is, 1 second of slowing during a billion seconds of time, 30 years. Such slowing is so tiny that Oliver and I paid no attention to it at all when designing the wormhole. Handles for adjusting the wormhole's shape. The ultimate decision about the wormhole's shape was in the hands of Christopher Nolan, the director, and Paul Franklin, the visual effects supervisor. My task was to give Oliver and his colleagues at Double Negative handles, or in technical language, parameters, that they could use to adjust the shape. They then simulated the wormhole's appearance for various adjustments of the handles and showed the simulations to Chris and Paul, who chose the one that was most compelling. I gave the wormhole's shape 3 handles, 3 ways to adjust the shape. The first handle is the wormhole's radius, as measured by an ultra-advanced engineer looking in from the bulk, analog of Gargantua's radius. If we multiply that radius by 2 pi, 6.28318, etc., we get the wormhole's circumference as measured by Cooper when he pilots the Endurance around or through it. Chris chose the radius before I began to work. He wanted the wormhole's gravitational lensing of stars to be barely visible from Earth with the best large telescope technology then available to NASA. That fixed the radius at about a kilometer. The second handle is the wormhole's length, as measured equally well by Cooper or by an engineer in the bulk. The third handle determines how strongly the wormhole lenses the light from objects behind it. The details of the lensing are fixed by the shape of space near the wormhole's mouths. I chose that shape similar to the shape of space outside the horizon of a non-spinning black hole. My chosen shape has just one adjustable handle, the width of the region that produces strong lensing. I call this the lensing width. How the handles influence the wormhole's appearance. Just as I had done for Gargantua, I used Einstein's relativistic laws to deduce equations for the paths of light rays around and through the wormhole, and I worked out a procedure for manipulating my equations to compute the wormhole's gravitational lensing, and thence what a camera sees when it orbits the wormhole or travels through it. After checking that my equations and procedure produced the kinds of images I expected, I sent them to Oliver, and he wrote computer code capable of creating the quality IMAX images needed for the movie. Eugenie von Tunzelmann added background star fields and images of astronomical objects for the wormhole to lens, and then she, Oliver, and Paul began exploring the influence of my handles. Independently, I did my own explorations. Eugenie kindly provided the pictures in figures 35 and 37, both available in your PDF companion for this book, in which we look at Saturn through the wormhole. The resolutions of her pictures are far higher than my own crude computer code can produce. The wormhole's length. We first explored the influence of the wormhole's length with modest lensing, small lensing width. See figure 35 in your PDF companion. When the wormhole is short, top picture in figure 35, the camera sees one distorted image of Saturn through the wormhole, the primary image, filling the right half of the wormhole's crystal ball-like mouth. There is an extremely thin secondary, lenticular image on the left edge of the crystal ball. The lenticular structure at the lower right is not Saturn. It is a distorted part of the external universe. As the wormhole is lengthened, middle picture in figure 35, the primary image shrinks and moves inward. The secondary image also moves inward, and a very thin lenticular tertiary image emerges from the right edge of the crystal ball. With further lengthening, bottom picture in figure 35, the primary image shrinks further. All the images move inward. A fourth image emerges from the left edge of the crystal ball, a fifth from the right, and so forth. These behaviors can be understood by drawing light rays on the wormhole as seen from the bulk. In figure 36 in your PDF companion, the primary image is carried by the black light ray, labeled 1 in the figure, which travels on the shortest possible path from Saturn to the camera, and by a bundle of rays tightly surrounding it. The secondary image is carried by a bundle surrounding the red ray, 2 in the figure, which travels around the wormhole's wall in the opposite direction to the black ray, counterclockwise. This red ray is the shortest possible counterclockwise ray from Saturn to the camera. The tertiary image is carried by a bundle surrounding the green ray, 3 in the figure, which is the shortest possible clockwise ray that makes more than one full trip around the wormhole. And the fourth image is carried by a bundle surrounding the brown ray, 4 in the figure, the shortest possible counterclockwise ray that makes more than one full trip around the wormhole. Can you explain the fifth and sixth images? And explain why the images shrink when the wormhole is lengthened? And explain why the images appear to emerge from the edge of the wormhole's crystal ball mouth and move inward. The wormhole's lensing width. Having understood how the wormhole's length affects what the camera sees, we then fixed the length to be fairly short, the same as the wormhole's radius, and varied the gravitational lensing. We increased the wormhole's lensing width from near 0 to about half the wormhole's diameter and computed what that did to the images the camera sees. Figure 37 in your PDF companion shows the two extremes. With very small lensing width, the wormhole shape, upper left in Figure 37, has a sharp transition from the external universe, horizontal sheets, to the wormhole throat, vertical cylinder. As seen by the camera, upper right in Figure 37, the wormhole distorts the star field and a dark cloud in the upper left only slightly, near the wormhole's edge. Otherwise, it simply masks the star field out, as would any opaque body with weak gravity, for example, a planet or a spacecraft. In the lower half of Figure 37, the lensing width is about half the wormhole's radius, so there is a slow transition from the throat, vertical cylinder, to the external universe, asymptotically horizontal sheet. With this large lensing width, the wormhole strongly distorts the star field and dark cloud, lower right in Figure 36 in your PDF companion, in nearly the same way as does a non-spinning black hole, producing multiple images, and the lensing also enlarges the secondary and tertiary images of Saturn. The wormhole looks bigger in the lower half of Figure 36 than in the upper half. It subtends a larger angle as seen by the camera. This is not because the camera is closer to the mouth. It is not closer. The camera is the same distance in both pictures. The enlargement is entirely due to the gravitational lensing. Interstellar's wormhole. When Chris saw the various possibilities, with varying wormhole length and lensing width, his choice was unequivocal. For medium and large length, the multiple images seen through the wormhole would be confusing to a mass audience, so he made Interstellar's wormhole very short, 1% of the wormhole radius. And he gave Interstellar's wormhole a modest lensing width, about 5% of the wormhole radius, so the lensing of stars around it would be noticeable and intriguing, but much smaller than Gargantua's lensing. The resulting wormhole is the one at the top of Figure 35 in your PDF companion. And in Interstellar, after the double negative team had created for its far side a galaxy with beautiful nebulae, dust lanes, and star fields, it is marvelous to behold. To me, it is one of the movie's grandest sights. The trip through the wormhole. On April 10, 2014, I got an urgent phone call. Chris was having trouble with visualizing the Endurance's trip through the wormhole, and he wanted advice. I drove over to his Syncope compound, where post-production editing was underway, and Chris showed me the problem. Using my equations, Paul's team had produced visualizations for wormhole trips with various wormhole lengths and lensing widths. For the short, modest lensing wormhole depicted in the movie, the trip was quick and uninteresting. For a long wormhole, it looked like traveling through a long tunnel with walls whizzing past, too much like things we've seen in movies before. Chris showed me many variants with many bells and whistles, and I had to agree that none had the compelling freshness that he wanted. After sleeping on it, I still had no magic bullet solution. The next day, Chris flew to London and closeted himself with Paul's double negative team, searching for a solution. In the end, they were forced to abandon my wormhole equations and, in Paul's words, go for a much more abstract interpretation of the wormhole's interior, an interpretation informed by simulations with my equations, but altered significantly to add artistic freshness. When I experienced the wormhole trip in an early screening of Interstellar, I was pleased. Though not fully accurate, it captures the spirit and much of the feel of a real wormhole trip, and it's fresh and compelling. What did you think? 16. Discovering the wormhole. Gravitational waves. Status of science? Truth. How might humans have discovered Interstellar's wormhole? As a physicist, I have a favorite way. I describe it here in an extrapolation of Interstellar's story, an extrapolation that, of course, is my own and not Christopher Nolan's. LIGO detects a burst of gravitational waves. I imagine that decades before the movie begins, when Professor Brand was in his 20s, he was deputy director of a project called LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO was searching for ripples in the shape of space arriving at Earth from the distant universe. These ripples, called gravitational waves, are produced when black holes collide with each other, when a black hole tears a neutron star apart, when the universe was born, and in many other ways. One day, in 2019, LIGO was hit by a burst of gravitational waves far stronger than any ever before seen. The waves oscillated with an amplitude that grew and fell several times, and then cut off suddenly. The entire burst lasted for only a few seconds. By comparing the waves' shape, their waveform, with simulations performed on supercomputers, Professor Brand and his team deduced their source. Neutron star orbiting a black hole. A neutron star orbiting around a black hole had emitted the waves. The star weighed 1.5 times as much as the Sun, the hole weighed 4.5 times the Sun, and the hole was spinning rapidly. The spin dragged space into motion, and the space whirl grabbed the star's orbit, forcing it to precess slowly, like a tilted top. The precession modulated the waves, causing them to rise and fall in amplitude. The waves traveled out through the universe, carrying away energy. With its energy gradually decreasing, the star gradually spiraled inward toward the black hole. When the distance between the star and the hole had shrunk to 30 kilometers, the hole's tidal gravity began tearing the star apart. 97% of the stellar debris was swallowed by the black hole, and 3% was thrown outward, forming a tail of hot gas that the hole then sucked back inward to form an accretion disk. Figure 38 in your PDF companion shows a computer simulation of the last few milliseconds of the star's life. At 10 milliseconds before the end of the star's life, the black hole is spinning around the red arrowed axis, and the star is orbiting around the picture's vertical axis. At 4 milliseconds, the hole's Tendex lines are stretching the star apart. At 2 milliseconds, the hole's whirling space has thrown the stellar debris up into the hole's equatorial plane. At 0 milliseconds, the debris is beginning to form an accretion disk. Discovering the wormhole. Looking back through LIGO's data for the preceding 2 years, Professor Brand and his team discovered very weak waves emitted by the neutron star. The star had a tiny mountain, a centimeter high and a few kilometers wide. Such mountains are thought likely. As the mountain was carried around and around by the star's rotation, it produced waves that oscillated weakly but steadily, day after day after day. By analyzing these steady waves with care, Professor Brand learned the direction to their source. The direction was unbelievable. The waves were coming from something in orbit around Saturn. As the Earth and Saturn moved in their orbits, the source was always near Saturn. A neutron star orbiting Saturn? Impossible. A black hole accompanying the neutron star, with both orbiting Saturn? Even more impossible. Saturn would long ago have been destroyed, and the star's and hole's gravity would long ago have disrupted the orbits of all of the Sun's planets, including Earth. With disrupted orbit, the Earth would have been carried close to the Sun and then far away. We would have been fried, frozen, and killed. But there the waves were, unequivocally emerging from near Saturn. Professor Brand could find only one explanation. The waves must emerge from a wormhole that orbits Saturn, and their source, the black hole and neutron star, must be on the other end of the wormhole. The waves traveled outward from the star and hole. Small portions of the waves were captured by the wormhole, traveled through it, and then spread outward through the solar system with a small portion reaching Earth and passing through the LIGO gravitational wave detector. Origin of this story. A brief variant of this story was in the original 2006 treatment for Interstellar that Linda Obst and I wrote. However, gravitational waves did not play a significant role in the rest of our treatment, nor in the subsequent screenplay that Jonathan Nolan wrote and Chris rewrote. And even without gravitational waves, the amount of serious science in the movie was enormous, So, when Chris sought ways to simplify Interstellar's rich panoply of science, gravitational waves were a natural candidate for the axe. He jettisoned them. For me personally, Chris's decision was painful. I co-founded the LIGO project in 1983, together with Rainer Weiss at MIT and Ronald Drever at Caltech. I formulated LIGO's scientific vision, and I spent 2 decades working hard to help make it a reality. And LIGO today is nearing maturity, with the first detection of gravitational waves expected in this decade. But Chris's reasons to jettison gravitational waves were compelling, so I didn't utter even a whisper of protest. Gravitational waves and their detectors. I'll indulge myself and tell you a bit more about gravitational waves before moving back to Interstellar. Figure 39 in your PDF companion is an artist's conception of some Tendex lines emerging from 2 black holes that orbit each other counterclockwise and collide. Recall that Tendex lines produce tidal gravity. The lines emerging from the hole's ends stretch everything they encounter, including the artist's friend, whom she has placed there. The lines emerging from the collision region squeeze everything they encounter. As the holes orbit around each other, they drag their Tendex lines around, splaying outward and backward, like water from a whirling sprinkler. The holes merge to form a single, larger black hole that is deformed and spinning counterclockwise, and that drags its Tendex lines around and around. The Tendex lines travel outward, like water from the sprinkler, creating the intricate pattern that I show in Figure 40 in your PDF companion. The red lines stretch, the blue lines squeeze. A person at rest, far from the hole, experiences an oscillating stretch, then squeeze, then stretch, as the Tendex lines travel outward through her. The Tendex lines have become a gravitational wave. As you see in Figure 40, wherever the lines in the plane of the picture are strongly blue, strongly squeezing, there are strongly red lines coming out of the picture that stretch. And wherever the lines in the picture are strongly red, stretching, there are blue, squeezing lines pointing in the third direction out of the picture. As the waves flow outward, the hole's deformation gradually grows weaker and the waves weaken. When these waves reach Earth, they have the form that I show in the upper part of Figure 41 in your PDF companion. They stretch along one direction and squeeze along the other. The stretch and squeeze oscillate from red right-left to blue right-left to red right-left, etc., as the waves pass through the detector in the bottom part of Figure 41. The detector consists of 4 huge mirrors, 40 kilograms, 34 centimeters in diameter, that hang from overhead supports at the ends of 2 perpendicular arms. The wave's Tendex lines stretch one arm while squeezing the other, and then squeeze the first while stretching the second, over and over and over again. The oscillating separation between mirrors is monitored with laser beams by a technique called interferometry. Hence LIGO's name, Laser Interferometer Gravitational Wave Observatory. LIGO is now an international collaboration of 900 scientists in 17 nations, headquartered at Caltech. It is currently led by David Reitze, Director, Albert Lazzarini, Deputy Director, and Gabriela Gonzalez, spokesperson for the collaboration. And in view of its huge potential payoffs for our understanding of the universe, it is funded primarily by U.S. taxpayers through the National Science Foundation. LIGO has gravitational wave detectors in Hanford, Washington, and Livingston, Louisiana, and is planning to place a third in India. Scientists in Italy, France, and the Netherlands have built a similar interferometer near Pisa, and Japanese physicists are building one in a tunnel under a mountain. These detectors will all operate together, forming a giant worldwide network to explore the universe using gravitational waves. Having trained many scientists who work on LIGO, in 2000 I turned my own research in other directions. But I watch eagerly as LIGO and its international partners near maturity and near their first detections of gravitational waves. The warped side of the universe. Interstellar is an adventure in which humans encounter black holes, wormholes, singularities, gravitational anomalies, and higher dimensions. All these phenomena are made from warped space and time, or are tied intimately to that warping. This is why I like to call them the warped side of the universe. We humans, as yet, have very little experimental or observational data from the universe's warped side. That's why gravitational waves are important. They are made from warped space, and so they are the ideal tool for probing the warped side. Suppose you had only seen the ocean on a very calm day. You would know nothing of the heaving seas and breaking ocean waves that come with a huge storm. That is similar to our knowledge, today, of warped space and time. We know little about how warped space and warped time behave in a storm, when the shape of space is oscillating wildly and the rate of flow of time is oscillating wildly. For me, this is a fascinating frontier of knowledge. John Wheeler, the creative coiner we met in earlier chapters, dubbed this geometrodynamics, the wildly dynamical behavior of the geometry of space and time. In the early 1960s, when I was Wheeler's student, he exhorted me and others to explore geometrodynamics in our research. We tried and failed miserably. We didn't know how to solve Einstein's equations well enough to learn their predictions, and we had no way to observe geometrodynamics in the astronomical universe. I've devoted much of my career to changing this. I co-founded LIGO with the goal of observing geometrodynamics in the distant universe. In 2000, when I turned my LIGO roles over to others, I co-founded a research group at Caltech aimed at simulating geometrodynamics on supercomputers by solving Einstein's relativistic equations numerically. We call this project SXS, Simulating Extreme Spacetimes. It is a collaboration with Saul Tucholsky's research group at Cornell University and others. A wonderful venue for geometrodynamics is the collision of two black holes. When they collide, the holes set space and time into wild gyrations. Our SXS simulations have now reached maturity and are beginning to reveal relativity's predictions. LIGO and its partners will observe the gravitational waves from colliding black holes within the next few years and test our simulations' predictions. It's a wonderful era for probing geometrodynamics. Gravitational waves from the Big Bang. In 1975, Leonid Grishchuk, a dear Russian friend of mine, made a startling prediction. A rich plethora of gravitational waves was produced in the Big Bang, he predicted, by a previously unknown mechanism. Quantum fluctuations of gravity coming off the Big Bang were amplified enormously, he told us, by the universe's initial expansion, and when amplified, they became primordial gravitational waves. If discovered, these gravitational waves could bring us a glimpse of our universe's birth. In subsequent years, as our understanding of the Big Bang matured, it became evident that the waves would be strongest at wavelengths nearly as large as the visible universe itself, billions of light-years wavelength, and would likely be too weak for detection at LIGO's far shorter wavelengths, hundreds and thousands of kilometers. In the early 1990s, several cosmologists realized that these billion light-years-long gravitational waves should have placed a unique imprint on electromagnetic waves that fill the universe, the so-called cosmic microwave background, or CMB. A holy grail quickly emerged. Search for that CMB imprint. From it, infer the properties of the primordial gravitational waves that produced the imprint, and thereby explore the birth of the universe. In March 2014, while I was writing this book, the CMB imprint was discovered by a team assembled by Jamie Bach, a cosmologist down the hall from me at Caltech. It was a fantastic discovery, but with a cautionary note. The imprint that Jamie and his team found might possibly be due to something else and not gravitational waves. At this moment, intense efforts are underway to find out for sure. If the imprint is really due to gravitational waves from the Big Bang, then this is the type of cosmological discovery that comes along perhaps once every 50 years. It brings us a glimpse of the universe a trillionth of a trillionth of a trillionth of a second after the universe's birth. It confirms theorists' prediction that the expansion of the universe at that early moment was exceedingly fast, inflationarily fast in cosmologists' jargon. It ushers in a whole new era for cosmology. Having indulged my passion for gravitational waves, having seen how they could be used to discover Interstellar's wormhole, and having explored the properties of wormholes, especially interstellars, I now take you on a tour of the other side of the interstellar wormhole, a tour of Miller's planet, man's planet, and the Endurance, which carries Cooper there. 5. Exploring Gargantua's environs. 17. Miller's planet. Status of science: truth. The first planet that Cooper and his crew visit is Miller's. The most impressive things about this planet are the extreme slowing of time there, gigantic water waves, and huge tidal gravity. All three are related and arise from the planet's closeness to Gargantua. The planet's orbit. In my interpretation of Interstellar's science, Miller's planet is at the blue location in Figure 42 in your PDF companion, very close to Gargantua's horizon. Space there is warped, like the surface of a cylinder. In the figure, the cylinder's cross-sections are circles whose circumferences don't change as we move nearer to or farther from Gargantua. In reality, when we restore the missing dimension, the cross-sections are spheroids, whose circumferences don't change as we move nearer or farther. So why is this location different from any other on the cylinder? What makes this location special? The key to the answer is the warping of time, which does not show up in Figure 42. Time slows near Gargantua, and the slowing becomes more extreme as we get closer and closer to Gargantua's event horizon. Therefore, according to Einstein's law of time warps, gravity becomes ultra-strong as we near the horizon. The red curve in Figure 43 in your PDF companion, which depicts the strength of the gravitational force, turns sharply upward. By contrast, the centrifugal force that the planet feels, the blue curve, has a more gradually changing slope. As a result, the two curves cross at two locations. There, the planet can travel around Gargantua with the outward centrifugal force balancing the inward gravitational force. At the inner balance point, the planet's orbit is unstable. If the planet gets pushed outward a tiny bit, for example by the gravity of some passing comet, the centrifugal force wins the competition and pushes the planet further outward. If the planet is pushed inward, the gravitational force wins and the planet is pulled into Gargantua. This means Miller's planet can't live for long at the inner balance point. The outer balance point, by contrast, is stable. If Miller's planet is there and gets pushed outward, gravity wins the competition and pulls the planet back in. If the planet gets pushed inward, centrifugal forces win and push it back out. So this is where Miller's planet lives in my interpretation of Interstellar. The slowing of time and tidal gravity. Among all stable, circular orbits around Gargantua, the orbit of Miller's planet is the closest to the black hole. This means it's the orbit with the maximum slowing of time. 7 years on Earth is 1 hour on Miller's planet. Time flows 60,000 times more slowly there than on Earth. This is what Christopher Nolan wanted for his movie. But being so close to Gargantua, in my interpretation of the movie, Miller's planet is subjected to enormous tidal gravity. So enormous that Gargantua's tidal forces almost tear the planet apart. Almost, but not quite. Instead, they simply deform the planet. Deform it greatly. It bulges strongly toward and away from Gargantua. If Miller's planet were to rotate relative to Gargantua, if it didn't keep the same face toward Gargantua at all times, then as seen by the planet, the tidal forces would rotate. First, the planet would be crushed east-west and stretched north-south. Then, after a quarter rotation, the crush would be north-south and the stretch east-west. These crushes and stretches would be enormous compared to the strength of the planet's mantle, its solid outer layers. The mantle would be pulverized, and then friction would heat it and melt it, making the whole planet red hot. That's not at all what Miller's planet looks like. So the conclusion is clear. In my science interpretation, the planet must always keep the same face pointing toward Gargantua, or nearly so, as I discuss later. The whirl of space. Einstein's laws dictate that, as seen from afar, for example from man's planet, Miller's planet travels around Gargantua's billion-kilometer circumference orbit once each 1.7 hours. This is roughly half the speed of light. Because of time's slowing, the Ranger's crew measure an orbital period 60,000 times smaller than this, a tenth of a second. 10 trips around Gargantua per second. That's really fast. Isn't it far faster than light? No, because of the space whirl induced by Gargantua's fast spin. Relative to the whirling space at the planet's location, and using time as measured there, the planet is moving slower than light, and that's what counts. That's the sense in which the speed limit is enforced. In my science interpretation of the movie, since the planet always keeps the same face pointed toward Gargantua, it must spin at the same rate as it orbits, 10 revolutions per second. How can it possibly spin so fast? Won't centrifugal forces tear it apart? No, and again the savior is the whirl of space. The planet would feel no disruptive centrifugal forces if it were spinning at precisely the same rate as space near it whirls, which it is almost doing. So centrifugal forces due to its rotation, in fact, are weak. If, instead, it were non-spinning relative to the distant stars, it would turn at 10 revolutions per second relative to whirling space, and so would be torn apart by centrifugal forces. It's weird what relativity can do. Giant waves on Miller's planet. What could possibly produce the two gigantic water waves, 1.2 kilometers high, that bear down on the Ranger as it rests on Miller's planet? I searched for a while, did various calculations with the laws of physics, and found two possible answers for my science interpretation of the movie. Both answers require that the planet be not quite locked to Gargantua. Instead, it must rock back and forth relative to Gargantua by a small amount, from the orientation on the left of figure 44 in your PDF companion to that on the right, then back to the left, and so on. This rocking is a natural thing, as you can see by looking at Gargantua's tidal gravity. In figure 44, I described the tidal gravity by Tendex lines. No matter which way the planet is tilted, left or right in figure 44, Gargantua's blue squeezing Tendex lines push its sides in, which drives the planet back toward its preferred orientation, the one with its bulges nearest Gargantua and farthest away. Similarly, Gargantua's red stretching Tendex lines pull its bottom bulge toward Gargantua and push its top bulge away from Gargantua. This also drives the planet back toward its preferred orientation. The result is a simple rocking of the planet, back and forth. If the tilts are small enough that the planet's mantle isn't pulverized. When I computed the period of this rocking, how long it takes to swing from left to right and back again, I got a joyous answer. About an hour. The same as the observed time between giant waves, a time chosen by Chris without knowing about my science interpretation. The first explanation for the giant waves, in my science interpretation, is a sloshing of the planet's oceans as the planet rocks under the influence of Gargantua's tidal gravity. A similar sloshing, called tidal bores, happens on Earth, on nearly flat rivers that empty into the sea. When the ocean tide rises, a wall of water can go rushing up the river, usually a tiny wall, but very occasionally respectably big. such as with the tidal bore on the Changtang River in Hangzhou, China, in August 2010. Though impressive, this tidal bore was very small compared to the 1.2-kilometer high waves on Miller's planet. But the Moon's tidal gravity that drove this tidal bore is tiny, really tiny, compared to Gargantua's huge tidal gravity. My second explanation is tsunamis. As Miller's planet rocks, Gargantua's tidal forces may not pulverize its crust, but they do deform the crust first this way and then that, once an hour, and those deformations could easily produce gigantic earthquakes, or Millerquakes, I suppose we should call them, and those Millerquakes could generate tsunamis on the planet's oceans, far larger than any tsunami ever seen on Earth, such as the one that hit Miyako City, Japan, on March 11, 2011. Past history of Miller's planet. It is interesting to speculate about the past and future history of Miller's planet. Try it using as much physics as you know or can scrounge up from the web or elsewhere. This is not easy. Here are some things you might think about. How old is Miller's planet? If, as an extreme hypothesis, it was born in its present orbit when its galaxy was very young, about 12 billion years ago, and Gargantua has had its same ultra-fast spin ever since, then the planet's age is about 12 billion years divided by 60,000, the slowing of time on the planet. 200,000 years. This is awfully young compared to most geological processes on Earth. Could Miller's planet be that young and look like it looks? Could the planet develop its oceans and oxygen-rich atmosphere that quickly? If not, how could the planet have formed elsewhere and gotten moved to this orbit, so close to Gargantua? How long can the planet's rocking continue until friction inside the planet converts all the rocking energy to heat? And how long could it have rocked in the past? If a lot shorter than 200,000 years, then perhaps something set it rocking. What could have done so? When friction converts rocking energy to heat, how hot does the planet's interior get? Hot enough to trigger volcanoes and lava flows? Jupiter's moon Io is a remarkable example of this. Io, the large moon that orbits closest to Jupiter's surface, doesn't rock. But it does move closer and farther from Jupiter along an elliptical orbit, so it feels Jupiter's tidal gravity strengthen, then weaken, then strengthen, much like Miller's planet feels Gargantua's tidal gravity oscillate. This heats Io enough to produce huge volcanoes and lava flows. The appearance of Gargantua from Miller's planet. In Interstellar, as the Ranger approaches Miller's planet, carrying Cooper and his crew, we see Gargantua in the sky above, 10 degrees across, 20 times larger than the Moon as seen from Earth, and surrounded by its bright accretion disk. As startlingly impressive as this may be, Gargantua's angular size has actually been reduced greatly from what it would really be at the location of Miller's planet. If Miller's planet is indeed close enough to Gargantua to experience extreme time slowing, as I chose for my interpretation of the movie, then it must be deep into the cylindrical region of Gargantua's warped space, as depicted in Figure 42 in your PDF companion. It seems likely, then, that if you look down the cylinder from Miller's planet, you will see Gargantua, and if you look up the cylinder, you will see the external universe. So Gargantua should encompass roughly half of the sky, 180 degrees, around the planet, and the universe the other half. Indeed, that is what Einstein's relativistic laws predict. It also seems clear that, since Miller's planet is the closest anything can live stably without falling into Gargantua, the entire accretion disk should be outside the orbit of Miller's planet. Therefore, as the crew approach the planet, they should see a giant disk above them and a giant black hole shadow below. Again, that is what Einstein's laws predict. If Chris had followed these dictates of Einstein's laws, it would have spoiled his movie. To see such fantastic sights so early in the movie would make the movie's climax, when Cooper falls into Gargantua, visually anticlimactic. So Chris consciously saved such sites for the end of the movie, and invoking artistic license, near Miller's planet, he depicted Gargantua and its disk together, just 20 times bigger than the moon looks from Earth. Although I'm a scientist and aspire to science accuracy in science fiction, I can't blame Chris at all. I would have done the same had I been making the decision, and you'd have thanked me for it. 18. Gargantua's vibrations. Status of science? Truth. While Cooper and Amelia Brand are on Miller's planet, Romilly stays behind in the Endurance, observing Gargantua. From exquisitely accurate observations, he hopes to learn more about gravitational anomalies. Above all, I presume, he hopes that quantum data from Gargantua's singularity will leak out through the event horizon, bringing information about how to control the gravitational anomalies. Or, in Romilly's pithy language, bringing information for solving gravity. When Amelia Brand returns from Miller's planet, Romilly tells her, "I learned what I could from studying the black hole, but I couldn't send anything to your father. We've been receiving, but nothing gets out." What did Romilly observe? He's not specific, but I presume he would focus on Gargantua's vibrations, and I offer this chapter's extrapolation of the movie for that. Vibrations of black holes. In 1971, Bill Press, a student of mine at Caltech, discovered that black holes can vibrate at special, resonant frequencies, in much the same way as a violin string vibrates. When a violin string is plucked just right, it emits a very pure tone, sound waves with a single frequency. When plucked a little differently, it emits that pure tone and also higher harmonics of the pure tone. In other words, if the string is firmly clamped, with the clamping finger not moving around, its vibrations produce sound at only a discrete set of frequencies, the string's resonant frequencies. The same is true of a wine glass whose rim you rub with your finger, and a bell struck by a hammer, and also a black hole disturbed by something falling into it, Press discovered. A year later, Saul Tucholsky, another of my students, used Einstein's relativistic laws to work out a mathematical description of these resonant vibrations for a spinning black hole. That's the best thing about teaching at Caltech. We get fabulous students. By solving Tucholsky's equations, we physicists can compute a black hole's resonant frequencies. But solving them for an extremely fast spinning hole, like Gargantua, is very difficult. So difficult that it was not done successfully until 40 years later, by a collaboration in which the lead players again were two Caltech students, Huan Yang and Aaron Zimmerman. In September 2013, Richie Kramer, the property master for Interstellar, the person in charge of props, asked me for observational data that Romilly could show to Brand. Of course, I turned to the world's best experts for help, Yang and Zimmerman. They quickly produced tables of Gargantua's resonant vibration frequencies, and also of the rates that the vibrations die out by feeding energy into gravitational waves. Tables based on their own calculations using Tucholsky's equations. Then they added fake observational numbers to go along with the theoretical predictions, and I added pictures of Gargantua's event horizon, or rather the edge of its shadow. Pictures from simulations by the Interstellar visual effects team at Double Negative. The result was Romilly's observational data set. When Christopher Nolan filmed the scene where Romilly discusses his observations with Amelia Brand, Romilly wound up not actually showing her his data set. It was there on a table, but he didn't pick it up. However, the data set is central to my science extrapolation of Interstellar. Gargantua's resonant vibrations. Each line of data on the first page of Romilly's data set refers to a single resonant frequency at which Gargantua vibrates. The first column is a 3-number code for the shape of Gargantua's vibrations. The second column of data is the vibration frequency, and the third is the rate at which this vibration dies out, as predicted by Tucholsky's equations. The fourth and fifth columns show the difference between Romilly's observations and the theoretical predictions. In my extrapolation, Romilly finds a few anomalies, severe disagreements between his observations and the theory. On page 1 of the dataset, there is just one anomaly, but the disagreement is severe, 39 times larger than the uncertainty in his measurements. These anomalies might be helpful in solving gravity, learning how to harness the anomalies, Romilly thinks, in my extrapolation. He wishes he could transmit what he has learned to Professor Brand back on Earth, but the outbound communication link has been severed, so he's frustrated. Even more, he wishes he could see inside Gargantua to extract the crucial quantum data embedded in its singularity, but he can't. And he doesn't know whether the anomalies he observed are encoding some of the quantum data or not. Perhaps, with the hole spinning so rapidly, some of the quantum data leaked out through the horizon and produced the anomalies. Maybe Professor Brand could figure that out if only Romilly could transmit the data to him. I say a lot more later about gravitational anomalies and quantum data from inside Gargantua as the key to harnessing the anomalies. But that's later. For now, let's continue our exploration of Gargantua's environs, turning next to man's planet. 19. Man's planet. Status of science: truth. After discovering that Miller's planet is hopeless for human colonization, Cooper and his crew travel to man's planet. The planet's orbit and lack of sun. I have deduced a plausible orbit for man's planet from two things in Interstellar. First, Doyle says the trip to man's planet will require months. From this, I infer that when the Endurance arrives at man's planet, it must be far from Gargantua's vicinity where the trip began. Second, almost immediately after the Endurance's explosive accident in orbit around man's planet, the crew find the Endurance being pulled toward Gargantua's horizon. From this, I infer that when they leave man's planet, the planet must be near Gargantua. To achieve both requirements, the orbit of man's planet must be highly elongated, and to avoid the planet's being engulfed by Gargantua's accretion disk as it nears Gargantua, the orbit, so far as possible, must be far above or below Gargantua's equatorial plane, where the disk resides. This dictates an orbit something like that shown in Figure 45 in your PDF companion, though extending much farther from Gargantua to 600 Gargantua radii or more. Like the orbit of Halley's Comet in our solar system, the planet swings close around Gargantua, then flies out to a large distance, then returns, swings around Gargantua, and flies out again. The whirl of space near Gargantua makes the planet fly around Gargantua once or twice on each swing by, and makes its orbit precess through a large angle from one outward excursion to the next, as shown in the figure. Man's planet can't be accompanied by a sun on its inward and outward journeys because, when near Gargantua, huge tidal forces would pry the planet and its sun apart, sending them onward in markedly different orbits. Therefore, like Miller's planet, it must be heated and lit by Gargantua's anemic accretion disk. The trip to man's planet. The Endurance's trip to man's planet begins near Gargantua and ends far from it. Such a trip, in my scientist's interpretation of the movie, requires two gravitational slingshots, one at the beginning of the trip and one at the end. At the beginning, the challenges are twofold. In its parking orbit near Gargantua, the Endurance is moving at a third of light speed, c/3, in the wrong direction, a circumferential orbit around Gargantua. It must be deflected into radial motion away from Gargantua, and the Endurance isn't moving fast enough. Gargantua's gravitational pull is so strong that if the Endurance is deflected onto a radial trajectory but still has its starting speed of c/3, then Gargantua will pull it to a halt by the time it has traversed only a small fraction of the distance to man's planet. To overcome Gargantua's gravity and reach man's planet moving with the same speed as the planet, roughly c/20, the first slingshot must accelerate the Endurance up to nearly half the speed of light. To achieve this, Cooper must find an intermediate mass black hole, IMBH, at an appropriate location and moving with a suitable velocity. Finding the necessary IMBH is not easy, and having found it, reaching it at the right point and moment in its orbit may not be easy. Most of the months-long trip may be spent reaching the IMBH, and it might entail considerable waiting for the IMBH to arrive. Once the slingshot is completed, the trip to man's planet, with speed about c/2 initially and gradual slowing to roughly c/20, will take roughly an additional 40 days. In the second slingshot, near man's planet, the Endurance swings around a suitable IMBH and soars into a gentle rendezvous with the planet, a rendezvous that doesn't require much rocket fuel. Arrival at man's planet. Ice clouds. In the movie, the Endurance parks in orbit around man's planet, and then Cooper and his crew descend to the planet in a Ranger. The planet is covered with ice, as one might expect, since, in my interpretation, it spends most of its life far from the warmth of Gargantua's accretion disk. As the Ranger nears the planet, we see it maneuver among what appear to be clouds, but then it scrapes along one and we discover the cloud is actually made from some sort of ice. Motivated by a conversation with Paul Franklin, I imagine that these clouds are largely frozen carbon dioxide, dry ice, and they are starting to be warmed as the planet is on its inward excursion toward the accretion disk, as in Figure 45 in your PDF companion. When warmed, dry ice sublimates, vaporizes, and so what appears to be clouds may be a mixture of dry ice and sublimating vapor, perhaps mostly vapor. At lower altitudes, where the Ranger lands, temperatures are higher, and the ice on which they land is presumably all frozen water. Dr. Mann's geological data. In the movie, Dr. Mann has been searching for organic material on his planet, and he claims to have found promising evidence. Promising, but not definitive. He shows his data to Brand and Romilly. The data consist of field notes that indicate where each rock sample was collected and the geological environment there, together with chemical analyses of the sample. Those chemical analyses are Dr. Mann's evidence of organics. The data were actually prepared for the movie by Erica Swanson, a talented geology PhD student at Caltech. Erica has done field work and chemical analyses somewhat similar to Dr. Mann's. In the movie, it turns out that Dr. Mann has faked his data. That's a bit ironic, since, of course, Erica faked her data too. She has never made a field trip to Mann's planet. Perhaps someday. In this book, I say nothing about the tragedy of Dr. Mann. It's a human tragedy involving little science. The tragedy's climax is an explosion that severely damages the Endurance. The explosion, the damage, and the Endurance's design. That's the stuff of science and engineering. So let's discuss them. 20. The Endurance. Status of science? Truth. Tidal gravity and the Endurance's design. The Endurance has 12 modules linked in a ring, and a control module at the ring's center. 2 landers and Rangers dock onto the Endurance's central module. In my scientist's interpretation of the movie, the Endurance was designed to survive strong tidal gravitational forces. This was important for the Endurance's trip through the wormhole. The Endurance's ring's diameter of 64 meters is nearly 1% of the wormhole's circumference. Steel and other solid materials break or flow when subjected to distortions bigger than about a few tenths of a percent, so the dangers were obvious. And little was known about what the Endurance would encounter on the Gargantua side of the wormhole, so it was designed to withstand tidal forces far stronger than the wormholes. Now, a thin fiber can be bent around into complicated shapes without any portion of the fiber's material being distorted by anything close to 1%. The key is the thinness of the fiber. You could imagine the Endurance's strength relying on a huge number of thin fibers stretching around the ring, like the strands of a cable that hold up a suspension bridge, and can bend as needed when a strong wind blows. But that would make the ring too flexible. The ring needs much resistance to being deformed, so it won't deform so severely when subjected to tidal forces that the modules crash into each other. The designers, in my interpretation, worked hard to make the Endurance resist deformation, but be able to deform without breaking if it encounters tidal forces far stronger than anticipated. Explosion in orbit above man's planet. This design philosophy really pays off when Dr. Mann unwittingly triggers a huge explosion that breaks the Endurance's ring, destroys 2 of the ring modules, and damages 2 others. The explosion sets the ring spinning so fast that its modules feel 70 Gs, 70 Earth gravities, of centrifugal force. Its broken ends swing apart from each other but don't break, and the ring's modules don't crash into each other. This, in my scientist's interpretation, is a great example of conservative design by clever engineers. Incidentally, I'm impressed by the explosion in the movie. An explosion in space makes no sound, as there is no air to transmit the sound waves. The Endurance explosion has no sound. The flames in such an explosion must quench quickly, as the oxygen that feeds them is quickly dispersed into space. The flames in the movie quench quickly. Paul Franklin tells me that his team worked hard to achieve this, as the explosion was a real one on a movie set and not a computer-generated visual effect. Another example of Christopher Nolan's commitment to science accuracy. Our discussion of Gargantua's environs has taken us from the physics of planets, tidal deformation, tsunamis, tidal bores, through Gargantua's vibrations and the search for organic signs of life, to engineering issues, the Endurance's robust design and its damaging explosion. As much as I enjoy these topics, and I've done research or textbook writing on most of them, they are not my greatest passion. My passion is extreme physics, physics at the edge of human knowledge and just beyond. That's where I take us next. 6. Extreme physics. 21. The 4th and 5th dimensions. Time as the 4th dimension. Status of science, truth. In our universe, space has 3 dimensions: up-down, east-west, and north-south. But to schedule lunch with a friend, we must tell her not only where, but also when. In this sense, time is a 4th dimension. However, time is a different kind of dimension than space. We have no trouble traveling westward as well as eastward. We make our choice and go. But having arrived at our luncheon, we cannot immediately, then and there, travel backward in time. No matter how hard we may try, we can only travel forward. The relativistic laws guarantee it. They enforce it. Nevertheless, time is a 4th dimension. It is the 4th dimension of our universe. The arena for our lives is 4-dimensional space-time, 3 space dimensions plus 1 time dimension. When we physicists explore this space-time arena by experiments and by mathematics, we discover that space and time are unified in several ways. At the simplest level, when we look out in space, we are automatically looking backward in time because of how long it takes light to reach us. We see a quasar a billion light-years away as it was a billion years ago, when the light that enters our telescope was launched on its journey to us. At a much deeper level, if you move relative to me at high speed, then we disagree on what events are simultaneous. You may think that 2 explosions, one on the Sun and the other on Earth, are simultaneous, while I think the Earth explosion was 5 minutes before the one on the Sun. In this sense, what you regard as purely spatial, the separation of the explosions, I see as a mixture of space and time. This mixing of space and time may seem counterintuitive, but it is fundamental to the very fabric of our universe. Fortunately, we can pretty much ignore it in this book, except for Chapter 30. The bulk. Is it real? Status of science, educated guess. Throughout this book, I visualize warped space by picturing our universe as a 2-dimensional warped membrane, or brain, that resides in a bulk with 3 space dimensions, as in Figure 46 in your PDF companion, for example. Of course, in reality, our brain has 3 space dimensions and the bulk has 4. But I'm not very good at drawing that, so in my pictures I usually throw one dimension away. Does the bulk really and truly exist? Or is it just a figment of our imaginations? Until the 1980s, most physicists, including me, thought it a figment. How could it be a figment? Don't we know for sure that our universe's space is warped? Don't the radio signals sent to the Viking spacecraft reveal its warpage to high precision? Yes. And since our space is truly warped, doesn't it have to be warped inside some higher dimensional space, inside some bulk? No. It is perfectly possible for our universe to be warped without there really existing a higher dimensional bulk. We physicists can describe our universe's warping, in mathematics, without the aid of a bulk. We can formulate Einstein's relativistic laws, which govern the warping, without the aid of a bulk. In fact, that's how we almost always do it in our research. The bulk, for us, until the 1980s, was just a visual aid. An aid to give us intuition about what's going on in our mathematics, and to help us communicate with each other and with non-physicists. A visual aid, not a real thing. What would it mean for the bulk to be real? How can we test whether it's real? The bulk is real if it can influence things we measure, and until the 1980s, we saw no way it could influence our measurements. Then in 1984, this changed, radically. Michael Green at the University of London and John Schwartz at Caltech had a huge breakthrough in the quest to discover the laws of quantum gravity. But strangely, their breakthrough worked only if our universe is a brain embedded in a bulk that has 1 time dimension and 9 space dimensions. A bulk with 6 more space dimensions than our brain. In the mathematical formalism that Green and Schwartz were pursuing, called superstring theory, the bulk's extra dimensions influence our brain in major ways, in ways that can be measured in physics experiments when we have sufficiently advanced technology, in ways that may make it possible to reconcile the laws of quantum physics with Einstein's relativistic laws. Since the Green-Schwartz breakthrough, we physicists have taken superstring theory very seriously and have put great effort into exploring and extending it. And, consequently, we have taken very seriously the idea that the bulk truly exists and truly can influence our universe. The 5th dimension. Status of science, educated guess. Although superstring theory says the bulk has 6 more dimensions than our universe, there is reason to suspect that, for practical purposes, the number of extra dimensions is really only 1. I explain this in Chapter 23. For this reason, and because 6 extra dimensions is a bit much for a science fiction movie, Interstellar's bulk has just 1 extra dimension, for a total of 5 dimensions in all. It shares 3 space dimensions with our brain, east-west, north-south, and up-down. It shares a 4th time dimension with our brain. And it has a 5th space dimension, out-back, which extends perpendicular to our brain, both above the brain and below. The out-back dimension plays a major role in Interstellar, though the professor and others don't use the phrase out-back, but instead just refer to the 5th dimension. Out-back is central to the next 2 chapters, and to chapters 25, 29, and 30. 22. Bulk beings. 2D brain and 3D bulk. Status of science, truth. In 1844, Edwin Abbott wrote a satirical novella titled Flatland, A Romance of Many Dimensions. Though its satire on Victorian culture seems quaint today, and its attitude toward women outrageous, the novella's venue is highly relevant to Interstellar. I recommend it to you. It describes the adventures of a square-shaped being who lives in a 2-dimensional universe called Flatland. The square visits a 1-dimensional universe called Lineland, a 0-dimensional universe called Pointland, and most amazing of all to him, a three-dimensional universe called Spaceland. And while living in Flatland, he is visited by a spherical being from Spaceland. In my first meeting with Christopher Nolan, we were both delighted to find the other had read Abbott's novella and loved it. In the spirit of Abbott's novella, imagine that you are a two-dimensional being, like the square, who lives in a two-dimensional universe like Flatland. Your universe could be a tabletop, or a flat sheet of paper, or a rubber membrane. In the spirit of modern physics, I refer to it as a two-dimensional, 2D brain. Being well-educated, you suppose there is a 3D bulk in which your brain is embedded, but you're not certain. Imagine your excitement when one day you are visited by a sphere from the 3D bulk, a bulk being, you might call him. At first, you don't realize it's a bulk being, but after much observation and thought, you see no other explanation. What you observe is this. Suddenly, with no warning and no apparent source, a blue point appears in your brain, top left of figure 47 in your PDF companion. It expands to become a blue circle that grows to a maximum diameter, middle left of figure 47, and then gradually shrinks to a point, bottom left of figure 47, and disappears completely. You believe in conservation of matter. No object can ever be created from nothing, yet this object was. The only explanation you can find is shown in the right half of figure 47. A three-dimensional bulk being, a sphere, passed through your brain. As it passed through, you saw in your brain its changing two-dimensional cross-section. The cross-section began with a point at the sphere's south pole, top right of figure 47. It expanded to a maximal circle, the sphere's equatorial plane, middle right of figure 47. It then shrank to a point, the sphere's north pole, and disappeared, bottom right of figure 47. Imagine what would happen if a 3D human being, living in the 3D bulk, passed through your 2D brain. What would you see? Bulk beings from the fifth dimension, passing through our 3D brain. Status of science? Truth. Suppose that our universe, with its 3 space and 1 time dimensions, really does live in a 5-dimensional bulk, 4 space and 1 time. And suppose there are hyperspherical beings who live in the bulk. Such a being would have a center and a surface. Its surface would consist of all points in 4 space dimensions that are some fixed distance from the center, for example, 30 centimeters. The bulk being's surface would have 3 dimensions, and its interior would have 4. Suppose that this hyperspherical bulk being, traveling in the bulk's out direction or back direction, were to pass through our brain. What would we see? The obvious guess is correct. We would see spherical cross-sections of the hypersphere. See figure 48 in your PDF companion. A point would appear from nothing. See 1 in figure 48. It would expand to become a 3-dimensional sphere, 2 in the figure. The sphere would expand to a maximum diameter, 3 in the figure, then contract, 4 in the figure, shrink to a point, 5 in the figure, and disappear. Can you guess what we would see if a 4-dimensional human being living in the bulk were to pass through our brain? To speculate about this, you need to imagine what a 4-dimensional human being with 2 legs, a torso, 2 arms, and a head must look like in the bulk with its 4 space dimensions, and what its cross-sections must look like. The nature of bulk beings and their gravity. Status of science, educated guess, and speculation. If there are bulk beings, what are they made of? Certainly not atom-based matter like us. Atoms have 3 space dimensions. They can only exist in 3 space dimensions, not 4. And this is true of subatomic particles as well. And it is true also of electric fields and magnetic fields, and the forces that hold atomic nuclei together. Some of the world's most brilliant physicists have struggled to understand how matter and fields and forces behave if our universe really is a brain in a higher dimensional bulk. Those struggles have pointed rather firmly to the conclusion that all the particles and all the forces and all the fields known to humans are confined to our brain, with one exception: gravity, and the warping of space-time associated with gravity. There might be other kinds of matter and fields and forces that have 4 space dimensions and reside in the bulk. But if there are, we are ignorant of their nature. We can speculate. Physicists do speculate. But we have no observational or experimental evidence to guide our speculations. In Interstellar, on Professor Brand's blackboard, we see him speculating. It's a reasonable, half-educated guess that if bulk forces and fields and particles do exist, we will never be able to feel them or see them. When a bulk being passes through our brain, we will not see the stuff of which the being is made. The being's cross-sections will be transparent. On the other hand, we will feel and see the being's gravity and its warping of space and time. For example, if a hyperspherical bulk being appears in my stomach and has a strong enough gravitational pull, my stomach may begin to cramp as my muscles tighten, trying to resist getting sucked to the center of the being's spherical cross-section. If the bulk being's cross-section appears and then disappears in front of a checkerboard of paint swatches, its space warp might lens the swatches, bending the image I see. And if the bulk being is spinning, it might drag space into a whirling motion that I can feel and see. Interstellar's bulk beings. Status of science: speculation. All the characters in Interstellar are convinced that bulk beings exist, though they use that name only rarely. Usually the characters call the bulk beings they, a reverential they. Early in the movie, Amelia Brand says to Cooper, "And whoever they are, they appear to be looking out for us. That wormhole lets us travel to other stars. It came along right as we needed it." One of Christopher Nolan's clever and intriguing ideas is to imagine that they are actually our descendants, humans who, in the far future, evolve to acquire an additional space dimension and live in the bulk. Late in the movie, Cooper says to Tars, "Don't you get it yet, Tars? They aren't beings. They're us, trying to help, just like I tried to help Murph." Tars responds, "People didn't build this tesseract." "Not yet," Cooper says, "but one day. Not you and me, but people. People who've evolved beyond the 4 dimensions we know." Cooper, Brand, and the crew of the Endurance never actually feel or see our bulk descendants' gravity or their space warps and whirls. That, if it ever occurs, is left for a sequel to Interstellar. But older Cooper himself, riding through the bulk in the closing tesseract of Chapter 30, reaches out to the Endurance's crew and his younger self, reaches out through the bulk, reaches out gravitationally. Brand feels and sees his presence and thinks he is they. 23. Confining gravity. The trouble with gravity in 5 dimensions. Status of science: educated guess. If the bulk does exist, then its space must be warped. If it were not warped, then gravity would obey an inverse cube law instead of inverse square. Our sun could not hang onto its planets, and the solar system would fly apart. Okay, I'll slow down and explain this more carefully. Recall that the sun's gravitational force lines, like those of the Earth and any other spherical body, point radially toward its center and pull objects along themselves toward the sun. The strength of the sun's gravitational pull is proportional to the density of the force lines, the number of lines passing through a fixed area. And since the transverse areas, spheres, through which the lines pass have 2 dimensions, the line's density goes down with increasing radius r, as 1 over r squared, and so does gravity's strength. This is Newton's inverse square law for gravity. String theory insists that gravity in the bulk is also described by force lines. If space in the bulk is not warped, then the sun's gravitational force lines will spread radially outward into the bulk. Because of the bulk's extra dimension, just 1 in Interstellar, There are 3 transverse dimensions into which gravity can spread instead of just 2. Therefore, if the bulk exists and is not warped, then the density of force lines, and thence gravity's strength, should decrease as 1 over r squared when we move away from the Sun, rather than as 1 over r cubed. The Sun's pull on the Earth would be 200 times weaker, and on Saturn 2,000 times weaker. With gravity weakening so rapidly, the Sun couldn't hold on to its planets. They would fly away into interstellar space. But they don't fly away, and their measured motions reveal unequivocally that the Sun's gravity weakens as the inverse square of the distance. The conclusion is inescapable. If there is a bulk, it must be warped in some manner that prevents gravity from spreading into the 5th dimension, the outback dimension. Is outback curled up? Status of science, educated guess. If the bulk's outback dimension were curled up into a tight roll, then gravity could not spread far into the bulk, and the inverse square law would be restored. Figure 49 in your PDF companion depicts this for the gravity of a tiny particle that resides at the center of the blue disk. In this picture, 2 space dimensions are suppressed, so we see only one of our brain's dimensions, call it north-south, along with the bulk's outback dimension. Near the particle, inside the blue disk, the force lines spread in the outback dimension as well as north-south. So, with the missing dimensions restored, gravity's strength obeys an inverse cube law. However, outside the blue disk, the curl-up makes the force lines lie parallel to our brain. They spread no further into outback, and Newton's inverse square law is restored. Physicists who struggle to understand quantum gravity think this is the fate of all the extra dimensions except possibly 1 or 2. They are curled up on microscopic scales, preventing gravity from spreading too fast. In Interstellar, Christopher Nolan ignores these curled-up dimensions and focuses on just one bulk dimension that's not curled up. This becomes his outback, 5th dimension. Why should outback not be curled up? For Chris, the answer is simple. A curled-up bulk has very little volume, nowhere near enough volume to be an arena for interesting science fiction. For Cooper to travel into the bulk riding in the Tesseract, as he does in the movie, the Tesseract needs far more volume than a curled-up dimension would provide. Outback, the anti-de Sitter warp. Status of science, educated guess. In 1999, Lisa Randall at Princeton University and MIT and Raman Sundram at Boston University conceived another way to stop gravitational force lines from spreading into the bulk. The bulk could suffer what is called anti-de Sitter warping. This warping might be produced by what are called quantum fluctuations of bulk fields, but that's irrelevant to my story, so I do not explain it here. Suffice it to say that this mechanism to produce the warping is very natural. By contrast, the anti-de Sitter, ADS, warping itself does not look natural at all. It looks downright weird. Suppose you're a microbe, and you live in a face of a microscopic tesseract. You travel, in your tesseract, out from our brain, perpendicularly out, straight up in Figure 50 in your PDF companion. And suppose you have a microbial pal, who also travels perpendicularly out from our brain. When you and your pal depart our brain, you are 1 kilometer apart, 1,000 meters, about 0.6 miles. Although you both travel precisely outward, perpendicular to our brain, your separation plummets precipitously due to ADS warping. When you have traveled 1/10 of a millimeter, the thickness of a human hair, your separation has decreased tenfold, from 1 kilometer to 100 meters. The next 0.1 millimeter of travel reduces your separation by another factor of 10 to 10 meters. The next 0.1 millimeter reduces it to 1 meter, and so forth. This shrinkage of distances parallel to our brain is hard to imagine. I don't know a good way to draw it, no better way than Figure 50 in your PDF companion. But it has marvelous consequences. It has the potential to explain a mystery called the hierarchy problem in the laws of physics. But that's outside the scope of this book. And because of the shrinkage, there is very little volume above or below our brain into which gravitational force lines can spread. Closer to our brain than 0.1 millimeter, the force lines spread into 3 transverse dimensions with impunity, so gravity obeys an inverse cube law. Farther than 0.1 millimeter, the force lines are bent parallel to our brain, and so spread into just 2 transverse dimensions, whence gravity obeys the observed inverse square law. The ADS sandwich. Plenty of room in the bulk. Status of science, speculation. Sadly, the precipitous shrinkage of distances parallel to our brain as you move outward makes the bulk's volume above and below our brain too small for Cooper and his tesseract, and too small for any other human activity in the bulk. I recognized this problem way back in 2006, when Interstellar was in its infancy, and I quickly conceived a solution for my science interpretation of the movie. Confine the ADS warping to a thin layer around our brain, a sandwich. Do so by placing 2 other brains, confining brains, alongside ours. In the sandwich between these brains, the bulk suffers ADS warping. Outside the sandwich, the bulk is totally unwarped. So there is all the volume any sci-fi writer could want outside the sandwich for bulk-based adventures. How thick must the sandwich be? Thick enough to bend gravitational force lines emerging from our brain parallel to our brain and hold them there, so we in our brain see gravity obey an inverse square law. But no thicker, because added thickness means greater total transverse shrinkage, which may cause trouble for bulk-based adventures. Suppose our whole universe, as seen from outside the ADS layer, were shrunk to the size of a pinhead. The required thickness turns out to be about 3 centimeters, roughly an inch. So as you travel from our brain to a confining brain, distances parallel to our brain shrink by 15 powers of 10, 1,000 trillion. In my interpretation of Interstellar, Gargantua is in the far reaches of the observable universe, roughly 10 billion light-years from Earth. Cooper, in the tesseract, rises through the ADS layer, from Gargantua's core into the bulk. There, the distance to Earth is 10 billion light-years divided by 1,000 trillion, which is about the same as the distance between the Sun and the Earth, 1 astronomical unit. Cooper then travels that 1 AU distance through the bulk, parallel to our brain, to reach the Earth and visit Murph. Danger. The sandwich is unstable. Status of science, speculation. In 2006, I used Einstein's relativistic laws to work out a mathematical description of the ADS layer and its confining brains. Because I had never before worked with relativity in 5 dimensions, I asked Lisa Randall to critique my analysis. Lisa browsed it quickly and then told me some good news and some bad news. The good news. My idea of an ADS sandwich had been invented 6 years earlier by Ruth Gregory, University of Durham, UK, together with Valery Rubakov and Sergei Sibirikov, Institute for Nuclear Research in Moscow, Russia. This showed I was not being stupid in my first mathematical foray into the bulk. I had rediscovered something worth discovering. The bad news. Edward Witten, Princeton, and others had shown that the ADS sandwich is unstable. The confining brains are under pressure, rather like a playing card that you squeeze end to end between your finger and thumb. The card bends, and with further squeezing, it buckles. Similarly, the confining brains will bend and crash into our brain, our universe, destroying it. The entire universe destroyed. That's the worst news ever. But I can think of several ways to save our universe, if it really does live in an ADS sandwich, which I very much doubt it does. Several ways to stabilize the confining brains, in the jargon of physicists. In my science interpretation of Interstellar, Professor Brand, working with Einstein's relativity equations, rediscovers the ADS sandwich, as I did. How the confining brains are stabilized then gets intertwined with the professor's struggle to understand and control gravitational anomalies. In the movie, that struggle is spelled out mathematically on the 16 blackboards in Professor Brand's office. Traveling through the ADS layer. Status of science, speculation. In the ADS layer, the ADS warpage of space produces tidal forces that are enormous by human standards. Any bulk being traveling through the layer to reach our brain must deal with those forces. Because we know nothing about the matter of which a bulk being is made, matter with 4 space dimensions, we have no idea whether this is an issue. In science fiction, it can be left in the hands of the writers. Not so for Cooper, riding in the Tesseract. In my interpretation of the movie, he has to cross the ADS layer. The Tesseract must either protect him from the layer's enormous tidal forces or clear the ADS layer away from his path. Otherwise, he'll be spaghettified. By confining gravity, the ADS layer regulates its strength. In Interstellar, we see gravity's strength fluctuate, perhaps due to fluctuations in the ADS layer. These fluctuations, gravitational anomalies, play a huge role in Interstellar. To them we now turn. 24. Gravitational anomalies. A gravitational anomaly is something about gravity that doesn't fit our understanding of the universe, or our understanding of the physical laws that control the universe. For example, the falling books in Interstellar that Murph attributes to a ghost. Since 1850, physicists have put a lot of effort into searching for gravitational anomalies and understanding those few that were found. Why? Because any true anomaly is likely to produce a scientific revolution, a major change in what we think is true. This, in fact, has happened 3 times since 1850. In Interstellar, Professor Brand's struggle to understand gravitational anomalies is very much in the spirit of these previous revolutions, so I describe the previous ones briefly. The anomalous precession of Mercury's orbit. Status of science, truth. Newton's inverse square law for gravity forces the orbits of the planets around the Sun to be ellipses. Each planet feels small gravitational tugs from the other planets, and these tugs cause its ellipse to gradually change orientation, that is, to gradually precess. In 1859, the astronomer Urbain Le Verrier at the Observatoire de Paris, France, announced he had discovered an anomaly in the orbit of the planet Mercury. When he computed the total precession of Mercury's orbit caused by all the other planets, he got the wrong answer. The measured precession is larger than the planets could produce by about 0.1 arcsecond each time Mercury traverses its orbit. Now, 0.1 arcsecond is a tiny angle, just 1/10,000,000th of a circle. But Newton's inverse square law insists there can be no anomaly whatsoever. Le Verrier convinced himself that this anomaly is produced by the gravitational tug of an undiscovered planet closer to the Sun than Mercury. Vulcan, he called it. Astronomers searched in vain for Vulcan. They could not find it, nor could they find any other explanation for the anomaly. By 1890, the conclusion seemed clear. Newton's inverse square law must be very slightly wrong. Wrong in what way? A revolutionary way, it turned out. The way discovered by Einstein 25 years later. The warping of time and space endowed the Sun with a gravitational force that obeys Newton's inverse square law, but only nearly, not precisely. Upon realizing that his new relativistic laws explained the observed anomaly, Einstein was so excited that he suffered heart palpitations and felt like something snapped inside himself. For a few days, I was beside myself with joyous excitement. Today, the measured anomalous precession and the predictions by Einstein's laws agree to within 1 part in 1,000, 1,000th of the anomalous precession, which is the accuracy of the observations, a great triumph for Einstein. The anomalous orbits of galaxies around each other. Status of science, truth. In 1933, the Caltech astrophysicist Fritz Zwicky announced he had discovered a huge anomaly in the orbits of galaxies around each other. The galaxies were in the Coma cluster, a collection of about 1,000 galaxies, 300 million light-years from Earth, in the constellation Coma Berenices. From the Doppler shifts of the galaxy's spectral lines, Zwicky could estimate how fast they were moving relative to each other. And from the brightness of each galaxy, he could estimate its mass and thence its gravitational pull on the other galaxies. The galaxies' motions were so fast that there was no way their gravitational pulls could hold the cluster together. Our best understanding of the universe and of gravity insisted that the cluster must be flying apart and would soon be completely destroyed. If so, then the cluster must have formed by random motions of all those galaxies and would disrupt in a veritable blink of an eye compared to other astronomical phenomena. This conclusion was totally implausible to Zwicky. Something was wrong with our conventional wisdom. Zwicky made an educated guess. The Coma cluster must be filled with some sort of dark matter, whose gravity is strong enough to hold the cluster together. Now, many anomalies that astronomers and physicists think they have discovered go away when observations improve. This one did not. Instead, it spread. By the 1970s, it was clear that so-called dark matter permeates most all clusters of galaxies, and even individual galaxies. By the 2000s, it was clear that the dark matter gravitationally lenses light from more distant galaxies, just as Gargantua gravitationally lenses light from stars. Today, that lensing is being used to map the dark matter in our universe. And today, physicists are fairly sure that the dark matter is truly revolutionary, that it consists of fundamental particles of a type never before seen, but a type predicted by our best current understanding of the quantum laws of physics. Physicists have embarked on a holy grail mission, a quest to detect these particles of dark matter, shooting through the Earth with near impunity, and measure their properties. The anomalous acceleration of the universe's expansion. Status of science, truth. In 1998, two research groups independently discovered an astounding anomaly in the expansion of our universe. For this discovery, the group's leaders, Saul Perlmutter and Adam Rees at the University of California, Berkeley, and Brian Schmidt at the Australian National University, won the 2011 Nobel Prize in Physics. Both groups were observing supernova explosions triggered when a massive star exhausts its nuclear fuel and implodes to form a neutron star, and the implosion energy blows off the star's outer layers. They discovered that distant supernovae are dimmer than expected, and therefore farther away than expected. Farther enough away that the universe's expansion must have been slower in the past than today. The expansion is accelerating. Now, our best understanding of gravity and the universe required, unequivocally, that all things in the universe, stars, galaxies, galaxy clusters, dark matter, etc., must pull on each other gravitationally. And by that pull they must slow the universe's expansion. The universe's expansion must slow down over time, not speed up. For this reason, I, personally, didn't believe the claimed acceleration, nor did many of my astronomer and physicist colleagues. We didn't believe until other observations, by completely different methods, confirmed it. Then we caved. So what's going on? There are two possibilities. Something is wrong with Einstein's relativistic laws of gravity, or something else is filling the universe, in addition to ordinary matter and dark matter, something that repels gravitationally. Most physicists love Einstein's relativistic laws and are loath to give them up, and so lean toward repulsion. The hypothetical material that repels has been given the name dark energy. The final verdict is not in. But if the cause of the anomaly is indeed dark energy, whatever that may be, then gravitational observations now tell us that 68% of the universe's mass is in dark energy, 27% is in dark matter, and only 5% is in the kind of ordinary matter of which you, I, planets, stars, and galaxies are made. So, physicists today have another holy grail: to understand whether the universe's accelerated expansion is caused by a breakdown of Einstein's relativistic laws, and if so, what is the nature of the correct laws, or is caused by repulsive dark energy, and if so, what is the nature of the dark energy? Gravitational anomalies in Interstellar. Status of science, speculation. The gravitational anomalies in Interstellar are seen on Earth, by contrast with the three anomalies that I described. Physicists have put great effort into searching for such anomalies on Earth, beginning with Isaac Newton himself in the late 1600s. Those searches have produced many claimed anomalies, but all claims, upon deeper scrutiny, have collapsed. The anomalies in Interstellar are startling for their weirdness and strength, and the way they change as time passes. If anything like them had occurred in the 20th century or early 21st, physicists would surely have noticed them and explored them with great fervor. Somehow, gravity on Earth has been altered in the era of Interstellar. And indeed, Romilly tells Cooper so in the movie. We started detecting gravitational anomalies on Earth almost 50 years ago, and also around that same time, the most significant anomaly of all, the sudden appearance of a wormhole near Saturn, where before there was none. In the movie's opening scene, Cooper experiences an anomaly himself while trying to land a Ranger spacecraft. "Over the straits, something tripped my fly-by-wire," he tells Romilly. The GPS system that Cooper has adapted to control harvesting machines as they roam through cornfields has also gone haywire, and a bunch of harvesters have converged on his farmhouse. He attributes this to gravitational anomalies that screwed up the gravity corrections that any GPS system relies on. Early in the movie, we see Murph watch, transfixed, as dust falls unnaturally fast to the floor of her bedroom, collecting in a barcode-like pattern of thick lines. And then we see Cooper stare at the lines and toss a coin across one. The coin shoots to the floor. In my science interpretation of Interstellar, I presume that Professor Brand's team has collected a large trove of data on the anomalies. The most interesting data to me as a physicist, and to Professor Brand in my movie interpretation, is new and changing patterns of tidal gravity. We first met tidal gravity in Chapter 4. The tidal gravity produced by a black hole and tidal gravity on Earth produced by the Moon and Sun. In Chapter 17, we saw Gargantua's tidal gravity in action on Miller's planet, triggering gigantic Miller quakes, tsunamis, and tidal bores. In Chapter 16, we met the tiny stretching and squeezing of tidal gravity in a gravitational wave. Tidal gravity is produced not only by black holes, the Sun, the Moon, and gravitational waves, but also, in fact, by all gravitating objects. For example, regions of the Earth's crust that contain oil are less dense than regions containing only rock, so their gravitational pull is weaker. This leads to a peculiar pattern of tidal gravitational forces. In Figure 51 in your PDF companion, I use Tendex lines to illustrate that tidal force pattern. Squeezing Tendex lines, drawn blue, stick out of the oil-bearing region, while stretching Tendex lines, drawn red, stick out of the denser, oil-free region. As always, the two families of Tendex lines are perpendicular to each other. An instrument called a gravity gradiometer can measure these tidal patterns. See Figure 52 in your PDF companion. It consists of two crossed, solid rods attached to a torsional spring. On the ends of each rod are masses that feel gravity. The rods are normally perpendicular to each other, but in the figure, the blue Tendex lines squeeze the top two masses together and squeeze the bottom two together, while the red Tendex lines stretch the right pair of masses apart and stretch the left pair apart. As a result, the angle between the rods decreases until the spring counterbalances the tidal forces. This is the gradiometer's readout, its readout angle. If this gradiometer is flown rightward through the tidal pattern of Figure 51, its readout angle opens up above the oil-bearing region and then closes down over the oil-free region. Gradiometers like this, but more sophisticated, are used by geologists to search for oil and also for mineral deposits. NASA has flown a more sophisticated gradiometer called GRACE to map tidal fields everywhere above the Earth and watch slow changes of tidal gravity produced, for example, by the melting of ice sheets. In my interpretation of Interstellar, most of the gravitational anomalies that Professor Brand's team measures are sudden and unexpected changes in the patterns of Tendex lines above the Earth's surface, changes that occur for no obvious reason. The rocks and oil in the Earth's crust are not moving. The melting of ice sheets is much too slow to produce these quick changes. People see no new gravitating masses coming near the gradiometers. Nevertheless, the gradiometers report changing tidal patterns. Falling dust accumulates in radial lines. Cooper sees the coin plunge to the floor. The members of Professor Brand's team monitor these changing patterns and eagerly record Cooper's observations. Their trove of data becomes grist for the professor's quest to understand gravity, a quest that centers on the professor's equation. 25. The professor's equation. Status of science: speculation. In Interstellar, the gravitational anomalies excite Professor Brand for two reasons. If he can discover their cause, that may trigger a revolution in our understanding of gravity, a revolution as great as Einstein's relativistic laws. More important, if he can figure out how to control the anomalies, that could enable NASA to lift large colonies of people off the dying Earth and launch them toward a new home elsewhere in the universe. For the professor, the key to understanding and controlling the anomalies is an equation he has written on his blackboard. In the movie, he and Murph struggle to solve his equation. Murph's and the professor's notebooks, and the blackboard. Before filming began, two impressive Caltech physics students filled notebooks with calculations about the professor's equation. Elena Merchikova filled a clean, new notebook with calculations by grown-up Murph, calculations written with elegant calligraphy. Keith Matthews filled a beat-up old notebook with calculations by Professor Brand, in the more sloppy handwriting common for old guys like the professor and me. In the movie, grown-up Murph, played by Jessica Chastain, discusses the math in her notebook with the professor, played by Michael Caine. Merchikova, an expert in quantum gravity and cosmology, was on set to advise Chastain about her dialogue and notebook, and things she was to write on the blackboard. It was startling to see these two brilliant and beautiful women from very different worlds, both with bright red hair, huddled together. As for me, I filled Professor Brand's blackboard with diagrams and mathematics, including the professor's equation, the equation, at Christopher Nolan's request, of course. And I took great pleasure in talking with Michael Caine, who seemed to view me as a sort of prototype for the professor he was playing, and great pleasure in watching Chris, a master craftsman, mold the scenes he was filming into precisely the form he wanted. Some weeks before filming in the professor's office, Chris and I went back and forth about what should be the nature of the equation. Here's my long scientist's interpretation for what we wound up with, my extrapolation of the movie's story. Source of the anomalies: the fifth dimension. In my extrapolation, it does not take long for the professor to convince himself that the anomalies are due to gravity from the fifth dimension, from the bulk. Why? The sudden changes in tidal gravity have no apparent source in our four-dimensional universe. For example, in my extrapolation, the professor's team sees the tidal gravity above an oil deposit switch in just a few minutes from the pattern we expect to a radically different pattern. The oil has not moved, the rocks have not shifted, Nothing in our four-dimensional universe has changed except the tidal gravity. These sudden changes must have a source. If the source is not in our universe, on our brain, then there is only one other place it can be, the professor reasons, in the bulk. In my extrapolation, the professor can think of just 3 ways that something in the bulk could produce these anomalies, and the first 2 he quickly rejects. 1. Some object in the bulk, perhaps even a living object, a bulk being, might come near our brain but not pass through it. See upper right of figure 53 in your PDF companion. The object's gravity reaches out through all the bulk's dimensions and so could reach into our brain. However, the ADS layer surrounding our brain would drive the object's tidal tendex lines parallel to our brain, allowing only a minuscule portion to reach our brain. So the professor rejects this. 2. A bulk object passing through our brain could produce tidal gravity that changes as the bulk object moves. See middle right of figure 53. However, in my extrapolation, most of the patterns of changing gravity that the professor's team observed don't fit this explanation. The tendex lines tend to be more diffuse than those from a localized object. Some tidal anomalies might be from localized objects, but most must be something else. 3. Bulk fields passing through our brain could produce the changing tidal gravity. See left side of figure 53. This, the professor concludes in my extrapolation, is the most likely explanation for most of the anomalies. What is a bulk field? Physicists use the word field to mean something that extends out through space and exerts forces on things it encounters. We have already met several examples of fields that live in our universe, our brain. In Chapter 2, magnetic fields, collections of magnetic force lines. Electric fields, collections of electric force lines. Gravitational fields, collections of gravitational force lines. And in Chapter 4, tidal fields, collections of stretching and squeezing tendex lines. A bulk field is a collection of force lines that resides in the 5-dimensional bulk. What kind of force lines, the professor doesn't know, but he speculates. Figure 55 in your PDF companion shows a bulk field, dashed purple lines, passing through our brain. This bulk field generates tidal gravity in our brain, red and blue tendex lines. As the bulk field changes, its tidal gravity changes, resulting, the professor thinks, in most of the observed anomalies. But that isn't the only role of bulk fields, he suspects, in my extrapolation. They may also control the strength of the gravity produced by objects living in our brain, such as a rock or planet. Bulk fields control the strength of gravity. The gravity of each little bit of matter in our brain is governed to high accuracy by Newton's inverse square law. Its gravitational pull is embodied in the formula G equals gm over r squared, where r is the distance from that bit of matter, m is the mass of that bit of matter, and g is Newton's gravitational constant. This g controls the overall strength of the gravitational pull. In Einstein's more accurate relativistic version of the gravitational laws, the strength of gravity and the strength of all the warping of space and time produced by matter are also proportional to this g. If there is no bulk, if the only thing that exists is our 4-dimensional universe, then Einstein's relativistic laws say that g is absolutely constant, the same everywhere in space, never changing in time. But if the bulk does exist, then the relativistic laws allow this g to change. It might, the professor speculates, be controlled by bulk fields. It probably is controlled by bulk fields, he thinks. That's the best explanation for one of the observed anomalies in my extrapolation of the movie story. The strength of the Earth's gravitational pull varies slightly from place to place due to the varying density of the rocks, oil, oceans, and atmosphere. Earth-orbiting satellites have mapped this varying strength. As of 2014, the most accurate map is from the European Space Agency's satellite GOCE. According to this map, in 2014, the Earth's gravity is weakest in southern India and strongest in Iceland and Indonesia. In my extrapolation, this map did not change noticeably until anomalies started appearing. Then one day, quite suddenly, the Earth's gravitational pull in North America weakened a bit, and in South Africa it strengthened. Professor Brand tried to explain this as a change in the tidal forces produced by bulk fields, but had difficulty. The best explanation he could find is that the gravitational constant G increased inside the Earth, below South Africa, and decreased inside the Earth, below North America. Rock below South Africa was suddenly pulling more strongly. Rock below North America was suddenly pulling more weakly. These changes must have been produced by some sort of bulk field that passes through our brain and controls G, he reasoned. Bulk fields are not just the key to gravitational anomalies on Earth, Professor Brand believes, in my extrapolation. Bulk fields also play two other crucial roles. They hold the wormhole open, and they protect our universe from destruction. Holding the wormhole open. The wormhole that connects our solar system to Gargantua's neighborhood, if left to its own devices, will pinch off. Our connection to Gargantua will be severed. This is the unequivocal conclusion of Einstein's relativistic laws. If there is no bulk, then the only way to hold the wormhole open is to thread it with exotic matter that repels gravitationally. The dark energy that may accelerate our universe's expansion is probably not repulsive enough. In fact, it seems likely, in 2014, that the laws of quantum physics prevent even an exceedingly advanced civilization from ever collecting enough exotic matter to hold the wormhole open. And I imagine this conclusion is even more certain in Professor Brand's era. But there is an alternative, the professor realizes in my extrapolation of the movie's story. Bulk fields may do the job. They may hold the wormhole open. And since the professor thinks the wormhole has been constructed and placed near Saturn by bulk beings, bulk fields holding it open seem natural to him. Protecting our universe from destruction. In order for gravity in our universe to obey Newton's inverse square law to high accuracy, our brain must be sandwiched between two confining brains with ADS warping between them. However, the confining brains are filled with pressure and prone to buckle, like a playing card pinched between two fingers. This is the unequivocal prediction of Einstein's relativistic laws applied to the bulk and brains. This buckling, if not counteracted, will make the confining brains collide with our brain, with our universe. Our universe will be destroyed. Obviously, our universe has not been destroyed, the professor observes in my extrapolation. So something must prevent the confining brains from buckling. The only thing he can think of to do the job is bulk fields. Whenever a confining brain starts to bend, bulk fields must somehow exert a force on it, pushing it back into its proper, straight shape. The professor's equation, at last. The laws of physics are expressed in the language of mathematics. Before Cooper met Professor Brand, in my extrapolation of the movie's story, the professor tried to build a mathematical description of the bulk fields and how they might generate anomalies, control our universe's gravitational constant G, hold the wormhole open, and protect our brain from collisions. In creating this mathematics, the professor was guided by the trove of observational data his team was collecting, and by Einstein's relativistic laws of physics in 5 dimensions. The professor embodied all his insights in a single equation, the equation, which he wrote on one of the 16 blackboards in his office. Cooper sees the equation on his first visit to NASA, and the equation is still there 30 years later, when Murph has grown up to become a brilliant physicist in her own right and is helping the professor try to solve it. This equation is called an action. There is a well-known, to physicists, mathematical procedure to begin with such an action, and from it deduce all the non-quantum physical laws. The professor's equation, in effect, is the mother of all non-quantum laws. But for it to give birth to the right laws, the laws that predict correctly how the anomalies are produced, how the wormhole is held open, how G is controlled, and how our universe is protected. The equation must have precisely the correct mathematical form. The professor doesn't know the correct form. He is guessing. His is an educated guess, but a guess nevertheless. His equation contains lots of guessing. Guesses for the things called UQ, H sub ij, Q squared, W sub ij, and M, standard model fields, on his blackboard. In effect, these are guesses for the nature of the bulk field's force lines, and how they influence our brain, and how fields in our brain influence them. When the professor and his team speak of solving his equation, in my extrapolation, they mean two things. First, figure out the right forms for all these things they are guessing. UQ, H sub ij, Q squared, W sub ij, and M, standard model fields. Second, following the well-known procedure, deduce from his equation everything he wants to know about our universe, about the anomalies, and most important, about how to control the anomalies so as to lift colonies off the Earth. When characters in the movie speak of solving gravity, they mean the same thing. In the movie, when the professor is very old, we see him and grown-up Murph trying to solve his equation by iterations. On a blackboard, they make a list of guesses for the unknown things. Then, in my extrapolation, Murph inserts each guess into a huge computer program that they've written. The program computes the physical laws for that guess and those laws' predictions for how the gravitational anomalies behave. In my extrapolation, none of the guesses predicts anomalies that look anything like the observations. But in the movie, the professor and Murph keep trying. They keep iterating, making a guess, computing the consequences, abandoning the guess, and going on to the next guess. One guess after another, after another, after another, until exhaustion sets in. Then they begin again the next day. A bit later in the movie, when the professor is on his deathbed, he confesses to Murph, "I lied, Murph. I lied to you." It is a poignant scene. Murph infers that he knew something was wrong with his equation, knew from the outset. And Dr. Mann tells the professor's daughter as much in an equally poignant scene on Mann's planet. But, in fact, Murph realizes, soon after the professor's death, his solution was correct. He'd had it for years. It's half the answer. The other half can be found inside a black hole, in a black hole's singularity. 26. Singularities and quantum gravity. In Interstellar, Cooper and TARS seek quantum data inside Gargantua, data that could help the professor solve his equation and lift humanity off Earth. The data, they believe, must reside inside a singularity that inhabits Gargantua's core, a gentle singularity, Romilly predicts. What are the quantum data? How could they help the professor? And what is a gentle singularity? The primacy of quantum laws. Status of science, truth. Our universe is fundamentally quantum. By this, I mean that everything fluctuates randomly, at least a little bit. Everything. When we use high-precision instruments to look at tiny things, we see big fluctuations. The location of an electron inside an atom fluctuates so rapidly and so randomly that we can't know where the electron is at any moment of time. The fluctuations are as big as the atom itself. That's why the quantum laws of physics deal with probabilities for where the electron is, and not with its actual location. When we use instruments to look at big things, we also see fluctuations, if our instruments are precise enough. But the fluctuations of big things are minuscule. In the LIGO gravitational wave detectors, laser beams monitor the locations of hanging mirrors that weigh 40 kilograms, 90 pounds. Those locations fluctuate randomly, but by amounts far less than the size of an atom. 1/10,000,000,000th of an atom's size, in fact. Nevertheless, LIGO's laser beams will see those fluctuations a few years from now. LIGO's design prevents those random fluctuations from getting in the way of measuring gravitational waves. My students and I helped make sure of this. Because objects of human size and larger have only minuscule quantum fluctuations, physicists almost always ignore those fluctuations. Discarding the fluctuations in our mathematics simplifies the laws of physics. If we begin with the ordinary quantum laws that ignore gravity and then discard the fluctuations, we obtain the Newtonian laws of physics, the laws used for the past few centuries to describe planets, stars, bridges, and marbles. If we begin with the ill-understood laws of quantum gravity and then discard the fluctuations, we must obtain Einstein's well-understood relativistic laws of physics. The fluctuations we discard are, for example, a froth of fluctuating, exquisitely tiny wormholes, quantum foam that pervades all of space. With the fluctuations gone, Einstein's laws describe the precise warping of space and time around black holes, and the precise slowing of time on Earth. This is all the preamble to a punchline. If Professor Brand could discover the quantum gravity laws for the bulk as well as our brain, then by discarding those laws' fluctuations, he could deduce the precise form of his equation. And that precise form would tell him the origin of the gravitational anomalies and how to control the anomalies, how to employ them, he hopes, to lift colonies off Earth. In my extrapolation of the movie, the professor knows this, and he also knows a place where the quantum gravity laws can be learned, inside singularities. Singularities, the domain of quantum gravity. Status of science, truth. The beginning of a singularity is a place where the warping of space and time grows without bound, where space warps and time warps become infinitely strong. If we think of our universe's warped space as like the undulating surface of the ocean, then the beginning of a singularity is like the tip of a wave that is about to break, and the interior of the singularity is like the froth after it breaks. The smooth wave, before it breaks, is governed by smooth laws of physics, analogues of Einstein's relativistic laws. The froth after it breaks requires laws capable of dealing with frothing water, analogues of the laws of quantum gravity with their quantum foam. Singularities inhabit the cores of black holes. Einstein's relativistic laws predict them unequivocally, even though those laws can't tell us what happens inside the singularities. For that, we need the quantum gravity laws. In 1962, I moved from Caltech, my undergraduate school, to Princeton University to study for a PhD in physics. I chose Princeton because John Wheeler taught there. Wheeler was that era's most creative genius when it comes to Einstein's relativistic laws. I wanted to learn from him. One September day, with trepidation, I knocked on the door of Professor Wheeler's office. It would be my first meeting with the great man. He greeted me with a warm smile, ushered me in, and immediately, as though I were an esteemed colleague, not a total novice, began discussing the mysteries of the implosions of stars. Implosions that produce black holes with singularities in their cores. These singularities, he asserted, are a place in which the fiery marriage of Einstein's relativistic laws with the quantum laws is consummated. The fruits of that marriage, the laws of quantum gravity, come into full blossom in singularities, Wheeler asserted. If we could understand singularities, we would learn the laws of quantum gravity. Singularities are a Rosetta Stone for deciphering quantum gravity. From that private lecture, I emerged a convert. From Wheeler's public lectures and writings, many other physicists emerged as converts and embarked on a quest to understand singularities and their quantum gravity laws. That quest continues today. That quest produced superstring theory, which in turn led to a belief that our universe must be a brain residing in a higher dimensional bulk. Naked singularities? Status of science, educated guess. It would be fabulous if we could find or make a singularity outside a black hole. A singularity not hidden beneath a black hole's event horizon, a naked singularity. Then, in Interstellar, the professor's task could be easy. He might extract the crucial quantum data from a naked singularity in his NASA lab. In 1991, John Preskill and I made a bet about naked singularities with our friend Stephen Hawking. Preskill, a Caltech professor, is one of the world's great experts on quantum information. Stephen is the wheelchair guy who appears on Star Trek, The Simpsons, and The Big Bang Theory. He also happens to be one of the greatest geniuses of our era. John and I bet the laws of physics permit naked singularities. Stephen bet they are forbidden. None of us thought the bet would be resolved quickly, but it was. Just 5 years later, Matthew Choptik, a postdoctoral student at the University of Texas, carried out a simulation on a supercomputer that he hoped would reveal new, unexpected features of the laws of physics. And he hit the jackpot. What he simulated was the implosion of a gravitational wave. When the imploding wave was weak, it imploded and then dispersed. When it was strong, the wave imploded and formed a black hole. When its strength was very precisely tuned to an intermediate strength, the wave created a sort of boiling in the shapes of space and time. The boiling produced outgoing gravitational waves with shorter and shorter wavelengths. It also left behind, at the end, an infinitesimally tiny, naked singularity. Now, such a singularity can never occur in nature. The required tuning is not a natural thing. But an exceedingly advanced civilization could produce such a singularity artificially by precisely tuning a wave's implosion, and then could try to extract the laws of quantum gravity from the singularity's behavior. Upon seeing Choptik's simulation, Stephen conceded our bet. On a technicality, he said. He thought precise tuning unfair. He wanted to know whether naked singularities can occur naturally. So we renewed our bet with a new wording that the singularity must arise without any need for precise tuning. Nevertheless, Stephen's concession, in a very public venue, was a big deal. It made the front page of the New York Times. Despite our renewed bet, I doubt that naked singularities do exist in our universe. In Interstellar, Dr. Mann firmly asserts that the laws of nature prohibit a naked singularity, and Professor Brand never even mentions that possibility. Instead, the professor focuses on singularities inside black holes. Those, he thinks, are the only hope for learning the laws of quantum gravity. The BKL singularity inside a black hole. Status of science, educated guess. In Wheeler's era, the 1960s, we thought of a singularity inside a black hole as like a sharp point. A point that squeezes matter until the matter becomes infinitely dense and is destroyed. That's how, until now in this book, I have depicted a black hole's singularity. Since Wheeler's era, mathematical calculations with Einstein's laws have taught us that these pointy singularities are unstable. To create them inside a black hole requires precise tuning. When perturbed ever so slightly, for example by something falling in, they change enormously. Change into what? 3 Russian physicists, Vladimir Belinsky, Isaac Kalatnikov, and Eugene Lifshitz, used long, complicated calculations to guess the answer. In 1971. And in the 2000s, when computer simulations became sufficiently advanced, their guess was confirmed by David Garfinkel at Oakland University. The resulting stable singularities now carry the name BKL in honor of Belinsky, Kalatnikov, and Lifshitz. A BKL singularity is chaotic, highly chaotic, and lethal, highly lethal. In Figure 54 in your PDF companion, I depict the warping of space outside and inside a fast-spinning black hole. The BKL singularity is at the bottom. If you fall into this black hole, its interior at first is smooth and perhaps pleasant. But as you near the singularity, the space around you begins to stretch and squeeze in a chaotic pattern, and tidal forces begin to stretch and squeeze you chaotically. The stretch and squeeze are gentle at first, but quickly they become strong. then ultra-strong. Your flesh and bones are pummeled and give way. Then the atoms of which your body was made are pummeled and give way, distorted beyond recognition. All this and its chaotic pattern are described by Einstein's relativistic laws. It is this that the Russians, B, K, and L, predicted. What they could not predict, what nobody can predict today, is the fate of your atoms and subatomic particles when the chaotic pummeling grows to an infinite crescendo. Only the laws of quantum gravity know their fate. But you, yourself, are long since dead, with no possibility to retrieve the quantum data and escape. I labeled the science in this section as an educated guess because we are not absolutely certain that the singularity inside a black hole's core is a BKL one. BKL singularities are surely allowed by Einstein's relativistic laws. Garfinkel confirmed it by computer simulations. But more sophisticated simulations are needed to confirm that the BKL patterns of humongous stretch and squeeze do actually occur in the core of a black hole. I'm almost sure the result of those simulations will be yes, they do occur, but I'm not completely certain. A black hole's infalling and outflying singularities. Status of science, educated guess. My physicist colleagues and I were pretty sure in the 1980s, as an educated guess, that there is just one singularity inside a black hole, and it's a BKL singularity. We were wrong. In 1991, Eric Poisson and Werner Israel at the University of Alberta, Canada, working with the mathematics of Einstein's laws, discovered a second singularity. This one grows with time as the black hole ages. It's caused by extreme slowing of time inside the black hole. If you fall into a spinning black hole such as Gargantua, lots of other stuff inevitably will fall in after you. Gas, dust, light, gravitational waves, and so forth. This stuff may take millions or billions of years to enter the hole as seen by me watching from outside. But as seen by you, now inside the hole, it may take only a few seconds or less due to the extreme slowing of your time compared with mine. As a result, as seen by you, this stuff all piles up in a thin sheet, falling inward toward you at the speed of light, or nearly the speed of light. This sheet generates intense tidal forces that distort space and will distort you if the sheet hits you. The tidal forces grow to become infinite. The result is an infalling singularity, governed by the laws of quantum gravity. However, the tidal forces grow so swiftly, Poisson and Israel deduced, that if they hit you, they will have deformed you by only a finite amount at the moment you reach the singularity. This is explained in Figure 55 in your PDF companion, which plots your net stretch along the up-down direction and squeeze along the north-south and east-west directions as time passes. When you hit the singularity, your net stretch and squeeze are finite, but the rates at which you are being stretched and squeezed, the slopes of the black curves, are infinite. Those infinite rates are the infinite tidal forces signaling the singularity. Because your body has been stretched and squeezed by only a finite net amount when you reach the singularity, it is conceivable you might survive. Conceivable but unlikely, I think. In this sense, the infalling singularity is far more gentle than the BKL singularity. If you do survive, what happens next is known only to the laws of quantum gravity. In the 1990s and 2000s, we physicists thought this was the whole story. A BKL singularity created when the black hole is born, and an infalling singularity that grows afterward. That's all. Then, in late 2012, while Christopher Nolan was negotiating to rewrite and direct Interstellar, a third singularity was discovered by Donald Maroff, University of California at Santa Barbara, and Amos Ori, the Technion in Haifa, Israel. It was discovered, of course, via an in-depth study of Einstein's relativistic laws and not via astronomical observations. In retrospect, this singularity should have been obvious. It is an outflying singularity that grows as the black hole ages, just like the infalling singularity grows. It is produced by stuff, gas, dust, light, gravitational waves, etc., that fell into the black hole before you fell in. A tiny fraction of that stuff is scattered back upward toward you, scattered by the hole's warpage of space and of time, much like sunlight scattered off a curved, smooth ocean wave, which brings us an image of the wave. The upscattered stuff gets compressed by the black hole's extreme slowing of time into a thin layer, rather like a sonic boom, a shock front. The stuff's gravity produces tidal forces that grow infinitely strong and thence become an outflying singularity. But as for the infalling singularity, so also for this outflying one, the tidal forces are gentle. They grow so quickly, so suddenly, that if you encounter one, your net distortion is finite, not infinite, at the moment you hit the singularity. In Interstellar, Romilly tells Cooper about these gentle singularities. I have a suggestion for your return journey from man's planet. Have one last crack at the black hole. Gargantua is an older, spinning black hole. It has what we call a gentle singularity. Gentle? Cooper asks. They're hardly gentle, but their tidal gravity is quick enough that something crossing the horizon fast might survive. Cooper, lured by this conversation and the quest for quantum data, later plunges into Gargantua. It's a brave plunge. He can't know in advance whether he'll survive. Only the laws of quantum gravity know for sure. Or the bulk beings. We've now laid the extreme physics foundations for Interstellar's climactic scenes. So let's turn to the climax. 7. Climax. 27. The volcano's rim. Status of science: truth. Late in Interstellar, Cooper has just dragged the Endurance out of its death spiral at man's planet and feels a great sense of relief when the robot Case says to him, "We're heading into Gargantua's pull." Cooper makes a quick decision. The navigation mainframe's destroyed and we don't have enough life support to make it back to Earth. But we might scrape to Edmund's planet. What about fuel? Amelia Brand asks. Not enough, Cooper responds. Let Gargantua suck us right to near the horizon, then a powered slingshot around to launch us at Edmund's planet. Manually? That's what I'm here for. I'll take us just inside the critical orbit. Within minutes, they are at the critical orbit, and all hell breaks loose. In this chapter, I describe my scientist's interpretation of this. Tidal gravity, breaking the Endurance away from man's planet. In my interpretation, man's planet is on a highly elongated orbit. When the Endurance arrived at the planet, it was rather far from Gargantua but zooming inward. The Endurance's explosion occurred when the planet was nearing the black hole. Cooper rescues the Endurance after the explosion and lifts it upward, away from the planet. In my interpretation, he lifts the Endurance high enough for Gargantua's huge tidal forces to pry it away from the planet, sending it on a separate trajectory. Centrifugal forces fling man's planet outward on its next distant excursion, while the Endurance heads into the critical orbit. The critical orbit and the volcano analogy. I discussed the critical orbit using the picture shown in Figure 56 in your PDF companion. I first describe this picture heuristically, and then I explain it in physicists' language. Think of the surface in Figure 56 as that of a smooth, granite sculpture sitting on the floor in your home. It sinks down to a deep moat that surrounds a sculpted volcano. The Endurance, after being pried away from man's planet, is like a tiny marble that rolls freely on this granite surface. As it rolls inward toward the moat, the marble picks up speed because of the surface's downward slope. It then rolls up the volcano's side, slowing as it goes, and arrives on the volcano's rim with some residual circumferential motion. And it then rolls around and around on the rim, delicately and unstably balanced between falling inward into the volcano and falling back outward and down to the moat. The volcano's interior is Gargantua, and the volcano's rim is the critical orbit, from which the Endurance launches toward Edmund's planet. The meaning of the volcano: gravitational and circumferential energy. To explain the volcano's meaning, how it relates to the laws of physics, I have to get a bit technical. For the sake of simplicity, let's pretend the Endurance is moving in Gargantua's equatorial plane. For the Endurance's non-equatorial trajectory, the ideas are the same, but because the black hole is not spherical, the details are more complicated. The volcano analogy neatly encapsulates the true physics of the critical orbit and Gargantua's trajectory. To explain how, I need two physics concepts: the Endurance's angular momentum and its energy. After tidal forces pry it apart from man's planet, the Endurance has a certain amount of angular momentum, its circumferential speed around Gargantua times its distance from Gargantua. The relativistic laws tell us that this angular momentum remains fixed, conserved, along the Endurance's trajectory. This means that as the Endurance plunges toward Gargantua, with its distance from Gargantua decreasing, its circumferential speed increases. This is similar to an ice skater, whose whirling speed increases when she moves her arms. See Figure 57 in your PDF companion. The Endurance heads toward Gargantua with a certain amount of energy, which, like its angular momentum, remains constant along its trajectory. This energy consists of three parts: the Endurance's gravitational energy, which gets more and more negative as the Endurance plunges toward Gargantua; its centrifugal energy, its energy of circumferential motion around Gargantua, which increases as the Endurance plunges because the circumferential motion is speeding up; and its radial kinetic energy, its energy of motion toward Gargantua. The surface in Figure 56 in your PDF companion is the Endurance's gravitational energy plus its centrifugal energy plotted vertically, and location in Gargantua's equatorial plane plotted horizontally. Wherever the surface dips downward, the Endurance's gravitational plus centrifugal energy decreases, so its radial kinetic energy must increase, since the total energy is unchanged. Its radial motion must speed up. This is precisely what happens in our intuitive volcano analogy. Outside the moat of Figure 56, the surface's height is controlled by the Endurance's negative gravitational energy. See the gravitational energy label on the figure. By comparison, there the positive centrifugal energy is unimportant. On the outer edge of the volcano, by contrast, the height is controlled by the rising centrifugal energy, which has come to dominate over the gravitational energy. On the inside of the volcano, near Gargantua's horizon, the gravitational energy has grown hugely negative and overwhelms the centrifugal energy, so the surface plunges downward. See Figure 58 in your PDF companion. The critical orbit is on the volcano's rim. The critical orbit: balance of centrifugal and gravitational forces. Upon reaching the volcano's rim, the Endurance, ideally, would travel around and around it at constant speed. Because it moves neither inward nor outward, the inward pull of gravity on the rim must precisely be counterbalanced by the outward centrifugal force that arises from the ship's fast circumferential motion. This indeed is the case, as shown in Figure 59 in your PDF companion, an analog of the force balance plot for Miller's planet. Refer back to Figure 43. At the Endurance's critical orbit, the red curve, the inward gravitational pull on the Endurance, and the blue curve, the outward centrifugal force, cross, so the two forces are in balance. However, the balance is unstable, as our volcano rim analogy suggests. If the Endurance is randomly pushed inward just a bit, then gravity overwhelms the centrifugal force. The red curve rises above the blue curve, so the Endurance is pulled on inward toward Gargantua's horizon. If the Endurance is pushed outward just a bit, then the centrifugal force wins the battle with gravity. The blue curve is above the red curve, so the Endurance is pushed on outward, escaping Gargantua's tight grip. By contrast, on the orbit of Miller's planet, The balance between the gravitational and centrifugal forces is stable. Disaster on the rim. Ejection of TARS and Cooper. In my science interpretation of the movie, the volcano's rim is very narrow, so the critical orbit on the rim is exceedingly unstable. Tiny errors in navigation will send the Endurance careening down toward Gargantua, down into the volcano, or away from Gargantua, down toward the moat. Errors are inevitable, so the Endurance's course must be corrected continually by a well-designed feedback system, like an automobile's cruise control, but much better. In my interpretation, the feedback system is not quite good enough, and the Endurance winds up dangerously far down the inside lip of the volcano. The Endurance must use all the thrust at its disposal to climb back up to the critical orbit. But this is too subtle and technical for action-packed scenes and a hugely diverse audience, so Christopher Nolan chose a simpler, more in-your-face approach. No mention of instability, no mention of feedback. The Endurance simply plunges too close to Gargantua, and Cooper responds with all the thrust he can muster to climb back out and escape Gargantua's grip. The result is the same. Lander 1, piloted by TARS, and Ranger 2, piloted by Cooper, fire their rockets while attached to the Endurance, pushing the Endurance back out of Gargantua's gravitational grip. Then, to get the last possible kick, explosive bolts blow the Endurance apart from Lander 1 and Ranger 2. The Lander and Ranger go plunging downward toward Gargantua, carrying TARS and Cooper with them, and the Endurance is saved. In the movie, there is a tragic parting conversation between Brand and Cooper. Brand doesn't understand why Cooper and TARS must accompany the Lander and Ranger into the black hole. Cooper gives her a rather lame though poetic excuse. Newton's third law. The only way humans have ever figured out for getting somewhere is to leave something behind. This surely is true. But the additional thrust on the Endurance, from Cooper and TARS accompanying the Lander and Ranger into the hole, is awfully small. The greater truth, of course, is that Cooper wants to go into Gargantua. He hopes that he and TARS can learn the quantum gravity laws from a singularity inside Gargantua, and somehow transmit them back to Earth. It is his last, desperate hope for saving all of humanity. The Endurance's launch toward Edmund's planet. The critical orbit is an ideal spot for Brand and the robot Case to launch the Endurance in any desired direction, in particular toward Edmund's planet. How do they control their launch direction? Because the critical orbit is so unstable, a small rocket blast is sufficient to send the Endurance off it. And if the blast is ignited at precisely the right location along the critical orbit and has precisely the right strength, it will send the Endurance in precisely the desired direction. See Figure 60 in your PDF companion. Actually, Figure 60 may leave you unconvinced that Brand and Case can launch in any direction they wish. That's because it doesn't capture the critical orbit's three-dimensional structure. For that, see Figure 61 in the PDF companion to this audiobook. This convoluted critical orbit is a close analog of the trajectories of temporarily trapped light rays inside Gargantua's shell of fire. See Figures 18 and 20 in your PDF companion. Like those light rays, the Endurance is temporarily trapped when on its critical orbit. Unlike the light rays, the Endurance has a control system and rockets, so its launch off the critical orbit is in Brand's and Case's hands. And because of the orbit's convoluted three-dimensional structure, the launch can be in any direction they wish. But their launch leaves behind Cooper and TARS, plunging through Gargantua's horizon, plunging toward Gargantua's singularities. 28. Into Gargantua. Some personal history. Status of science. Truth. In 1985, when Carl Sagan wanted to send his heroine, Eleanor Arroway, Jodie Foster, through a black hole to the star Vega, I told him no. Inside a black hole, she will die. The singularity in the hole's core will tear her apart, chaotically and painfully. I suggested he send Dr. Arroway through a wormhole instead. In 2013, I encouraged Christopher Nolan to send Cooper into the black hole Gargantua. So, what happened in the quarter century between 1985 and 2013? Why did my attitude toward falling into a black hole change so dramatically? In 1985, we physicists thought the cores of all black holes were inhabited by chaotic, destructive BKL singularities, and everything that entered a black hole would be destroyed by the singularities' stretch and squeeze. That was our highly educated guess. We were wrong. In the intervening quarter century, 2 additional singularities were discovered, mathematically, inside black holes, gentle singularities, to the extent that any singularity can be gentle. Gentle enough that Cooper, falling into one, might possibly survive. I'm dubious of survival, but we can't be sure. So I now think it's respectable, in science fiction, to posit survival. Also, in the intervening quarter century, we have learned that our universe is probably a brain in a higher dimensional bulk. So it's respectable, I think, to posit living beings that inhabit the bulk. A very advanced civilization of bulk beings who might save Cooper from the singularity at the last moment. That's what Christopher Nolan chose. Through the Event Horizon. Status of Science, Truth. In Interstellar, when Ranger 2, piloted by Cooper, and Lander 1, piloted by TARS, eject from the Endurance, they spiral down toward Gargantua's event horizon and then through it. What do Einstein's relativistic laws say about this downward spiral? According to those laws, and hence my interpretation of the movie, Brand, watching from the Endurance, can never see the Ranger penetrate the horizon. No signal Cooper tries to send her from inside the horizon can ever get out. The flow of time inside the horizon is downward, and that downward time flow drags Cooper and all signals he sends downward with itself, away from the horizon. So what does Brand see? If she and Case can stabilize the Endurance long enough for her to watch. Because the Endurance and the Ranger are both deep in the cylindrical part of Gargantua's warped space, as shown in Figure 62 in your PDF companion, they are both dragged circumferentially by Gargantua's whirling space with almost the same angular velocity, the same orbital period. So as seen by Brand in her orbiting reference frame, the Ranger drops away from the Endurance almost straight downward toward the horizon. That's what the movie depicts. As Brand watches the Ranger approach the horizon, she must see time on the Ranger slow and then freeze relative to her time. Einstein's laws say. This has several consequences. She sees the Ranger slow its downward motion and then freeze just above the horizon. She sees light from the Ranger shift to longer and longer wavelengths, lower and lower frequencies, becoming redder and redder, until the Ranger turns completely black and unobservable. And bits of information that Cooper transmits to Brand 1 second apart as measured by his time on the Ranger arrive with larger and larger time separations as measured by Brand. After a few hours, Brand receives the last bit that she will ever receive from Cooper, the last bit that Cooper emitted before piercing the horizon. Cooper, by contrast, continues receiving signals from Brand even after he crosses the horizon. Brand's signals have no trouble entering Gargantua and reaching Cooper. Cooper's signals can't get out to Brand. Einstein's laws are unequivocal. This is how it must be. Moreover, those laws tell us that Cooper sees nothing special as he crosses the horizon. He can't know, at least not with any ease, which bit that he transmits is the last one Brand will receive. He can't tell, by looking around himself, precisely where the horizon is. The horizon is no more distinguishable to him than the Earth's equator is to you as you cross it in a ship. These seemingly contradictory observations by Brand and Cooper are a result of 2 things: the warping of time and the finite travel time for the light and information that they send to each other. When I think carefully about both of these things, I don't see any contradiction at all. Sandwiched between singularities. Status of science, educated guess. As the Ranger carries Cooper deeper and deeper into the bowels of Gargantua, he continues to see the universe above himself. Chasing the light that brings him that image is an infalling singularity. The singularity is weak at first, but it grows stronger rapidly as more and more stuff falls into Gargantua and piles up in a thin sheet. Einstein's laws dictate this. Below the Ranger is an outflying singularity, created by stuff that fell into the black hole long ago and was backscattered upward toward the Ranger. The Ranger is sandwiched between the two singularities. Inevitably, it will be hit by one or the other. When I explained the two singularities to Chris, he immediately knew which one should hit the Ranger. The outflying singularity. Why? Because Chris had already adopted, for Interstellar, a variant of the laws of physics that prevents physical objects from ever traveling backward in time. The infalling singularity is produced by stuff that falls into Gargantua long after Cooper falls in. Long after, as measured by the external universe's time, Earth's time. If Cooper is hit by that singularity and survives, the universe's far future will be in his past. He will be so far in our future that, even with the help of bulk beings, he won't be able to return to the solar system until billions of years after he left, if ever. That would prevent him from ever reuniting with his daughter, Murph. So Chris firmly chose Cooper to be hit by the outflying singularity, not the infalling one, hit by the singularity arising from stuff that fell into Gargantua before the Ranger, not after it. Chris's choice, though, presents a bit of a problem for my scientist's interpretation of the movie. But not a problem so severe as backward time travel. If the Ranger falls directly into Gargantua from the critical orbit, then its infall is slow enough that the infalling singularity will catch up to it and hit it. For the Ranger to hit the outflying singularity instead, as Chris wants, the Ranger must nearly outrun the infalling singularity, which is descending at the speed of light. The Ranger can do so if it is given a large inward kick. How? The usual. By a slingshot around a suitable intermediate mass black hole soon after leaving the Endurance. What does Cooper see inside Gargantua? Status of science, speculation. Looking up as he falls inward, Cooper sees the external universe. Because his infall has been sped up, he sees time in the external universe flow at roughly the same rate as his own time, and he sees the image of the external universe reduced in size, from about half of the sky to roughly a quarter. When I was first shown the movie's depiction of this, I was pleased to discover that Paul Franklin's team got it right, and also got right something I had missed. In the movie, the image of the universe above is surrounded by Gargantua's accretion disk. Can you explain why this must be so? Cooper sees all this above him, but he doesn't see the infalling singularity. It is moving downward toward him at the speed of light, chasing but not catching the light rays that bring him images of the disk and universe above. Because we are rather ignorant of what goes on inside black holes, I told Chris and Paul that I'd be comfortable if they used their imaginations in depicting what Cooper sees coming up at him from below as he falls. I made only one request. Please don't depict Satan and the fires of Hades inside the black hole like the Disney Studios did in their Black Hole movie. Chris and Paul chuckled. They weren't tempted in the least. When I saw what they did depict, it made great sense. Looking downward, Cooper should see light from objects that fell into Gargantua before him and are still falling inward. Those objects need not emit light themselves. He can see them in reflected light from the accretion disk above, just as we see the moon in reflected sunlight. I expect those objects to be mostly interstellar dust, and this could explain the fog he encounters in the movie as he falls. Cooper can also overtake stuff that's infalling more slowly than he. This may explain the white flakes that hit and bounce off his Ranger in the movie. Rescued by the Tesseract. Status of science, speculation. In my science interpretation, as the Ranger nears the outflying singularity, it encounters mounting tidal forces. Cooper ejects just in the nick of time. Tidal forces tear the Ranger apart. Visually, it splits in two. At the singularity's edge, the Tesseract awaits Cooper, placed there, presumably, by bulk beings. 29. The Tesseract. In Interstellar, the entrance to the Tesseract is a white checkerboard pattern. Each white square is the end of a beam. Cooper, entering the Tesseract, falls down a channel between beams. Dazed and confused, lashing out at what appear to be bricks along the channel wall, but turn out to be books. The channel leads to a large chamber, where he floats and struggles, gradually getting oriented. The chamber is Christopher Nolan's unique take on one three-dimensional face of the four-dimensional Tesseract, enhanced by Paul Franklin and his visual effects team. The chamber and its environs are remarkably complex. Seeing them for the first time, I felt as disoriented as Cooper, even though I know what a Tesseract is. Chris and Paul had enriched the Tesseract so greatly that I only fully understood after talking with them. Here's what I know, and what I learned, filtered through my physicist's eyes. I begin with the standard, simple Tesseract, and then I build up to Chris's complexified Tesseract. From point to line to square to cube to Tesseract. A standard Tesseract is a hypercube, a cube in 4 space dimensions. In figures 63 and 64 in your PDF companion, I walk you through what this means. If we take a point, top of figure 63, and move it in 1 dimension, we get a line. The line has 2 faces, ends. They are points. The line has 1 dimension. It extends along 1 dimension. Its faces have 1 less dimension, 0. If we take a line and move it in a dimension perpendicular to itself, middle of figure 63, we get a square. The square has 4 faces. They are lines. The square has 2 dimensions. Its faces have 1 less dimension, 1. If we take a square and move it in a dimension perpendicular to itself, bottom of figure 63, we get a cube. The cube has 6 faces. They are squares. The cube has 3 dimensions. Its faces have 1 less dimension, 2. The next step should be obvious, but to visualize it, I need to redraw the cube as you would see it if you were up close to one of the orange faces. See top of figure 64 in your PDF companion. Here, the original square, the small dark orange one, when moved towards you to form the cube, appears to enlarge to become the cube's front face, the outer square. If we take a cube and move it in a dimension perpendicular to itself, bottom of figure 64, we get a tesseract. The picture of the tesseract is analogous to the one above it, of the cube. It looks like 2 cubes inside each other. The inner cube has expanded outward in the picture to sweep out the 4-dimensional volume of the tesseract. The tesseract has 8 faces. They are cubes. Can you identify and count them? The tesseract has 4 space dimensions. Its faces have 1 less dimension, 3. The tesseract and its faces share 1 time dimension, not shown in the figure. The chamber Cooper enters in the film is one of the tesseract's 8 cubical faces, though, as I said earlier, modified in a clever, complex way by Chris and Paul. Before explaining their clever modifications, I use the standard simple tesseract to describe my interpretation of the movie's early tesseract scenes. Cooper transported in the tesseract. Status of science, speculation. Because Cooper is made of atoms held together by electric and nuclear forces, all of which can exist only in 3 space dimensions and 1 time, he is confined to reside in one of the tesseract's 3 space-dimensional faces, cubes. He can't experience the tesseract's 4th spatial dimension. In my interpretation of the movie, the tesseract ascends from the singularity into the bulk. Being an object with the same number of space dimensions as the bulk, 4, it happily inhabits the bulk, and it transports 3-dimensional Cooper lodged in its three-dimensional face, through the bulk. Now, recall that the distance from Gargantua to Earth is about 10 billion light-years as measured in our brain, our universe with its 3 space dimensions. However, as measured in the bulk, that distance is only about 1 AU, the distance from the Sun to the Earth. So, traveling with whatever propulsion system the bulk beings provided, the Tesseract, in my interpretation, can quickly carry Cooper across our universe via the bulk to Earth. Figure 65 in your PDF companion is a snapshot from that trip. One spatial dimension is suppressed from the snapshot, so the Tesseract is a 3-dimensional cube in a 3-dimensional bulk, and Cooper has become a 2-dimensional icon of a man in a 2-dimensional face of the cube, traveling parallel to our 2-dimensional universe, brain. To match what is shown in the movie, I imagine this trip is very quick, just a few minutes, while Cooper is still dazed and falling. As he comes to rest, floating in the large chamber, the Tesseract docks beside Murph's bedroom. Docking. The view into Murph's bedroom. Status of science. Speculation. How does this docking work? In my interpretation, arriving in the bulk near Earth, the Tesseract must penetrate the 3-centimeter thick ADS layer that encases our brain in order to reach Murph's bedroom. Presumably, the bulk beings who built the Tesseract equipped it with technology to push the ADS layer to the side, clearing the way for its descent. Figure 66 in your PDF companion shows the Tesseract, after the clearing, docked alongside Murph's bedroom in Cooper's farmhouse. Again, one spatial dimension is suppressed, so the Tesseract is depicted as a 3-dimensional cube, and the farmhouse and bedroom and Murph are 2-dimensional, as, of course, is Cooper. The back face of the Tesseract coincides with Murph's bedroom. I'll explain that more carefully. The back face is a 3-dimensional cross-section of the Tesseract that resides in Murph's bedroom in the same sense as the circular cross-section of a sphere resides in a 2-dimensional brain. See Figure 47 in your PDF companion, and a spherical cross-section of a hypersphere resides in a 3-dimensional brain. See Figure 48. So everything in Murph's bedroom, including Murph herself, is also inside the Tesseract's back face. When a light ray traveling out from Murph reaches the common edge of Murph's bedroom and the Tesseract, it has 2 places to go. The ray can stay in our brain, traveling along Route 1 of Figure 66 in your PDF companion, out an open door, or into a wall where it is absorbed. Or the ray can stay in the Tesseract, traveling along Route 2 into and through the next Tesseract face, and then onward to Cooper's eyes. Some of the ray's photons go along Route 1, others go along Route 2, bringing Cooper an image of Murph. Now, look at Figure 67 in your PDF companion, in which I restore the suppressed dimension. When Cooper looks through the right wall of his chamber, he sees into Murph's bedroom through its right wall, right white light ray. Looking through the left wall of his chamber, Cooper sees into Murph's bedroom through its left wall, left white light ray. Looking through his back wall, he sees into the bedroom through its back wall. Looking through his front wall, orange light ray, he sees into the bedroom through its front wall, though this is not obvious in Figure 67. Can you explain why it is true? Looking along the yellow ray, he sees down through her ceiling. Looking along the red ray, he sees up through her floor. To Cooper, as he changes his gaze from one direction to another, it seems like he is orbiting Murph's bedroom. This is how Chris described it when he first showed me his complexified Tesseract. In Figure 67, all 6 light rays have to pass through intermediate cubes, Tesseract faces, before reaching Murph's bedroom. In the movie, they don't travel any noticeable distance from chamber to bedroom, so Chris and Paul must have shrunk the Tesseract in one dimension. See the gray arrow and notation, make thin, in Figure 67. After that shrinkage, every face of Cooper's chamber looks directly and immediately into one of the faces, wall or floor or ceiling, of Murph's bedroom with no intervening space. So to Cooper, the situation looks like figure 68 in your PDF companion. He sees 6 bedrooms, one bordering each face of his chamber, but all identical except for his viewing direction. In fact, they are all identical. There is only one bedroom, although to Cooper there appear to be 6. Nolan's complexified tesseract. Status of science, speculation. If we were to look at a scene from Interstellar showing Cooper floating in his chamber inside the tesseract, we would notice that it looks very different from figure 68. This is because of the complex and rich modifications that Chris conceived, and Paul and his team implemented. The first thing I noticed when I saw Chris's complexified tesseract was the threefold enlargement of Cooper's chamber. So the bedroom attached to each chamber face covers only a third of the face. I depict this in figure 69 in your PDF companion with all the other tesseract complexities removed and the chamber's back 3 faces hidden from view. The next thing I noticed were 2 extrusions extending out of each bedroom along the 2 directions transverse to Cooper's chamber. See figure 70 in your PDF companion. As Chris and Paul explained it to me, wherever these extrusions intersect, there is a bedroom. For example, bedrooms 7, 8, and 9, as well as the original 1 through 6. The extrusions extend indefinitely, creating at their intersections a seemingly infinite lattice of bedrooms and of chambers like Cooper's. See dashed edges in figure 70 in your PDF companion. For example, the labeled faces of bedrooms 7, 8, and 9 face into a chamber whose edges are indicated with dots. The back left bottom corner of that chamber overlaps the front right top corner of Cooper's chamber. Tars gives us a clue to the meaning of the extrusions and the latticework of bedrooms and chambers when he tells Cooper, "You've seen that time is represented here as a physical dimension." Chris and Paul elaborated on that clue for me. The bulk beings, they explained, are displaying time for the blue extrusions as flowing along the blue arrowed direction in figure 70, and for the green extrusions along the green arrowed direction, and for the brown extrusions along the brown arrowed direction. To understand this in greater detail, let's focus momentarily on the single pair of extrusions that intersect in bedroom 2. Refer to figure 71 in the PDF companion to this audiobook. Cross-sections through the room that are vertical in the picture travel rightward with passing time, along the blue time arrow, and as they travel, they create the blue extrusion. Similarly, cross-sections that are horizontal travel upward as time passes, along the green time arrow, creating the green extrusion. Where the 2 sets of cross-sections intersect, where the extrusions intersect, there is a bedroom. The same is true for all other extrusions. At each intersection of 2 extrusions, the cross-sections they carry produce a bedroom. Because of the cross-section's finite speed, the various bedrooms are out of time sync with each other. For example, if it takes 1 second for cross-sections to travel along each extrusion from one bedroom to the next, then all the bedrooms shown in figure 72 in your PDF companion are to the future of image 0 by the number of seconds shown in black. In particular, bedroom 2 is 1 second ahead of bedroom 0. Bedroom 9 is 2 seconds ahead of bedroom 0, and bedroom 8 is 4 seconds ahead of bedroom 0. Can you explain why? In the movie, the time lapse between adjacent bedrooms is closer to 1/10 of a second than a full second. By watching adjacent bedrooms carefully as the curtains in Murph's bedroom window blow in the wind, you can estimate the time between bedrooms. Of course, each bedroom in the movie's tesseract is Murph's actual bedroom at a particular moment of time, the time labeled in black in figure 72. Cooper can move far faster than the flow of time in the bedroom extrusions, so he can easily travel through the tesseract complex to most any bedroom time that he wishes. To travel most rapidly into the future of Murph bedroom time, Cooper should move along a diagonal of his chamber in the direction of increasing blue, green, and brown time, rightward, upward, and inward. That is, along the diagonal dashed violet line in figure 72. Diagonals like this are devoid of extrusions. They are open channels along which Cooper can travel. In the movie, we see him traveling along such an open diagonal channel to get from the bedroom time of the early ghostly book falls to the bedroom time of the wristwatch ticking. Is Cooper really traveling forward and backward in time as he moves diagonally up and down through the complex? Forward and backward in the manner that Amelia Brand speculates bulk beings can when she says, "To them, time may be just another physical dimension. To them, the past might be a canyon they can climb into, and the future a mountain they can climb up. But to us, it's not. Okay?" What are the rules governing time travel in Interstellar? 30. Messaging the past. Communicating rule sets to a movie audience. Status of science: truth. Before Christopher Nolan became Interstellar's director and rewrote the screenplay, his brother Jonah taught me about rule sets. To maintain the desired level of suspense in a science fiction movie, Jonah said, the audience must be told the rules of the game, the movie's rule set. What do the laws of physics and the technology of the era allow, and what do they forbid? If the rules are not clear, then many in the audience will expect some miraculous event to save the heroine out of the blue, and tension will fail to mount as it should. Of course, you can't say to the audience, "Here is the rule set for this movie." It must be communicated in a subtle and natural way. And Chris is a master of this. He communicates his rule sets through the characters' dialogue. Next time you watch Interstellar, how can you resist watching it again? Look within the film for his telltale bits of rule set dialogue. Christopher Nolan's rule set for time travel. Status of science: speculation. It turns out that backward time travel is governed by the laws of quantum gravity, which are terra almost incognita, so we physicists don't know for sure what is allowed and what not. Chris made two specific choices for allowed and forbidden time travel, his rule set. Rule 1. Physical objects and fields with 3 space dimensions, such as people and light rays, cannot travel backward in time from one location in our brain to another, nor can information that they carry. The physical laws, or the actual warping of space-time, prevent it. This is true whether the objects are forever lodged in our brain or journey through the bulk in a 3-dimensional face of a tesseract, from one point in our brain to another. So, in particular, Cooper can never travel to his own past. Rule 2. Gravitational forces can carry messages into our brain's past. In the movie, Rule 1 generates mounting tension. Murph grows older and older as Cooper lingers near Gargantua. With no possibility to travel backward in time, there's a growing danger he'll never return to her. Rule 2 gives Cooper hope. Hope that he can use gravity to transmit the quantum data backward in time to young Murph, so she can solve the professor's equation and figure out how to lift humanity off Earth. How do these rules play out in Interstellar? Messaging Murph. Status of science: speculation. When falling into and through the tesseract, Cooper truly does travel backward relative to our brain's time, from the era when Murph is an old woman to the era when she is 10 years old. He does this in the sense that, looking at Murph in the tesseract bedrooms, he sees her 10 years old, and he can move forward and backward relative to our brain's time, the bedroom's time, in the sense that he can look at Murph at various bedroom times by choosing which bedroom to look into. This does not violate rule number 1 because Cooper has not re-entered our brain. He remains outside it, in the tesseract's 3-dimensional channel, and he looks into Murph's bedroom via light that travels forward in time from Murph to him. But just as Cooper can't re-enter our brain in Murph's 10-year-old era, so he can't send light to her. That would violate Rule 1. The light could bring her information from Cooper's personal past, which is her future, information from the era when she is an old woman, backward in time information from one location in our brain to another. So there must be some sort of one-way space-time barrier between 10-year-old Murph in her bedroom and Cooper in the Tesseract, rather like a one-way mirror or a black hole horizon. Light can travel from Murph to Cooper, but not from Cooper to Murph. In my scientist's interpretation of Interstellar, the one-way barrier has a simple origin. Cooper, in the Tesseract, is always in 10-year-old Murph's future. Light can travel toward the future from Murph to him. It can't travel to the past from him to Murph. However, gravity can surmount that one-way barrier, Cooper discovers. Gravitational signals can go backward in time from Cooper to Murph. We first see this when Cooper desperately pushes books out of Murph's bookcase. To explain this scene in the movie, I must tell you a bit more about the bedroom extrusions, as Chris and Paul Franklin explained them to me. Let's focus on the front blue extrusion in figures 70 and 71 in your PDF companion. Recall that this extrusion is a set of vertical cross-sections through Murph's bedroom, traveling forward in bedroom time along the blue direction, rightward. Each object in the bedroom, for example, each book, contributes to the bedroom's extrusion. In fact, the book has its own extrusion, which travels forward in time along the blue arrow direction as part of the bedroom's larger extrusion. We physicists call a variant of this extrusion the book's world tube, and we call the extrusion of each particle of matter in the book the particle's world line. So, the book's world tube is a bundle of world lines of all the particles that make up the book. Chris and Paul also use this language. The thin lines that you see in the movie, running along the extrusions, are world lines of particles of matter in Murph's bedroom. In the movie, Cooper slams his fist on the book's world tube over and over again, creating a gravitational force, which travels backward in time to the moment in Murph's bedroom that he is seeing and then pushes on the book's world tube. The book's tube responds by moving. The tube's motion appears to Cooper as an instantaneous response to his pushes, and the motion becomes a wave traveling leftward down the tube. When the motion gets strong enough, the book falls out of the bookcase. By the time Cooper has received the quantum data from TARS, he has mastered this means of communication. In the movie, we see him pushing with his finger on the world tube of a watch's second hand. His pushes produce a backward-in-time gravitational force, which makes the second hand twitch in a Morse-encoded pattern that carries the quantum data. The Tesseract stores the twitching pattern in the bulk, so it repeats over and over again. When 40-year-old Murph returns to her bedroom 3 decades later, she finds the second hand still twitching, repeating over and over again the encoded quantum data that Cooper has struggled so hard to send her. How does the backward-in-time gravitational force work? I'll describe my physicist's interpretation after I tell you what I know, or think I know, about backward time travel. Time travel without a bulk. What I think I know. Status of science, educated guess. In 1987, triggered by Carl Sagan, I realized something amazing about wormholes. If wormholes are allowed by the laws of physics, then Einstein's relativistic laws permit transforming them into time machines. The nicest example of this was discovered a year later by my close friend Igor Novikov in Moscow, Russia. Igor's example, figure 73 in your PDF companion, shows that a wormhole's transformation into a time machine might occur naturally, without the aid of intelligent beings. In figure 73, the bottom mouth of the wormhole is in orbit around a black hole, and the upper mouth is far from the black hole. Because of the black hole's intense gravitational pull, Einstein's law of time warps dictates that time flow more slowly at the lower mouth than at the upper mouth. More slowly, that is, when compared along the path of gravity's intense pull, the dashed purple path through the external universe in the figure. I presume, for concreteness, that this has produced a 1-hour lag, so when compared through the external universe, the bottom clock, shown in the figure, is 1 hour behind the top clock, and this time lag is continuing to grow. Since there is only a tiny gravitational pull inside the wormhole, Einstein's law of time warps dictates that, as seen through the wormhole, time flows at essentially the same rate in the upper mouth as in the lower mouth. So there is no time lag when the clocks are compared through the wormhole. They are synchronized. Suppose, further, for concreteness, that the distance from mouth to mouth in the external universe is short enough that you can traverse it in 5 minutes as measured by the clocks, and you can travel through the wormhole in 1 minute. Then this wormhole has already become a time machine. You leave the upper mouth at time 2 o'clock as measured by the clock there, and travel through the external universe to the lower mouth, arriving at 2:05 upper clock time and 1:05 lower clock time. You then make a 1-minute trip upward through the wormhole from lower mouth to upper. Since the clocks are synchronized through the wormhole, you reach the upper mouth at time 1:06 as seen by both clocks. You arrive back at your starting point 54 minutes before your 2 o'clock departure, and you meet your younger self. Some days earlier, when the time difference was much less, the wormhole was not yet a time machine. It became a time machine at the first moment when something, moving at the highest possible speed, the speed of light, was able to travel along your route and arrive back at the top mouth at the very moment it started out. If that something is a particle of light, a photon, for example, then we began with 1 photon and we now have 2 at the starting place and time. After those 2 make the trip, we have 4 at that same place and time, then 8, then 16. There is a growing crescendo of energy coursing through the wormhole, perhaps enough that the energy's gravity destroys the wormhole at the very moment it is becoming a time machine. It would seem easy to prevent this. Just shield the wormhole from photons. However, there is something you cannot shield out: quantum fluctuations of light with ultra-high frequency, fluctuations that inevitably exist according to the quantum laws. In 1990, Sung-Won Kim, a postdoctoral student in my research group, and I used the quantum laws to compute the fate of such fluctuations. We found a growing explosion. We thought at first that the explosion was too weak to destroy the wormhole. The wormhole would become a time machine despite the explosion, we thought. Stephen Hawking convinced us otherwise. The fate of the explosion is controlled by the laws of quantum gravity, he convinced us. Only when those laws are well understood will we know for sure whether backward time travel is possible. Stephen, however, was so convinced that the ultimate answer will be no time machines that he codified this in what he calls his chronology protection conjecture. The laws of physics will always prevent backward time travel, thereby keeping the universe safe for historians. Many researchers have struggled, over the past 20 years, to prove or disprove Hawking's chronology protection conjecture. The bottom line today, I think, remains the same as in the early 1990s, when he and I were debating the issue. Only the laws of quantum gravity know for sure. Time travel with a bulk. Status of science, speculation. All this research and conclusions, educated guesses, are based on the laws of physics that prevail if there is no bulk with a large fifth dimension. What happens to time travel if a large bulk does exist, as in Interstellar? We physicists find Einstein's relativistic laws so compelling that we suspect they hold in the bulk as well as in our brain. So Lisa Randall, Raman Sundram, and others have extended his laws into the 5-dimensional bulk by one simple step: adding a new dimension to space. That extension proceeds mathematically in a straightforward and beautiful manner, which makes us physicists think we may be on the right track. In my interpretation of the movie, Professor Brand uses this extension as a foundation for his equation and for his struggle to understand gravitational anomalies. If this speculative extension is correct, then time behaves fundamentally the same in the bulk as in our brain. In particular, objects and signals in the bulk, like those in our brain, can only move in one direction through locally measured time, local bulk time, toward the future. They cannot move backward, locally. If backward time travel is possible in the bulk, it can be achieved only by journeying out through the bulk's space and returning before the journey started, while always moving forward in local bulk time. This is a bulk analog of the round trip in Figure 73 in your PDF companion. Messaging MRF, my physicist's interpretation. Status of science, speculation. This description of time underlies my physicist's interpretation of Cooper's messaging MRF. Recall that the tesseract is an object whose faces have 3 space dimensions and interior has 4. The interior is part of the bulk. Everything we see in the movie's tesseract scenes lies in the faces. Cooper, MRF, MRF's bedroom, the bedroom's extrusions, the world tubes of the book and watch, all lie in tesseract faces. We never see the tesseract's bulk interior. We can't see it, since light can't travel through 4 space dimensions, only 3. However, gravity can do so. In my interpretation, when Cooper sees a book in MRF's bedroom, he does so via a light ray that travels in faces of the tesseract, for example, the red dashed ray in Figure 74 in the PDF companion to this audiobook. And when he pushes on a book's world tube, or on the world tube of the watch's second hand, he generates a gravitational signal, a gravitational wave in the bulk, that spirals into and through the tesseract's bulk interior, along the violet curve in Figure 74. The signal travels forward in local bulk time, but backward in bedroom time, arriving before it started out. It is this gravitational signal that pushes the book out of the bookcase and twitches the watch's second hand. This is rather like one of my favorite Escher drawings, Waterfall. Downward in the drawing is analogous to the forward flow of bedroom time, and the flowing water is analogous to the forward flow of local time. A leaf on the water is carried forward with the water, just like signals in the bulk are carried forward in local time. When carried by water down the waterfall, the leaf is like the light ray from the book to Cooper. It travels not only forward in local time, but also downward, forward in bedroom time. When carried along the aqueduct, the leaf is like the gravitational signal from Cooper to the book. It travels forward in local time, but upward, so backward in bedroom time. How, in this interpretation, do I explain Amelia Brand's description of time as seen by beings in the bulk? To them, time may be just another physical dimension. To them, the past might be a canyon they can climb into, and the future a mountain they can climb up. Einstein's laws, extended into the bulk, tell us that local bulk time can't behave this way. Nothing in the bulk can go backward in local bulk time. However, when looking into our brain from the bulk, Cooper and bulk beings can and do see our brain's time, bedroom time, behave like Brand says. As seen from the bulk, our brain's time can look like just another physical dimension, to paraphrase Brand. Our brain's past looks like a canyon that Cooper can climb into by traveling down the tesseract's diagonal channel, and our brain's future looks like a mountain that Cooper can climb up by traveling up the tesseract's diagonal channel. This is my physicist's interpretation of Brand's words, and Chris interprets them similarly. Touching Brand across the 5th dimension. Status of science, speculation. In Interstellar, with the quantum data safely in MRF's hands, Cooper's mission is finished. The tesseract, carrying him through the bulk, begins to close. As it is closing, he sees the wormhole, and within the wormhole he sees the Endurance on its maiden voyage to Gargantua. As he sweeps past the Endurance, he reaches out and gravitationally touches Brand across the 5th dimension. She thinks she has been touched by a bulk being. She has, by a being riding through the bulk in a rapidly closing tesseract, by an exhausted, older Cooper. 31. Lifting colonies off Earth. Status of science, speculation. Early in Interstellar, when Cooper first visits the NASA facility, he is shown a giant, cylindrical enclosure being constructed to carry thousands of humans into space and house them for many generations. A space colony. And he's told there are others being constructed elsewhere. "How does it get off Earth?" Cooper asks the professor. "Those first gravitational anomalies changed everything," the professor replies. "Suddenly we knew that harnessing gravity was real. So I started working on the theory, and we started building this station." At the end of Interstellar, we see everyday life back on even keel, inside the colony, floating in space. How did it get lifted into space? The key, of course, was the quantum data, in my scientist's interpretation, the quantum gravity laws, that TARS extracted from Gargantua's singularity and Cooper transmitted to Murph. In my interpretation, by discarding quantum fluctuations from those laws, Murph learned the non-quantum laws that govern gravitational anomalies. And from those laws, she figured out how to control the anomalies. As a physicist, I'm eager to know the details. Was Professor Brand on the right track in the equations that covered his blackboards? Did he really have half the answer, as Murph asserted before getting the quantum data? Or was he way off? Is the secret to anomalies and controlling gravity something completely different? Perhaps a sequel to Interstellar will tell us. Christopher Nolan is a master of sequels. Just watch his Batman trilogy. But one thing seems clear. Murph must have figured out how to reduce Newton's gravitational constant g inside the Earth. Recall that the Earth's gravitational pull is given by Newton's inverse square law. G equals gm over r squared, where r squared is the squared distance from the Earth's center, m is the mass of the Earth, and g is Newton's gravitational constant. Cut Newton's g in half and you reduce the Earth's gravity by 2. Cut g by 1,000 and you reduce the Earth's gravity by 1,000. In my interpretation, with Newton's g reduced inside the Earth to, say, 1,000th its normal value for, say, an hour, rocket engines could lift the enormous colonies into space. As a byproduct, in my interpretation, the Earth's core, no longer compressed by the enormous weight of the planet above, must have sprung outward, pushing the Earth's surface upward. Gigantic earthquakes and tsunamis must have followed, wreaking havoc on Earth as the colonies soared into space. A terrible price for the Earth to pay on top of its blight-driven catastrophe. When Newton's g was restored to normal strength, the Earth must have shrunk back to its normal size, wreaking more earthquake and tsunami havoc. But humanity was saved, and Cooper and 94-year-old Murph were reunited. Then Cooper set out in search of Amelia Brand in the far reaches of the universe. Some parting thoughts. Status of science. Truth. Every time I watch Interstellar and return to this book, I'm amazed at the enormous variety of science they contain, and the richness and beauty of that science. More than anything, I'm moved by Interstellar's underlying optimistic message. We live in a universe governed by physical laws. By laws that we humans are capable of discovering, deciphering, mastering, and using to control our own fate. Even without bulk beings to help us, we humans are capable of dealing with most any catastrophe the universe may throw at us, and even those catastrophes we throw at ourselves, from climate change to biological and nuclear catastrophes. But doing so, controlling our own fate, requires that a large fraction of us understand and appreciate science, how it operates, what it teaches us about the universe, the Earth, and life, what it can achieve, what its limitations are due to inadequate knowledge or technology, how those limitations may be overcome, how we transition from speculation to educated guess to truth, how extremely rare are revolutions in which our perceived truth changes, yet how very important. I hope this book contributes to that understanding. This concludes The Science of Interstellar by Kip Thorne. Narrated by Eric Michael Summerer. Copyright 2014 by Kip Thorne. This unabridged audiobook is published by arrangement with W. W. Norton and Company, Incorporated, and was produced in the year 2015 by Tantor Media, Incorporated, which holds the copyright thereto. Please visit tantor.com for more information on our growing library of unabridged audiobooks and to take advantage of special offers. Or call toll-free 877-7-TANTOR to request a catalog.